Welcome to R Machine Learning Solutions by Yu-Wei Chu, a video course by Pact Publishing. I am Alistair Ruane and I will be the voiceover artist for this course. Yu-Wei Chu is the founder of Largit Data. He has previously worked for Trend Micro as a software engineer with the responsibility of building big data platforms for business intelligence and customer relationship management systems. In addition to being a startup entrepreneur and data scientist, he specializes in using Spark and Hadoop to process big data and apply data mining techniques for data analysis. Yu-Wei is also a professional lecturer and has delivered lectures on Python, R, Hadoop, and tech talks at a variety of conferences. In 2013, Yu-Wei reviewed Bioinformatics with R Cookbook, Pact Publishing. For more information, please visit his personal website at www.ywchu.com. Okay, so now let's talk about R. The most widely used tool for machine learning and data analysis is the R language. The R programming language offers a variety of learning packages and visualization functions which enable users to analyze data on the fly. Now let's look at our course. We start off with the basic R operations, from reading data into R, manipulating data, and performing simple statistics to visualizing data. In the next section, we walk you through the processes of transforming, analyzing, and visualizing the RMS Titanic data. We will then learn how to perform descriptive statistics and inferential statistics on data. The next section will teach us how to use different regression models to make sense of numeric relationships. We then learn how to fit data into a tree-based classifier, k-nearest neighbor classifier, logistic regression classifier, or the naive Bayes classifier. The next section introduces two complex but powerful classification methods, neural networks and support vector machines. The next section reveals some measurements that you can use to evaluate the performance of a fitted model. Following that, we introduce how to use the power of ensemble learners to produce better classification and regression results. We will then learn how to apply the clustering technique to segment customers and further compare differences between each clustering method. The next section discovers associated terms and underlying frequent patterns from transaction data. We will then learn how to compress and restore an image with the dimension reduction approach. Lastly, we will learn about R Hadoop, from setting up the R Hadoop environment to actual big data processing and machine learning on big data. The course takes a practical approach to teaching you how to perform machine learning with R. Each of the 12 sections are introduced to you by dividing this topic into several simple tasks. Through step-by-step instructions provided on each video, the reader can construct a predictive model by using a variety of machine learning packages. This video course will take you from the very basics of R to creating insightful machine learning models with R. You will only need a computer with access to the internet and the ability to install the R environment. The examples provided in this course were coded and tested with R version on a computer with Microsoft Windows installed on it. These examples should also work with any recent version of R installed on either Mac OS X or a Unix-like OS. This course is ideal for those of you who want to learn how to use R for machine learning and gain insights from data. Regardless of your level of experience, this course covers the basics of applying R to machine learning through advanced techniques. While it is helpful if you are familiar with basic programming or machine learning concepts, you do not require prior experience to benefit from this course. So let's start this journey together. I promise you it will be a ride full of fun and knowledge. Hello, welcome to the section, Getting Started with R. In this section, we will first download and install R and RStudio and prepare our environment for working with R. We will then install and load necessary packages. Then, we will perform basic operations, such as reading, writing, and manipulating data. We will apply basic statistics and visualize data with the help of plots. Lastly, we will get dataset for machine learning. Now we start with the first video of the section, downloading and installing R. This video will give detailed instructions on how to download and install R. To use R, we must first install it on our computer. If you are new to the R language, you can find a detailed introduction, language history, and functionality on this website. When you are ready to download and install R, please access this link. To download and install R for Windows, go to the R-CRAN website and click on the Download R link, that is cran.r-project.org/mirrors.html. You may select the mirror location closest to you. So here I am selecting the location, India. Select the correct download link based on your operating system. For me, it is Windows, so here I will click on that. As the installation of R differs for Windows and Mac, the steps required to install R for each OS are provided here. Click on Download R for Windows, then click on Base. Once you do that, click on Download R 3.3.1 for Windows. The installation file starts downloading. You can see the file here. It will take a little time. Once the download is finished, you can double-click on the installation file and begin installing R. The Windows installation of R is quite straightforward. The installation of GUI may instruct you on how to install the program step by step. Public license, destination, location, next is select components, startup options, startup menu folder, and select additional tasks. Leave all the installation options at the default settings if you do not want to make any changes. This will take a little time. After successfully completing the installation, a shortcut to the R application will appear in your Start menu, which will open the R console. This is the R console. For Mac OS X users, go to Download R for Mac OS X as shown in this screenshot. Click on the latest version .pkg file extension according to your Mac OS version. Double-click on the downloaded installation file .pkg extension and begin to install R. Leave all the installation options as the default settings if you do not want to make any changes. Follow the on-screen instructions: Introduction, README, License, Destination, Select, Installation Type, Installation, Summary, and click on Continue to complete the installation. After the file is installed, you can use Spotlight Search or go to the Application folder to find R. Click on R to open the R console. As an alternative to downloading a mac.pkg file to install R, Mac users can also install R using Homebrew. Download xquartz-2.x.x.dmg from this link. Double-click on the .dmg file to mount it. Update Brew with this command. Clone the repository and symlink all its formulae to homebrew/science using this command. Install G4tran, install R. For Linux users, there are precompiled binaries for Debian, Red Hat, SUSE, and Ubuntu. Alternatively, you can install R from a source code. Besides downloading precompiled binaries, you can install R for Linux through a package manager. Here are the installation steps for CentOS and Ubuntu. Now we will see how to download and install R on Ubuntu. First, add the entry to the /etc/apt/sources.list file. Then, update the repository. Install R with the following command. Start R in the command line. Next, downloading and installing R on CentOS 5. Get RPM CentOS 5 RHEL EPEL repository of CentOS 5. Install CentOS 5 RHEL EPEL repository. Update the installed packages. Install R through the repository. Start R in the command line. Downloading and installing R on CentOS 6. Get RPM CentOS 5 RHEL EPEL repository of CentOS 6. Install the CentOS 5 RHEL EPEL repository. Update the installed packages. Install R through the repository. Start R in the command line. In this video, we learnt to download and install R on different systems successfully. Amazing! In the next video, we will see how to download and install RStudio. Downloading and installing RStudio. Previously, we downloaded and installed R. This video shows how to download and install RStudio. To write an R script, one can use RConsole, RCommander, or any text editor, Emacs, Vim, or Sublime. However, the assistance of RStudio, an integrated development environment, IDE, for R, can make development a lot easier. RStudio provides comprehensive facilities for software development. Built-in features such as syntax highlighting, code completion, and smart indentation help maximize productivity. To make R programming more manageable, RStudio also integrates the main interface into a 4-panel layout. It includes an interactive R console, a tabbed source code editor, a panel for the currently active objects, history, and a tabbed panel for the file browser, plot window, package install window, R help window. Moreover, RStudio is open source and is available for many platforms, such as Windows, Mac OS X, and Linux. RStudio requires a working R installation. We have already installed R. When RStudio loads, it must be able to locate a version of R. You must therefore have R installed on your OS before proceeding to install RStudio. Access RStudio's official site by using this link. For a desktop version installation, click on Download RStudio Desktop and choose the RStudio recommended for your system. I will download the relevant packages for Windows. Install RStudio by double-clicking on the downloaded packages. For Windows users, follow the on-screen instruction in the wizard and install the application. For Mac users, simply drag the RStudio icon to the Applications folder. After the installation is complete, go to Start and you can see the RStudio icon here. Click on it. You can see 4 panes on the screen: the Data and Files pane, the Console, the Workspace and History pane, and the Plot, Files, Packages and Help pane. For Ubuntu Debian and Red Hat CentOS users, perform these steps for downloading and install RStudio. For Debian version 6 and higher and Ubuntu 10.04 and higher 32-bit. For 64-bit. For Red Hat CentOS version 4 or higher 32-bit. For 64-bit. In this video, we downloaded and installed RStudio successfully. Great! In the next video, we will install and load R packages. Installing and loading packages. In the previous video, we downloaded and installed RStudio. In this video, we will be looking at installing and loading R packages. After successfully installing R, users can download, install, and update packages from the repositories. As R allows users to create their own packages, official and non-official repositories are provided to manage these user-created packages. CRAN is the official R package repository. Currently, the CRAN package repository features 6,379 available packages. Through the use of the packages provided on CRAN, users may extend the functionality of R to machine learning, statistics, and related purposes. CRAN is a network of FTP and web servers around the world that store identical, up-to-date versions of code and documentation for R. You may select the closest CRAN mirror to your location to download packages. First, we start an R session on your host computer. To load a list of installed packages, we will run this query, so you can see the libraries of our package. For setting the default CRAN mirror, this is the command. R will return a list of CRAN mirrors, and then ask the user to either type a mirror ID to select it or enter 0 to exit. So here, I will just choose India, which is at 25. So that is done. Then we will install a package from CRAN, taking package E1071 as an example. It will take a little time. You can see the download progress here, so the downloaded binary packages are in this folder. Then we update a package from CRAN, taking package E1071 as an example. Load the package. If you would like to view the documentation of the package, you can use the Help function. You can see the documentation of the package in the Help pane. If you would like to view the documentation of the function, you can use the Help function again. You can see information on the support vector machine. Alternatively, you can use the Help shortcut, $, to view the help document for this function. This gives the same output. If the function does not provide any documentation, you may want to search the supplied documentation for a given keyword. For example, if you wish to search for documentation related to SVM, then you can use this command. Alternatively, you can use $! as the shortcut for help.search. To view the argument taken for the function, simply use the args function. For example, if you would like to know the argument taken before the lm function, you can use this command. These are the arguments. Some packages will provide examples and demos. You can use example or demo to view an example or demo. For example, one can view an example of the LM package and a demo of the graphics package by typing these commands. Here you can see the examples of the LM command. And these are the workgroups created. When you type return and enter, you can see the plot example. To start with it, first you type enter. You keep on typing return to get the next figure. So you can see different plots examples. It will come out of the loop once it is over. To view all the available demos, you may use the demo function to list all of them. Let's do that. So you can see the available demos here. For example, in Package Graphics, these are the demos available. Besides installing packages from CRAN, there are other R package repositories, including CRANtastic, a community site for rating and reviewing CRAN packages, and RForge, a central platform for the collaborative development of R packages. In addition to this, Bioconductor provides R packages for the analysis of genomic data. If you would like to find relevant functions and packages, please visit the list of task views at this link, or search for keywords at rseek.org, so you can type in any keywords you want to learn about here. In this video, we have installed and loaded R packages successfully. In the next video, we will learn how to read and write data in R. Reading and writing data. In the previous video, we learnt about installation and loading packages in R. In this video, we will introduce methods to load data, either from a file into the memory or use the predefined data within R. Before starting to explore data, you must load the data into an R session. First, start an R session on your machine. As this recipe involves steps towards the file I/O, if the user does not specify the full path, read and write activity will take place in the current working directory. You can simply type getwd in the R session to obtain the current working directory location. When I do that, I get the directory. However, if you would like to change the current working directory, you can use setwd path, where path can be replaced as your desired path to specify the working directory. To view the built-in datasets of R, type this command. R will return a list of datasets in a dataset package, and the list comprises the name and description of each dataset. To load the dataset iris into an R session, type the command data iris. The dataset iris is now loaded into the data frame format, which is a common data structure in R to store a data table. This is the iris dataset. To view the data type of iris, simply use the class function. This is of the type data.frame. The data.frame console print shows that the iris dataset is in the structure of the data frame. Now we will use the save function to store an object in a file. For example, to save the loaded iris data into mydata.rdata, use this command. So you can see mydata.rdata file is created here. Use the load function to read a saved object into an R session. For example, to load iris data from mydata.rdata, use this command. In addition to using built-in datasets, R also provides a function to import data from text into a data frame. For example, the read.table function can format a given text into a data frame, so you can use this command to do that. You can also use row.names and col.names to specify the names of columns and rows, so this is the command you need to execute. To view the class of the test.data variable, you need to run this command. The class function shows that the test.data variable contains a data frame. In addition to importing data by using the read.table function, you can use the write.table function to export data to a text file. So we do that using this command. The write.table function will write the content of test.data into a test.txt, which is created here with a separation delimiter as whitespace. Similar to write.table, write.csv can also export data to a file. However, write.csv uses a comma as the default delimiter. You can see a test.csv file created here. This is a test.txt file, and this is a text.csv file. With the read.csv function, the CSV file can be imported as a data frame. However, the last example writes column and row names of the data frame to the test.csv file. Therefore, specifying header to true and row names as the first column within the function can ensure the read data frame will not treat the header and the first column as values. Let's see how we can do this. This is the code we need to run. It will create a csv.data file here. For the load, read.table, and read.csv functions, the file to be read can also be a complete URL. For supported URLs, use !, followed by URL for more information. On some occasions, data may be in an Excel file instead of a flat text file. The write.xls package allows writing an object into an Excel file, with a given variable in the first argument and the file to be written in the second argument. Let's install the write.xls package. Here the package is installed. Then we load the write XLS package like this. Next, we use the write XLS function to write the data frame iris into a file named iris.xls, and here the data is written in the file. In this video, we have learned how to read and write data. Awesome! In the next video, we will see how to use R to manipulate data. Using R to manipulate data. In the previous video, we learned to read and write data. In this video, we will discuss how to use the built-in R functions to manipulate data. As data manipulation is the most time-consuming part of most analysis procedures, you should gain knowledge of how to apply these functions on data. Ensure you have installed R on your operating system. First, we subset the data using the bracelet notation. Then load the dataset iris into the R session. This is the command for that. To select values, you may use a bracket notation that designates the indices of the dataset. The first index is for the rows and the second for the columns. This is the line of code. You can see 5.1 as output. You can also select multiple columns using C. Here we are doing that. You can then use str to summarize and display the internal structure of sepal.iris. To subset data with the rows of given indices, you can specify the indices at the first index with the bracket notation. Here we see how to subset data with the top 5 records with the sepal.length column and the sepal.width selected. This is the command to do that. Let's use the str function to see the output. Here is the output. It is also possible to set conditions to filter the data. For example, to filter returned records containing the Setosa data with all 5 variables. In the following example, the first index specifies the returning criteria, and the second index specifies the range of indices of the variable returned. So this is the code for that. Again, use str for seeing the output. Alternatively, the which function returns the indexes of the satisfied data. The following example returns indices of the iris data containing species equal to Setosa. Here are the indices. The indices returned by the operation can then be applied as the index to select the iris containing the Setosa species. The following example returns the Setosa with all 5 variables. So here, all 5 variables can be seen. Next is subsetting data using the subset function. Besides using the bracket notation, R provides a subset function that enables users to subset the data frame by observations with a logical statement. First, subset species, sepal length, and sepal width out of the iris data. To select the sepal length and width out of the iris data, one should specify the column to be subset in the select argument. So I do that using these lines of code. You can see the output here. This reveals that sepal.data contains 150 objects with the sepal.length variable and sepal width. On the other hand, you can use a subset argument to get subset data containing Setosa only. In the second argument of the subset function, you can specify the subset criteria. We see the output using str function. Most of the time, you may want to apply a union or intersect, a condition while subsetting data. The OR and AND operations can be further employed for this purpose. For example, if you would like to retrieve data with petal.width is more than 0.2 and petal.length is less than 1.4, we use the AND functions to do that. So this is the output. Next is merging data. Merging data involves joining 2 data frames into a merged data frame by common column or row name. The following example shows how to merge the flower type data frame and the first 3 rows of the iris with a common row name within the species column. So we run these lines of code. Here you can see the output as follows. Then we order data. The order function will return the index of a sorted data frame with the specified column. The following example shows the results from the first 6 records with the sepal length ordered from big to small iris data. This is the function used. The sub and gsub functions allow using regular expression to substitute a string. The sub and gsub functions perform the replacement of the first and all other matches respectively. Here I'm using the sub function, and this is the corresponding output. Also, you can run the gsub function. Here is the output. In this video, we performed data manipulation in R successfully. Awesome! In the next video, we will apply basic R statistics. Applying basic statistics. In the previous video, we performed data manipulation in R. In this video, we cover basic statistics that can be applied to a dataset. R provides a wide range of statistical functions, allowing users to obtain the summary statistics of data, generate frequency and contingency tables, produce correlations, and conduct statistical inferences. Ensure you have installed R on your operating system. First, we load the iris data into an R session using data function. Now, let's observe the format of the data. It is a data.frame. The iris dataset is a data frame containing 4 numeric attributes: petal length, petal width, sepal width, and sepal length. For numeric values, you can perform descriptive statistics, such as mean, standard deviation, variance, minimum, maximum, median, range, and quantile. These can be applied to any of the 4 attributes in the dataset. So we will get to each of the values one by one. The preceding example demonstrates how to apply descriptive statistics on a single variable. In order to obtain summary statistics on every numeric attribute of the data frame, one may use sapply. For example, to apply the mean on the first 4 attributes in the iris data frame, ignore the NA value by setting NA.rm as true, so you can run this code to get that. As an alternative to using supply to apply descriptive statistics on given attributes, R offers the summary function that provides a full range of descriptive statistics. Here, the summary function will provide the mean, median, 25th, and 75th quartiles, min and max of every iris dataset numeric attribute. This is the summary function, and you can see the output of all the attributes. We saw how to output the descriptive statistics of a single variable. R also provides the correlation for users to investigate the relationship between variables. The following example generates a 4x4 matrix by computing the correlation of each attribute pair within the iris. So this is the code you need to run. R also provides a function to compute the covariance of each attribute pair within the iris. That is the cov function. You can see the output here. Statistical tests are performed to access the significance of the results. Here we demonstrate how to use a t-test to determine the statistical differences between 2 samples. We will perform a t-test on the petal width of an iris in either the Setosa or versicolor species. If we obtain a p-value less than 0.5, we can be certain that the petal width between the Setosa and versicolor will vary significantly. Here is the output for that. Alternatively, you can perform a correlation test on the sepal length to the sepal width of an iris, and then retrieve a correlation score between the 2 variables. The stronger the positive correlation, the closer the value is to 1. The stronger the negative correlation, the closer the value is to -1. Here we have the output for that. If you need to compute an aggregated summary statistics against data in different groups, you can use the aggregate and reshape functions to compute the summary statistics of data subsets. First, we use aggregate to calculate the mean of each iris attribute group by the species using aggregate. We then use reshape to calculate the mean of each iris attribute group by the species. After installing the reshape package, run the lines of code and the corresponding output can be seen here. For information on reshape and aggregate, refer to the help documents by using $reshape or $aggregate. In this video, we performed basic statistics on a dataset. Excellent! In the next video, we will visualize data. Visualizing data. In the previous video, we performed basic statistics on a dataset in R. In this video, we will present some basic functions to plot charts and demonstrate how visualizations are helpful in data exploration. Visualization is a powerful way to communicate information through graphical means. Visual presentations make data easier to comprehend. Ensure that you have installed R on your operating system. First, we load the iris data into the R session. Then we calculate the frequency of species within the iris using the table command. We print the table. So this is the table with data. As the frequency in the table shows, each species represents a third of the iris data. We can draw a simple pie chart to represent the distribution of species within the iris. So you can see the pie chart here. The histogram creates a frequency plot of sorts along the x-axis. The following example produces a histogram of the sepal length. So here we are plotting a histogram. In the histogram, the x-axis presents the sepal length, and the y-axis presents the count for different sepal lengths. The histogram shows that for most irises, sepal lengths range from 4 cm to 8 cm. Box plots, also named box and whisker graphs, allow you to convey a lot of information in one simple plot. In such a graph, the line represents the median of the sample. The box itself shows the upper and lower quartiles. The whiskers show the range. So you can see a box plot here. The preceding screenshot clearly shows the median and upper range of the petal width of the setosa is much shorter than versicolor and virginica. Therefore, the petal width can be used as a substantial attribute to distinguish iris species. A scatter plot is used when there are 2 variables to plot against one another. This example plots the petal length against the petal width, and colored dots in accordance to species it belongs to. To represent a scatter plot, you can run this code. The preceding plot is a scatter plot of the petal length against the petal width. As there are 4 attributes within the iris dataset, it takes 6 operations to plot all combinations. However, R provides a function named pairs, which can generate each subplot in one figure. You can see the plot of all the combinations here. ggplot2 is another plotting system for R, based on the implementation of Leyland Wilkinson's Grammar of Graphics. It allows users to add, remove, or alter components in a plot with a higher abstraction. However, the level of abstraction results is slow compared to lattice graphics. For those of you interested in the topic of ggplot, you can refer to this site. In this video, we have performed basic data visualization functions. In the next video, we will get dataset for machine learning in R. This is the last video of the section, getting a dataset for machine learning. In the previous video, we visualized data in R. This video introduces how to get a sample dataset from the UCI Machine Learning repository. While R has a built-in dataset, the sample size and field of application is limited. Apart from generating data within a simulation, another approach is to obtain data from external data repositories. A famous data repository is the UCI Machine Learning repository, which contains both artificial and real datasets. Ensure that you have installed R on your operating system. First, you need to access the UCI Machine Learning repository at this site. Then you need to click on View All Datasets. Here you will find a list of datasets containing field names such as name, data types, default task, attribute types, number of instances, number of attributes, and year. Use Ctrl F to search for Iris. Click on Iris. This will display the data folder and the dataset description. Click on Data Folder, which will display a directory containing the Iris dataset. You can then either download iris.data or use the read.csv function to read the dataset. This is the command we need to run where the URL for the iris.data is provided. Then you can see the output using the head function. KD Nuggets offers a resourceful list of datasets for data mining and data science. You can explore the list to find the data that satisfies your requirements. So this is the website. So, we learned how to get a dataset for machine learning in this video. Let's summarize what we learnt in this section. We started with the download and installation of R and RStudio. Then we installed and loaded basic packages. We performed reading and writing on data. We also performed data manipulation and visualization basics. We also applied basic statistics on a dataset and procured a dataset for machine learning. Superb! In the next section, we will perform data exploration with RMS Titanic. See you there. Hello. Welcome to a new section of the course, Data Exploration with RMS Titanic. In this section, we will perform a sample data exploration based on the dataset of passengers surviving the Titanic shipwreck. First, we will collect data from the online source, Kaggle, clean data through data munging, perform basic exploratory data analysis to discover important attributes that might give a prediction of the survival rate, perform advanced exploratory data analysis using the classification algorithm to predict the survival rate of the given data, and finally, perform model assessment to generate a prediction model. Let's start with the first video of the section, reading a Titanic dataset from a CSV file. In this video, we will see how to read a dataset from a CSV file. First, let's learn more about data exploration. Data exploration helps a data consumer to focus on searching for information with a view to forming a true analysis from the gathered information. Furthermore, with the completion of the steps of data munging, analysis, modeling, and evaluation, users can generate insights and valuable points from their focused data. In a real data exploration project, there are 6 steps involved in the exploration process. They are asking the right questions, data collection, data munging, basic exploratory data analysis, advanced exploratory data analysis, model assessment. Ask the right questions. When the user presents their question, for example, "What are my expected findings after the exploration is finished?" or "What kind of information can I extract through the exploration?" different results will be given. Therefore, asking the right question is essential in the first place, for the question itself determines the objective and target of the exploration. Data collection. Once the goal of exploration is determined, the user can start collecting or extracting relevant data from the data source with regard to the exploration target. Mostly, data collected from disparate systems appears unorganized and diverse in format. Clearly, the original data may be from different sources, such as files, databases, or the internet. To retrieve data from these sources requires the assistance of the File I/O function, JDBC, ODBC, web crawler, and so on. This extracted data is called raw data, which is because it has not been subjected to processing or been through any other manipulation. Most raw data is not easily consumed by the majority of analysis tools or visualization programs. Data munging. The next phase is data munging, or wrangling, a step to help map raw data into a more convenient format for consumption. During this phase, there are many processes such as data parsing, sorting, merging, filtering, missing value completion, and other processes to transform and organize the data and enable it to fit into a consumer structure. Later, the mapped data can be further utilized for data aggregation, analysis, or visualization. Basic exploratory data analysis. After the data munging phase, users can conduct further analysis toward data processing. The most basic analysis is to perform exploratory data analysis. Exploratory data analysis involves analyzing a dataset by summarizing its characteristics. Performing basic statistical aggregation and visual methods are also crucial tasks to help the user understand data characteristics, which are beneficial for the user to capture the majority, trends, and other outliers easily through plots. Advanced exploratory data analysis. Until now, the descriptive statistic gives a general description of the data features. However, one would like to generate an inference rule for the user to predict data features based on input parameters. Therefore, the application of machine learning enables the user to generate an inferential model, where the user can input a training dataset to generate a predictive model. After this, the prediction model can be utilized to predict the output value or label based on given parameters. Model assessment. Finally, to assess whether the generating model performs the best in the data estimation of a given problem, one must perform a model selection. The selection method here involves many steps, including data preprocessing, tuning parameters, and even switching the machine learning algorithm. However, one thing that is important to keep in mind is that the simplest models frequently achieve the best results in predictive or exploratory power, whereas complex models often result in overfitting. To start the exploration, we need to retrieve a dataset from Kaggle. We had a look at some of the samples in a previous section. Here, we introduce methods to deal with real-world problems. To retrieve data from Kaggle, you need to first sign up for a Kaggle account, then log in to the account for further exploration. Go to Getting Started with R to retrieve the data list. You can see a list of data files for download, as shown in the following table. Click on the CSV file to download. It will download the train.csv file. Go to the R session. Then, make sure the downloaded file is placed under the current directory. You can use the getWD function to check the current working directory. If the downloaded file is not located in the working directory, move the file to the current working directory. Or, you can use setWD to set the working directory to where the downloaded files are located. So here, when I run this, I get my directory as C. Next, one can use read.csv to load data into the data frame. So this is the function. Here, one can use the read.csv function to read train.csv to frame the data with the variable name set as train.data. However, in order to treat the blank string as NA, one can specify that NA.strings equals either NA or an empty string. This is the command you need to run. So train.data is created. Then, check the loaded data with the str function. Here is the output. You can see the table with different values for different attributes of passengers. On Kaggle, much of the data on science is related to competitions, which mostly refer to designing a machine learning method to solve real-world problems. Most competitions on Kaggle are held by either academia or corporate bodies, such as Amazon or Facebook. In fact, they create these contests and provide rewards such as bonuses or job prospects. So, you can find all this on this site, Kaggle Competitions. Thus, there are many data scientists who are attracted to registering for a Kaggle account to participate in competitions. A beginner in a pilot exploration can participate in one of these competitions, which will help them gain experience by solving real-world problems with their machine learning skills. To create a more challenging learning environment as a competitor, a participant needs to submit their output answer and will receive the assessment score, so that each one can assess their own rank on the leaderboard. In this video, we read a dataset from a CSV file successfully. In the next video, we will convert types on character variables. This is the second video of the section, Converting Types on Character Variables. Previously, we learnt to read a Titanic dataset from a CSV file. In this video, we will convert character variables into factors. Talking about statistics, there are 4 measurements: nominal, ordinal, interval, and ratio. Nominal variables are used to label variables such as gender and name. Ordinal variables are measures of non-numeric concepts such as satisfaction and happiness. Interval variables shows numeric scales which tell us not only the order but can also show the differences between the values, such as temperatures in Celsius. A ratio variable shows the ratio of a magnitude of a continuous quantity to a unit magnitude. Ratio variables provide order, differences between the values, and a true zero value, such as weight and height. In R, different measurements are calculated differently, so you should perform a type conversion before applying descriptive or inferential analytics towards the dataset. You need to have loaded the Titanic training data into the R session, with the read.csv function and an argument of na.strings equal to na, and the blank string assigned. Then assign the loaded data from train.csv into the train.data variables. You can see that the train.data is loaded here. Use the str function to print the overview of the Titanic data. You can see the table containing data of passengers here. To transform the variable from the int numeric type to the factor categorial type, you can cast factor. This is the line of code we need to run. Another is the class factor. Print out the variable with the str function, and again, you can see the p-class and survived are transformed into factor. Besides factor, there are more type conversion functions. For numeric types, there are is.numeric and as.numeric. For character, there are is.character and as.character. For vector, there are is.vector and as.vector. For matrix, there are is.matrix and as.matrix. Finally, for data frame, there are is.data.frame and as.data.frame. In this video, we converted character variables into factors successfully. Great! In the next video, we will detect missing values. This is the third video of the section, Detecting Missing Values. In the previous video, we converted character types into factors. This video will focus on detecting missing values within the Titanic dataset. Missing values reduce the representativeness of the sample and furthermore might distort inferences about the population. You need to have converted the p-class attribute and survived to a factor type. In R, a missing value is noted with the symbol NA, not available, and an impossible value is NaN, not a number. The is.na function is used to denote which index of the attribute contains the NA value. Here, we apply it to the age attribute first. So let's run this code. So, I can see all the missing values here. The is.na function indicates the missing value of the age attribute. To get a general number of how many missing values there are, you can perform a sum to calculate this. So here we get 177 missing values. To calculate the percentage of missing values, one method adopted is to count the number of missing values against non-missing values. So here we find that the value is 0.1986. To get a percentage of the missing value of the attributes, you can use supply to calculate the percentage of all the attributes. So as you can see, the percentage of missing value for age attribute is 19.87%. Besides simply viewing the percentage of a missing data, one may also use the Amelia package to visualize the missing values. Here we use install.packages and require to install Amelia and load the package. However, before the installation and loading of the Amelia package, you are required to install RCPP beforehand. So, we install the Amelia package. You can see the Amelia package is loaded. Then, use the mismap function to plot the missing value map. When you run this, you get the Plot in Plot tab. The missing value is beige-colored, and its observed value is dark red. The x-axis shows different attribute names, and the y-axis shows the recorded index. To handle the missing values, we introduced Amelia to visualize them. Apart from typing console commands, you can also use the interactive GUI of Amelia and Amelia View, which allows users to load datasets, manage options, and run Amelia from a windowed environment. To start running Amelia View, simply type Amelia View in the R console. You will see a window like this. It is the Amelia View. Awesome! In this video, we detected missing values for attributes. In the next video, we will impute missing values. This is the fourth video of the section, Imputing Missing Values. In the previous video, we understood how to detect missing values. In this video, we will have a look at imputing the missing values that are detected. After detecting the number of missing values within each attribute, we have to impute the missing values since they might have a significant effect on the conclusions that can be drawn from the data. This video will require train.data loaded in the R session and have the previous task completed by converting pclass and survived to a factor type. First, list the distribution of port of embarkation. Here, we add the useNA equals always argument to show the number of NA values contained within the train.data. When I run this line, I get this output. The number of NA values here is 2. Assign the 2 missing values to a more probable port, that is, the most counted port, which is Southampton in this case. When we run the necessary commands, we get this output. You can see that the NA value is becoming 0 and Southampton value is increased by 2. In order to discover the types of titles contained in the names of train.data, we first tokenized train.data $name by blank, a regular expression pattern as //s+, shown here, and then count the frequency of occurrence with the table function. After this, since the name title often ends with a period, we use the regular expression to grep the word containing the period. In the end, sort the table in decreasing order. So, first we follow the steps and get the table of different titles in the descending order. To obtain which title contains missing values, you can use strmatch, provided by the stringer package, to get a substring containing a period, then bind the column together with cbind. Finally, by using the table function to acquire the statistics of missing values, you can work on counting each title. So, first we load the library stringer. Then we obtain the missing values and bind the column together using cbind. You can see the TB dataset is loaded here. You can see the table here. For example, the number of people with title Master are 4. For a title containing a missing value, one way to impute data is to assign the mean value for each title, not containing a missing value. So this is the portion of the code. We find the mean value for each title. We run these lines one by one. We can see that the mean values are created here on the right-hand side. mean.mr, mean.mast, mean.miss, mean.mr, and mean.mrs. Then we assign the missing value with the mean value of each title. We need to do this for every attribute. You can learn more about the honorific entry from Wikipedia. This is the page. Mr. is used for a man, regardless of his marital status. Master is used for young men or boys, especially used in the UK. Miss is usually used for unmarried women, though also used in schools. Mrs. is used for married women. Ms. for gender neutral. Doctor is not shown here. Doctor is used for a person in the US who owns his first professional degree. There are common titles, formal titles, professional titles, and religious titles. In this video, we have learnt imputing missing values. In the next video, we will explore and visualize data. This is the 6th video of the section, Exploring and Visualizing Data. Previously, we had a look at imputing missing values. This video will introduce how to use basic plotting techniques with a view to help the user with exploratory analysis. After imputing the missing values, one should perform an exploratory analysis, which involves using a visualization plot and an aggregation method to summarize the data characteristics. The result helps the user gain a better understanding of the data in use. This recipe needs the previous task to be completed by imputing the missing value in the age and embarked attribute. First, you can use a bar plot and histogram to generate descriptive statistics for each attribute, starting with passenger survival. So we use the bar plot function for that. We can generate the bar plot of passenger class. So here, when we run this, we have bar plot for passenger class. Next, we outline the gender data with the bar plot. You can see the passenger gender plot when we do that. We then plot the histogram of the different ages with the hist function. You can see the histogram here. We can plot the bar plot of sibling passengers. We find out how many passengers are or have siblings. Next, we can get the distribution of the passenger parch. Next, we plot the histogram of the passenger fares. So this is how we do that. The bar plot for fare according to the number of passengers is shown in the plot. Finally, one can look at the port of embarkation. You see the number of people for different ports. Use bar plot to find out which gender is more likely to perish during shipwrecks. So here you can see the number of male and female passengers that can survive. You can see that the female passengers perishing is less than the male passengers. Next, we should examine whether the P-class factor of each passenger may affect the survival rate. You can make a note that the passengers of the third class will perish more. Next, we examine the gender composition of each P-class. We get the bar plot. There is male domination, i.e., number of males higher than number of females in all the 3 classes. Furthermore, we examine the histogram of passenger ages. You can see the passenger age histogram. To examine more details about the relationship between the age and survival rate, one can use a box plot. You can see the box plot here. To categorize people with different ages into different groups such as children below 13, youths 13 to 19, adults 20 to 65, and senior citizens above 65, execute these commands. You will get the percentage of children, youths, adults, and senior citizens, respectively. Apart from using bar plots, histograms, and box plots to visualize data, one can also apply Mosaic Plot in the VCD package to examine the relationship between multiple categorical variables. For example, when we examine the relationship between the survived and the P-class variables, the application performed is this, and this was the output for it. Amazing! For more information about the shipwreck, one can read the history of RMS Titanic. Refer to this wiki page. Some of the protocol practiced at that time may have substantially affected the passenger survival rate. In this video, we explored and visualized data successfully. In the next video, we will understand how to predict passenger survival using a decision tree. This is the sixth video of the section, Predicting Passenger Survival with a Decision Tree. In the previous video, we performed data exploration and visualization. In this video, we will introduce how to use a decision tree to predict passenger survival rates from the given variables. The exploratory analysis helps users gain insights into how single or multiple variables may affect the survival rate. However, it does not determine what combinations may generate a prediction model so as to predict the passenger's survival. On the other hand, machine learning can generate a prediction model from a training dataset so that the user can apply the model to predict the possible labels from the given attributes. We will use the data train.data that we have already used. First, we construct a data split.data function with three input parameters, data, p, and s. The data parameter stands for the input dataset. The p parameter stands for the proportion of generated subset from the input dataset, and the s parameter stands for the random seed. Then we split the data with 70% assigned to the training dataset and the remaining 30% for the testing dataset. For the condition tree, one has to use the ctree function from the party package. Therefore, we install and load the party package. The party package is being installed and loaded. We then use survived as a label to generate the prediction model in use. After that, we assign the classification tree model into the train.ctree variable. You can see the output here. We use a plot function to plot the tree. You can see the plot here. This video covers issues relating to classification algorithms and conditional inference trees. Since we do not discuss the background knowledge of the adapted algorithm, it is better for the user to use the help function to view the documents related to ctree in the party package, if necessary. There is a similar decision tree-based package named rpart. The difference between party and rpart is that ctree in the party package avoids the following variable selection bias of rpart and ctree in the party package, tending to select variables that have many possible splits or many missing values. Unlike the others, ctree uses a significance testing procedure in order to select variables, instead of selecting the variable that maximizes an information measure. Besides ctree, one can also use svm to generate a prediction model. To load the svm function, load the E1071 package first, and then use the svm build to generate this prediction. Here, we use the SVM to show how easy it is that you can immediately use different machine learning algorithms on the same dataset when using R. For further information on how to use SVM, please refer to the further section, Neural Network SVM. In this video, we predicted passenger survival using decision tree. In the next video, we will validate the power of prediction with a confusion matrix. This is the 7th video of the section, validating the power of prediction with a confusion matrix. In the previous video, we predicted passenger survival with a decision tree. In this video, we will perform analysis using confusion matrix. After constructing the prediction model, it is important to validate how the model performs while predicting the labels. Before assessing the prediction model, first be sure that the generated training set and testing dataset are within the R session. We start using the constructed train.ctree model to predict the survival of the testing set. First, we install the Caret package and then load it. So it is getting loaded and installed. It will take time. After loading Caret, one can use a confusion matrix to generate the statistics of the output matrix. You can see the confusion matrix and the various performance attributes and their values. A Caret package, classification and regression training, helps to make iterating and comparing different predictive models very convenient. The package also contains several functions, including data splits, common pre-processing, which contains creating dummy variables, identifying zero and near-zero variance predictors, finding correlated predictors, centering scaling, and so on. Training, using cross-validation, and common visualizations, for example, feature plot. In this video, we did performance analysis using confusion matrix. In the next video, we will assess performance using the ROC curve. This is the last video of the section, assessing performance with the ROC curve. In the previous video, we learnt to assess performance using confusion matrix. In this video, we will see how we can use the ROC curve to measure the performance of the prediction model. Another measurement is by using the ROC curve. This requires the ROCR package, which plots a curve according to its true positive rate against its false positive rate. Before applying the ROC curve to assess the prediction model, first be sure that the generated training set, these are the training sets, testing dataset, and built prediction model, ctree.predict, are within the R session. First, we prepare the probability matrix. Then we install and load the ROCR package. Here the packages are being installed. Next, we create an ROCR prediction object from probabilities. Prepare the ROCR performance object for the ROC curve. TPR equals true positive rate, FPR equals false positive rate, and the area under curve, AUC. Plot the ROC curve, with colorize as true, and put AUC as the title. You can see the AUC graph. To get more information on the ROCR, you can read the paper ROCR, Visualizing Classifier Performance in R Bioinformatics by Singh T, Sander O, Berenwinkel N, and Lengar T. So we assessed performance using ROC curve in this video. Let's have a quick recap of what we learned in this section. We started with reading a dataset from a CSV file. Then we converted character type variables into factors. Then we moved on to detecting missing values and imputing them. We also performed data visualization and exploration. We then used decision tree to detect passenger survival. Lastly, we validated power of prediction with confusion matrix and assessed performance using ROC curve. In the next section, we will see everything about R and statistics. Welcome to a new section of the course, R and statistics. In this section, we will discuss examples of data sampling, probability distribution, and univariate descriptive statistics. We will also understand correlations and multivariate analysis, and linear regression and multivariate analysis. We will perform a number of tests on our data, such as exact binomial test, student's t-test, Kolmogorov-Smirnov test, Wilcoxon ranked sum and signed rank test, and Pearson's chi-squared test. Additionally, we will also conduct one-way and two-way ANOVA. Let's start with the first video of this section, Understanding Data Sampling in R. In this video, we will demonstrate how to generate samples in R. To apply statistical methods in R, the user can categorize the method of implementation into descriptive statistics and inferential statistics. Descriptive statistics. These are used to summarize the characteristics of the data. The user can use mean and standard deviation to describe numerical data, and use frequency and percentages to describe categorical data. Inferential statistics. Based on the pattern within a sample data, the user can infer the characteristics of the population. The methods related to inferential statistics are for hypothesis testing, data estimation, data correlation, and relationship modeling. Inference can be further extended to forecasting, prediction, and estimation of unobserved values, either in or associated with the population being studied. Sampling is a method to select a subset of data from a statistical population, which can use the characteristics of the population to estimate the whole population. Make sure that you have an R working environment. In order to generate random samples of a given population, the user can simply use the sample function. This is the sample function. You can see the samples created here. To specify the number of items returned, the user can set the assigned value to the size argument. So here, the size argument is used and assigned the value 5. As mentioned in the argument, you can see that there are only 5 samples now. Moreover, the sample can also generate Bernoulli trials by specifying replace equal to true. By default, it will be assigned to false. So our output is a population of zeros and ones only. The 1 indicates true, and zeros indicate false or failure. In R, the default package provides another sample method, sample.int, where both n and size must be supplied as integers. So here is our sample.int function, with n as 20 and size as 12. In this video, we generated samples of data of different sizes. Amazing! In the next video, we will work on a probability distribution in R. Hi, this is the second video of the section, Operating Probability Distribution in R. In the previous video, we have understood data sampling. In this video, we will demonstrate how to generate probability distribution in R. Probability distribution and statistics analysis are closely related to each other. For statistics analysis, analysts make predictions based on a certain population, which is mostly under a probability distribution. Therefore, if you find that the data selected for prediction does not follow the exact assumed probability distribution in experiment design, the upcoming results can be refuted. In other words, probability provides the justification for statistics. Since most distribution functions originate from the stats package, make sure the library stats are loaded. You can check that by running the library function as shown here. Here, my library is loaded. For a normal distribution, the user can use dnorm, which will return the height of a normal curve at 0, so we do that this way. So here we get the height of the curve as 0.398. Then the user can change the mean and the standard deviation in the argument. We will assign the mean as 3 and standard deviation as 5. You can see the height of the curve changes. Next, plot the graph of a normal distribution with the curve function, so. In contrast to dnorm, which returns the height of a normal curve, the pnorm function can return the area under a given value. This is the demonstration for that. So the area is 0.933. Alternatively, to get to the area above a certain value, you can specify the option lower dot tail to false. You can see the area is 0.066. You may notice that the addition of the areas above the curve and below the curve will give the value 1. To plot the graph of pnorm, the user can employ a curve function. You can see the curve in the Plot tab. To calculate the quantiles for a specific distribution, you can use qnorm. The function qnorm can be treated as the inverse of pnorm, which returns the z-score of a given probability. We see the output as 0. To generate random numbers from a normal distribution, one can use the rnorm function and specify the number of generated numbers. Also, one can define optional arguments, such as the mean and the standard deviation. So on running these lines of code, we get this plot. To calculate the uniform distribution, the runIf function generates random numbers from a uniform distribution. The user can specify the range of the generated numbers by specifying variables, such as the minimum and maximum. Here, the user generates 100 random variables from 0 to 5. When we plot the histogram, it looks like this in the Plot tab. Lastly, if you would like to test the normality of the data, the most widely used test for this is the Shapiro-Wilks test. Here we demonstrate how to perform a test of normality on both samples from the normal and uniform distributions, respectively. Here we conduct the normality test on both the normal and uniform distribution samples, respectively. In both outputs, you can find the p-value in each test result. The p-value shows the changes, which show the sample comes from a normal distribution. If the p-value is higher than 0.05, we can conclude that the sample comes from a normal distribution. On the other hand, if the value is lower than 0.05, we conclude that the sample does not come from a normal distribution. Here, dataset X is from a normal distribution, and dataset Y is not from a normal distribution, which is also mentioned previously. Besides the normal distribution, you can obtain a t-distribution, binomial distribution, and chi-squared distribution by using the built-in functions of R. You can use the help function to access further information about this. For a t-distribution, you can type this command. All the information related to t-distribution is displayed here. For a binomial distribution, this is the command. For the chi-squared distribution, you can see the output here. To learn more about the distributions in the package, the user can access the help function with the keyword distributions to find all related documentation on this. You can learn about the distribution in the stats package here. In this video, we worked with probability distribution functions in R. Great! In the next video, we will work with univariate descriptive statistics in R. This is the third video of the section, working with univariate descriptive statistics in R. In the previous video, we worked on probability distribution functions. In this video, we introduce some basic functions used to describe a single variable. Univariate descriptive statistics describes a single variable for unit analysis, which is also the simplest form of quantitative analysis. We need to apply descriptive statistics to a sample data. Here, we use the built-in mtcars data as our example. First, load the mtcars data into a data frame with a variable named mtcars. You can see here the data is loaded. To obtain the vector range, the range function will return the lower and upper bound of the vector. So we get 10.4 as lower bound and 33.9 as upper bound. Compute the length of the variable. We do that using length function. You can see the length as 32. Then we obtain the mean of MPG using the mean function. The mean is 20.09, as you can see. Next, we obtain the median of the input vector using the median function. The median value is 19.2. To obtain the standard deviation of the input vector, we use the SD function. We get the deviation as 6.026. To obtain the variance of the input vector, we use the var function. The variance value is 36.324. The variance can also be computed with the square of standard deviation. You can see that the value is the same as obtained using the var function. To obtain the interquartile range, IQR, we run the IQR function and get the range as 7.375. To obtain the quantile, we run these lines of code. We get this output. To obtain the maximum of the input vector, max function is used. 33.9 is the max value. To obtain the minima of the input vector, 10.4 is the minimum value. Next, we obtain a vector with the elements that are the cumulative maxima. You can see the output here. As you can see, the cumulative maximum vector contains numbers that are consistently increasing. For more information, refer to this link. To obtain a vector with elements that are the cumulative minima, here is the output. You observe that the values are continuously decreasing. For more information on cumin, refer to the link. To summarize the dataset, you can apply the summary function. You can see the min, mean, median, etc. of all the variables. To obtain a frequency count of the categorical data, take a CYL of mtcars as an example. Here is the output. To obtain a frequency count of numerical data, you can use a stem plot to outline the data shape. Stem produces a stem and leaf plot of the given values. You can see the output here. The plot is called a stem and leaf plot because of its structure with decimal point at the center of the stem, first digit, on the left-hand side, and leaf, second digit, on the right-hand side. You can use a histogram of ggplot to plot the same stem and leaf figure. This is the histogram of mtcars. One common scenario in univariate descriptive statistics is to find the mode of a vector. In R, there is no built-in function to help the user obtain the mode of the data. However, one can implement the mode function by using the following code. So this is the code for that. You can see the load function is loaded in the environment. By applying the mode function on the vector mtcars$mpg, you can find the most frequently occurring numeric value or category of a given vector. You can see the output is given as 3 and 5, which are the most occurring numeric value. In this video, we worked with univariate descriptive statistics in R. Stunning! In the next video, we will perform correlations and multivariate analysis. See you there! Welcome to the fourth video of the section, Performing Correlations and Multivariate Analysis. In the previous video, we worked with univariate descriptive statistics. In this video, we will discuss how to conduct multivariate descriptive statistics using a correlation and covariance matrix. To analyze the relationship of more than two variables, you would need to conduct multivariate descriptive statistics, which allows the comparison of factors. Additionally, it prevents the effect of a single variable from distorting the analysis. Ensure that mtcars has already been loaded into a data frame within an R session. So here it is, already loaded. Here, you can get the convariance matrix by inputting the first three variables in mtcars to the cov function. When we execute the code, we can see the covariance matrix. Covariance can measure how variables are linearly related. Thus, a positive covariance, for example, CYL versus MPG, indicates that the two variables are positively linearly related. On the other hand, a negative covariance, for example, MPG versus DISP, indicates the two variables are negatively linearly related. To obtain a correlation matrix of the dataset, we input the first three variables of mtcars to the core function. So when we run this function, we get the matrix. In the correlation coefficient matrix, the numeric element of the matrix indicates the strength of the relationship between the two variables. If the correlation coefficient of a variable against itself scores 1, the variable has a positive relationship against itself. The CYL and MPG variables have a correlation coefficient of minus 0.85, which means that they have a strong negative relationship. On the other hand, the DISP and CYL variables score 0.9, which may indicate that they have a strong positive relationship. You can use ggplot to plot the heat map of the correlation coefficient matrix. For that, we need to load the library reshape2. Then we can use ggplot along with the proper arguments. We get the heat map as shown in the Plot tab. The darker the shade of the color, the higher is the value. In this video, we understood how to perform correlations and multivariate analysis successfully. Awesome! In the next video, we will work on linear regression and multivariate analysis. Hello, this is the fifth video of the section, Operating Linear Regression and Multivariate Analysis. In the previous video, we performed correlation and multivariate analysis. In this video, we will cover how to conduct linear regression for multivariate analysis. Linear regression is a method to assess the association between dependent and independent variables. Ensure that mtcars has already been loaded into a data frame within an R session. You can see that I've loaded mtcars here. To fit variables into a linear model, you can use the LM function. So when we run this line, we get formula and coefficients as output. To get detailed information on the fitted model, you can use the summary function. When we use the summary function, we get the values of the different coefficients and all the details of our model. You can see here that F statistic and P values are generated. It produces an F value, which is the ratio of the model mean square to the error mean square. Thus, a large F value indicates that more of the total variability is accounted for by the regression model. Then, we can use the F value to support or reject the null hypothesis that all of the regression coefficients are equal to 0. In other words, the null hypothesis is rejected if the F value is large and shows that the regression model has a predictive capability. On the other hand, p-values of each attribute test the null hypothesis that the coefficient is equal to 0, no effect on the response variable. In other words, a low p-value can reject a null hypothesis and indicates that a change in the predictor's value is related to the value of the response variable. To create an analysis of a variance table, one can employ the ANOVA function. Here we get the analysis of the variance table when we run the ANOVA function by passing the argument lmfit to it. The function outputs the sum of squares, which stands for the variability of the model's predicted value. To plot the regression line on a scatter plot of two variables, you first plot CYL against MPG in it. Then use the abline function to add a regression line on the plot. So when we do that, we get the graph in the Plot tab. You can see that we have plotted the values of the column or variables MPG versus CYL. From the figure, it is obvious that the MPG and CYL variables are negatively related. Enlightening, isn't it? For more information on how to perform linear and nonlinear regression analysis, you can refer to the forthcoming section on regression analysis. In this video, we understood how to perform linear regression and multivariate analysis. Awesome! In the next video, we will conduct an exact binomial test. Welcome back. This is the sixth video of the section, conducting an exact binomial test. In the previous video, we learnt to perform linear regression and multivariate analysis. In this video, we cover how to conduct a simple exact binomial test in R. Let's start. First, we cover the basics about binomial test. A binomial test uses the binomial distribution to find out whether the true success rate is likely to be p for n trials, with the binary outcome. The formula for the probability p can be defined in the following equation. Here x denotes the random variables, counting the number of outcomes of the interest. N denotes the number of trials. K indicates the number of successes. P indicates the probability of success. And Q denotes the probability of failure. After we have computed the probability P, we can then perform a sign test to determine whether the success probability is similar to what we expected. If the probability is not equal to what we expected, we can reject the null hypothesis. By definition, the null hypothesis is a skeptical perspective or statement about the population parameter that will be tested. The null hypothesis is denoted by H0. An alternative hypothesis is represented by a range of population values which are not included in the null hypothesis. The alternative hypothesis is denoted by H1. Since the binom.test function originates from the stats package, make sure the stats library is loaded. To check that, you can run the method library stats. So, ITR isn't showing me an error, so it's loaded. Assume there is a game where a gambler can win by rolling the number 6 on a dice. As part of the rules, gamblers can bring their own dice. If a gambler tried to cheat in a game, he would use a loaded dice to increase his chances of winning. Therefore, if we observe that the gambler won 92 out of 315 games, we could determine whether the dice was fair by conducting an exact binomial test. So here is the binom.test function. X indicates the number of games won, N is the total number of games, and P is the probability of a 6, i.e. once in 6 times. The result of the t-test shows that the p-value is 3.48e-08, which is lower than 0.05. For significance, at the 5% level, the null hypothesis, i.e. the dice is unbiased, is rejected, as too many 6s were rolled, because the probability of success is 0.2920635. To read more about the usage of the exact binomial test, please use the help function to view related documentation on this. You can do that by putting a question mark before any function you want to learn about, and then run it. You can see the exact binomial test documentation in the Help tab here. Informative. In this video, we learnt to conduct an exact binomial test in R and its significance. In the next video, we will perform the student's t-test. See you there. This is the 7th video of the section, Performing Student's t-test. In the previous video, we learnt everything about binomial test. In this video, we will discuss how to conduct one sample t-test and two sample t-tests using R. Student's t-test is where the test statistic follows a normal distribution, the student's t-distribution. If the null hypothesis is true, it can be used to determine whether there is a difference between two independent datasets. Student's t-test is best used with the problems associated with an inference based on small samples. A one-sample t-test enables us to test whether two means are significantly different. A two-sample t-test allows us to test whether the means of two independent groups are different. Ensure that MT-cars has already been loaded into a data frame within an R session. So, you can see that MT-cars is loaded here. As the t-test function originates from the stats package, make sure the library stats is loaded. So you can check it by executing the library method as shown here. I'm not getting any error, so the library is loaded. First, we visualize the attribute MPG against AM using a box plot. We use the box plot function for that. From the figure, it is clear that the mean of MPG of automobiles, the blue line, is lower than the average MPG, red line, of the overall population. We then perform a statistical procedure to validate whether the average MPG of automobiles is lower than the average of the overall MPG. The low p-value of 0.003595, less than 0.05, suggests that we should reject the null hypothesis that the mean MPG for automobiles is less than the average MPG of the overall population. We begin visualizing the data by plotting a box plot. The preceding figure reveals that the mean MPG of automatic transmission cars is lower than the average MPG of manual transition vehicles. The test results shows that the p-value is equal to 0.1374. P is less than 0.05. In other words, the test provides evidence that rejects the null hypothesis, which shows that the mean NPG of cars with automatic transmission differs from the cars with manual transmission. To read more about the usage of Student's t-test, please use the help function to view related documents. In this video, we have understood and implemented Student's t-test perfectly. Amazing! In the next video, we will perform the Kolmogorov-Smirnov test. This is the 8th video of the section, performing Kolmogorov-Smirnov test. In the previous video, we performed the Student's t-test. In this video, we will demonstrate how to perform the Kolmogorov-Smirnov test with R. The Kolmogorov-Smirnov test, KS test, is a non-parametric and statistical test used for the equality of continuous probability distributions. It can be used to compare a sample with a reference probability distribution, a one-sample KS test, or it can directly compare two samples, a two-sample KS test. The test is based on the empirical distribution function, ECDF. Let x1, x2, xn be a random sample of size, n the empirical distribution function. Fn of x is defined as this. Here, I is the indicator function. If xi is less than x, the function equals to 1. Otherwise, the function equals to 0. The Kolmogorov-Smirnov statistic D is based on the greatest, where sup x denotes the supremum, vertical difference between fx and fnx. It is defined as shown here. H0 is the sample follows the specified distribution. H1 is the sample does not follow the specified distribution. If Dn is greater than the critical value obtained from a table, then we reject H0 at the level of significance alpha. Then, we plot an empirical cumulative distribution function, ECDF plot, to show how a two-sample test calculates the maximum distance d, showing 0.3, and apply the two-sample Kolmogorov-Smirnov test to discover whether the two input datasets possibly come from the same distribution. The p-value is above 0.05, which does not reject the null hypothesis. In other words, it means the two datasets are possibly from the same distribution. A one-sample Kolmogorov-Smirnov test is used to compare a sample with a reference probability. A two-sample Kolmogorov-Smirnov test compares the cumulative distributions of two datasets. Ensure that MT-CARS has already been loaded into a data frame within an R session. As the ks.test function is originated from the stats package, make sure the stats library is loaded. Validate whether the dataset X, generated with the rnorm function, is distributed normally with a one-sample Kolmogorov-Smirnov test. For that, you need to run the ks.test function. And here is the output. The p-value of 0.0994 indicates that the input is normally distributed. Next, you can generate uniformly distributed sample data. So you need to first set seed and then use the runIf function. We first plot ECDF of the two generated data samples to show how two samples calculate the maximum distance d. You can see the graph of ECDF x. Finally, we apply a two-sample Kolmogorov-Smirnov test on two groups of data to check if the two datasets come from the same distribution. So this is the code for doing that. You can see the value here. The p-value is above 0.05, which does not reject the null hypothesis. In other words, it means the two datasets are possibly from the same distribution. To read more about the usage of the Kolmogorov-Smirnov test, please use the help function to view related documents. So you can run the help command, and here is the documentation containing all the information you want. As for the definition of an empirical cumulative distribution function, please refer to the help page of ECDF. Here is the document. In this video, we have performed the Kolmogorov-Smirnov test successfully. Splendid! In the next video, we will understand the Wilcoxon rank sum and signed rank test. This is the 9th video of the section, understanding the Wilcoxon rank sum and signed rank test. In the previous video, we learned all about Kolmogorov-Smirnov test. In this video, we will show you how to conduct the Wilcoxon rank sum and signed rank test in R. The Wilcoxon rank sum and signed rank test, or Mann-Whitney-Wilcoxon, is a non-parametric test of null hypothesis, which shows that the population distribution of two different groups are identical without assuming that the two groups are normally distributed. Let's ensure that MT-CARS has already been loaded into a data frame within an R session. As the Wilcox.test function is originated from the stats package, make sure the library stats is loaded. We first plot the data of MT-CARS with the boxplot function. So we use the boxplot function, and you can see the boxplot in the Plot tab. Next, we still perform a Wilcoxon rank sum test to validate whether the distribution of automatic transmission cars is identical to that of manual transmission cars. You can see the output here. We see that the p-value is 0.001871, less than 0.05, rejects the null hypothesis, and also reveals that the distribution of MPG in automatic and manual transmission cars is not identical. To read more about the usage of Wilcoxon rank sum and signed rank test, please use the help function to view the concerned documents. So here is the document. In this video, we have performed the Wilcoxon rank sum and signed rank test successfully. Awesome! In the next video, we will work with Pearson's chi-squared test. In the previous video, we explored the Wilcoxon rank sum and signed rank test. This is the 10th video of the section, working with Pearson's chi-squared test. In this video, we use a contingency table and mosaic plot to illustrate the differences in count numbers. It is obvious that the number of forward gears is less in automatic transmission cars than in manual transmission cars. In this video, we introduce Pearson's chi-squared test, which is used to examine whether the distributions of categorical variables of two groups differ. We will discuss how to conduct Pearson's chi-squared test in R. Ensure that MT-Cars has already been loaded into a data frame within an R session. Since the chisk.test function is originated from the stats package, make sure the library stats is loaded. Let's perform some steps. To make the counting table, we first use the contingency table built with the inputs of the transmission type and number of forward gears. This is the code we use. We see the contingency table here. We then plot the mosaic plot of the contingency table. This is the code for that. This is how we plot the mosaic plot. So here is the plot. Next, we perform the Pearson's chi-squared test on the contingency table to test whether the number of gears in automatic and manual transmission cars is the same. So we run this code. You will see the output here with a warning message. The output, p-value, equals 2.831e-05, less than 0.05, refutes the null hypothesis and shows the number of forward gears is different in automatic and manual transmission cars. However, the output message contains a warning message that chi-squared approximation may be incorrect, which is because the number of samples in the contingency table is less than 5. Pearson's chi-squared test is a statistical test used to discover whether there is a relationship between two categorical variables. It is best used for unpaired data from large samples. If you would like to conduct Pearson's chi-squared test, you need to make sure that the input samples satisfy two assumptions. Firstly, the two input variables should be categorical. Secondly, the variable should include two or more independent groups. In Pearson's chi-squared test, the assumption is that we have two variables, A and B. We can illustrate the null and alternative hypothesis in the following statements. Number 1. H0, variable A and variable B are independent. Number 2. H1, variable A and variable B are not independent. To test whether the null hypothesis is correct or incorrect, the chi-squared test takes these steps. It calculates the chi-squared test statistic, x squared, using this formula. It determines the degree of freedom, df, of that statistic. The degree of freedom is as shown in this formula. It compares x squared to the critical value from the chi-squared distribution with the degrees of freedom. To read more about the usage of the Pearson's chi-squared test, please use the help function to view the related documents. This is the code for that. Besides some common hypothesis testing methods mentioned in the previous examples, there are other hypothesis methods provided by R. Number 1. The proportional test, prop.test. It is used to test whether the proportions in different groups are the same. Number 2. The z-test, simple.z.test in the using R package. It compares the sample mean with the population mean and standard deviation. Number 3. The Bartlett test, bartlett.test. It is used to test whether the variance of different groups is the same. Number 4. The Kruskal-Wallis rank sum test, kruskal.test. It is used to test whether the distribution of different groups is identical without assuming that they are normally distributed. Number 5. The Shapiro.test. It is used to test for normality. In this video, we worked with Pearson's chi-squared test. In the next video, we will conduct a one-way ANOVA. In the previous video, we saw how to work with Pearson's chi-squared test. This is the 11th video, conducting a one-way ANOVA. In this video, we will discuss how to conduct a one-way ANOVA with R. Analysis of variance, ANOVA, investigates the relationship between categorical independent variables and continuous dependent variables. It can be used to test whether the means of several groups are equal. If there is only one categorical variable as an independent variable, you can perform a one-way ANOVA. On the other hand, if there are more than two categorical variables, you should perform a two-way ANOVA. Ensure that mtcars has already been loaded into a data frame within an R session. Since the one-way.test and two-key HSD functions originated from the stats package, make sure the library stats is loaded. We begin exploring by visualizing the data with a box plot. So we use the box plot function to do that. This is the box plot. This offers a simple indication if cars with a different number of forward gears have different means of MPG. Next, we conduct a one-way ANOVA to examine whether the mean of MPG changes with different numbers of forward gears. We use the function oneway.test. This is the output. Note that the p-value is 0.003085. In addition to oneway.test, a standard function AOV is used for the ANOVA analysis. So this is the code you need to run. We then use the summary function to get the details about the model. Note that the p-value is 0.000295. The model generated by the AOV function can also generate a summary as a fitted table. This is the line code. You can see the table here. Both test results show a small p-value, which rejects the null hypothesis that the mean between cars with a different number of forward gears have the same MPG mean. For the AOV model, one can use two-key HSD for a post hoc comparison test. So this is the output. Further, we can visualize the differences in mean level with a plot function. We can just plot the mtcars post hoc. The result shows that cars with 4 forward gears and cars with 3 gears have the largest difference, as their confidence interval is the furthest to the right within the plot. Now we will learn more about our ANOVA function. ANOVA relies on an F distribution as the basis of all probability distribution. An F score is obtained by dividing the between-group variance by the in-group variance. If the overall F-test was significant, you can conduct a post-hoc test, or multiple comparison tests, to measure the differences between groups. The most commonly used post-hoc tests are Sheff's method, the Tukey-Kramer method, and the Bonferroni correction. In order to interpret the output of ANOVA, you need to have a basic understanding of certain terms, including the degrees of freedom, the sum of square total, the sum of square groups, the sum of square errors, the mean square errors, and the F statistic. If you require more information about these terms, you may refer to using multivariate statistics, or refer to the Wikipedia entry of analysis of variance. Here is the link. You can look up the terms here. In this video, we learnt how to conduct a one-way ANOVA and use it to compare the mean of different geared cars. In the next video, we will conduct a two-way ANOVA. Hi, this is the last video of the section, performing a two-way ANOVA. In the previous video, we conducted a one-way ANOVA. In this video, we will discuss how to conduct a two-way ANOVA in R. A two-way ANOVA can be viewed as the extension of a one-way ANOVA, for the analysis covers more than two categorical variables rather than one. Ensure that mtcars has already been loaded into a data frame within an R session. So here the data frame is available. Since the two-way.test, two-key HSD, and interaction.plot functions are originated from the stats package, make sure the library stats is loaded. First, we plot the two box plots of factor gears in regard to MPG, with the plot separated from the transmission type. We use the box plot function and we get the two box plots. Also, you may produce a box plot of MPG by the number of forward gears into transmission type, with the use of the asterisk operation in the box plot function. Here is the box plot. Next, we use an interaction plot to characterize the relationship between variables. So the function is interaction.plot, and we pass the empty cars different columns as arguments. The resulting plot shows that the number of gears does have an effect on the mean of the MPG, but does not show a positive relationship either. We then perform a two-way ANOVA on MPG, with a combination of the gear and transmission type factors. So here's the code for that. We use the summary function to get details. Here is the output. The output shows that the p-value of the gear factor rejects the null hypothesis, while the factor transmission type does not reject the null hypothesis. In other words, cars with different numbers of gears are more likely to have different means of MPG. Similar to a one-way ANOVA, we can perform a post hoc comparison test to see the results of the two-way ANOVA model. Here are the values. We then visualize the differences in mean levels with the plot function. So this is the code you need to run. And you can see the output in the plot tab. The plot and values reveals that the cars with 4 gears and 3 gears respectively have the largest difference in terms of the mean MPG. Amazing! For multivariate analysis of variances, the function MANOVA can be used to examine the effect of multiple independent variables on multiple dependent variables. Further information about MANOVA is included within the help function in R, so here's the document in the help tab. So in this video, we performed a two-way ANOVA. Let's have a quick recap of the entire section. We started with examples of data sampling, probability distribution, and univariate descriptive statistics. We also understood correlations and multivariate analysis, and linear regression and multivariate analysis. We then performed a number of tests on our data, such as exact binomial test, student's t-test, Kolmogorov-Smirnov test, Wilcoxon rank sum and signed rank test, and Pearson's chi-squared test. Additionally, we also conducted one-way and two-way ANOVA. In the next section, we will understand regression analysis. See you there! Welcome to a new section of the course, Understanding Regression Analysis. In this section, we will introduce how to fit a linear model into data with the LM function. Next, for distribution in other than the normal Gaussian model, for example Poisson or binomial, we use the GLM function with an appropriate link function correspondent to the data distribution. Finally, we cover how to fit a generalized additive model into data using the GAM function. Now we move on to the first video of this section that deals with fitting a linear regression model with LM. In this video, we will first perform fitting of a model using LM. We will also use the LSFit function to perform simple linear regression. Regression is a supervised learning method which is employed to model and analyze the relationship between a dependent response variable and one or more independent predictor variables. One can use regression to build a prediction model, which can first be used to find the best fitted model with minimum squared errors of the fitted values. The fitted model can then be further applied to data for continuous value predictions. There are many types of regression. If there is only one predictor available and the relationship between the response variable and the independent variable is linear, we can apply a linear model. However, if there was more than one predictor variable, a multiple linear regression method should be used. When the relationship is nonlinear, one can use a nonlinear model to model the relationship between the predictor and the response variables. Now let's look at regression from an amathematical point of view. The regression model has the response terms form, where response is the response vector, and terms is a series of terms that specifies a predictor. We can illustrate a simple regression model in the formula y equal to alpha plus beta x, where alpha is the intercept, while the slope beta describes the change in y when x changes. By using the least squares method, we can calculate beta as, where y bar indicates the mean value of y and x bar denotes the mean value of x. The simple model in regression is linear regression, which is best used when there is only one predictor variable and the relationship between the response variable and the independent variable is linear. In R, we can fit a linear model to data with the LM function. We need to prepare data with one predictor and one response variable, and with a linear relationship between two variables. So first, we need to install the car package. So the car package is installed here. We then load its library. So the library is loaded. From the package, you can load the Quartet dataset. You can do that using data function. Then, you can use the str function to display the structure of the Quartet dataset. You can see the output here. Next, we draw a scatter plot of the x and y variables with plot and append a fitted line through the lm and abline function. You can see the simple regression plot. The regression line illustrates the linear relationship of x and y1 variables. To view the fit model, execute the following lmfr command. You can see the output here. We can see that the coefficient of the fitted model shows that the intercept equals 3.0001 and coefficient equals 0.5001. As a result, we can use the intercept and coefficient to infer the response value. For example, we can infer the response value when x at 3 is equal to 4.5103. This is calculated as 3 multiplied by 0.5001 plus 3.0001. Besides the LM function, you can also use the LSFit function to perform a simple linear regression. So as you can see, we get the same output plot using LSFi. Awesome! In this video, we fitted a linear model using LM successfully. In the next video, we will summarize linear model fits. Hi, this is the second video of the section, summarizing linear model fits. In the previous video, we learned how to fit a linear regression model using LM. In this video, we will obtain overall information on a model through the use of the summary function. We will analyze the model on the basis of the details provided by the summary function and also look at alternative functions to obtain information. The summary function can be used to obtain the formatted coefficient, standard errors, degree of freedom, and other summarized information of a fitted model. You need to have computed the linear model of the x and y1 variables from the quartet, and have the fitted model assigned to the LMFit variable. First, we compute a detailed summary of the fitted model, using the summary LMFit command. You can see the output here. The summary function is a generic function used to produce summary statistics. In this case, it computes and returns a list of summary statistics of the fitted linear model. Here, it outputs information such as residuals, coefficient standard error r squared, F statistic, and a degree of freedom. In the call section, the function called to generate the fitted model is displayed. In the residuals section, it provides a quick summary, min, 1q, median, 3q, max, of the distribution. In the coefficients section, each coefficient is a Gaussian random variable. Within this section, estimate represents the mean distribution of the variable. Standard error displays the standard error of the variable. The t-value is estimate divided by std.error, and the p-value indicates the probability of getting a value larger than the t-value. In this sample, the p-value of both intercepts, that is 0.002573, and x, that is 0.00217, have a 95% level of confidence. Residual standard error outputs the standard deviation of residuals, while the degree of freedom indicates the differences between the observation in training samples and the number used in the model. Multiple R² is obtained by dividing the sum of squares. One can use R² to measure how close the data is to fit into the regression line. Mostly, the higher the R², the better the model fits your data. However, it does not necessarily indicate whether the regression model is adequate. This means that you might get a good model with a low R², or you can have a bad model with a high R². Since multiple R² ignore a degree of freedom, the calculated score is biased. To make the calculation fair, an adjusted R², 0.6295, uses an unbiased estimate and will be slightly less than multiple R², 0.6665. F statistic is retrieved by performing an F-test on the model. A p-value equal to 0.00217, less than 0.05, rejects the null hypothesis, which was no linear correlation between variables, and indicates that the observed F is greater than the critical F value. In other words, the result shows that there is a significant positive linear correlation between the variables. For more information on the parameters used for obtaining a summary of the fitted model, you can use the help function, or question mark, to view the help page. When you run this command, you can see the information about summarizing linear model fits in the Help tab. Alternatively, you can use the following functions to display the properties of the model. So first is the coefficients function, which extracts model coefficients. Second is the confit function, which computes confidence levels for model parameters. Third is the fitted lmfit, which extracts the model fitted values. Next is residuals, that extracts model residuals. Then we perform ANOVA. You can see the analysis of the variance table for fitted model object. Next is VCOV, with calculated variance-covariance matrix for a fitted model. You can see the output here. Lastly, we implement the influence function, which diagnoses quality of regression fits. Amazing! In this video, we obtained information of our linear model fits using summary function successfully. In the next video, we will predict unknown values using linear regression. Hello, and welcome to the third video of the section, using linear regression to predict unknown values. In the previous video, we summarized linear model fits. In this video, we will introduce how to predict unknown values under the measurements prediction, intervals, and confidence interval. With a fitted regression model, we can apply the model to predict unknown values. For regression models, we can express the precision of prediction with a prediction interval and confidence interval. You need to have computed the linear model of the x and y1 variables from the Quartet dataset. You can see the Quartet dataset is already loaded here. First, we fit a linear model with the x and y1 variables, so we use the lmfit function for that. After doing that, we assign values to be predicted into a data frame, new data. You can see new data feeded here. Now let's compute the prediction result using the confidence interval with the level set as 0.95. You can see the output here. From the output of row 1, we get fitted y1 of the x equals 3 input, which equals to 4.500364, and a 95% confidence interval, set 0.95 in the level argument of the y1 mean for x equals 3 is between 2.691375 and 6.309352. In addition to this, row 2 and 3 give the prediction result of y1 with an input of x equals 6 and x equals 15. Next, we compute the prediction result using this prediction interval. From the output of row 1, we can see fitted y of the x equals 3 input equals to 4.500364, and a 95% prediction interval of y1 for x equals 3 is between 1.169022 and 7.831705. Row 2 and 3 output the prediction result of y1 with an input of x equals 6 and x equals 15. For those who are interested in the differences between prediction intervals and confidence intervals, you can refer to the Wikipedia entry Contrast with Confidence Intervals at this link. In this video, we predicted unknown values with the help of linear regression. Incredible! In the next video, we will generate a diagnostic plot of a fitted model. This is the fourth video of the section, Generating a Diagnostic Plot of a Fitted Model. In the previous video, we used linear regression to predict unknown values. In this video, we will introduce how to diagnose a regression model through the use of a diagnostic plot. We will understand the data in the plot and also find outliers based on Cook's distance. Diagnostics are methods to evaluate assumptions of the regression, which can be used to determine whether a fitted model adequately represents the data. You need to have computed a linear model of the x and y variables from the quartet, and have the model assigned to the LM-fit variable. We start by plotting the diagnostic plot of the regression model using the par function. I will enlarge the Plot tab here so you can see it clearly. The plot function generates 4 diagnostic plots of a regression model. The upper left plot shows residuals versus fitted values. Within the plot, residuals represent the vertical distance from a point to the regression line. If all points fall exactly on the regression line, all residuals will fall exactly on the dotted grey line. The red line within the plot is a smooth curve with regard to residuals, and if all the dots fall exactly on the regression line, the position of the red line should exactly match the dotted grey line. The upper right shows the normal of residuals. This plot verifies the assumption that residuals are normally distributed. Thus, if the residuals were normally distributed, they should lie exactly on the grey dash line. The scale location plot on the bottom left is used to measure the square root of the standardized residuals against the fitted value. Therefore, if all dots lie on the regression line, the value of y should be close to 0. Since it is assumed that the variancy of residuals does not change the distribution substantially, if the assumption is correct, the red line should be relatively flat. The bottom right plot shows standardized residuals versus leverage. The leverage is a measurement of how each data point influences the regression. It is a measurement of the distance from the centroid of regression and level of isolation, measured by whether it has neighbors. Also, you can find the contour of Cook's distance, which is affected by high leverage and large residuals. You can use this to measure how regression would change if a single point is deleted. The red line is smooth with regard to standardized residuals. For a perfect fit regression, the red line should be close to the dashed line, with no points over 0.5 in Cook's distance. Stunning! To see more of the diagnostic plot function, you can use the help function to access further information. So let's go back to the editor. Here you can see all data about the plot.lm function. In order to discover whether there are points with large Cook's distance, one can use Cook's.distance function to compute the Cook's distance of each point and analyze the distribution of distance through visualization. You can see the output here. In this case, where the point on index 3 shows greater Cook's distance than other points, one can investigate whether this point might be an outlier. You can see this point is an outlier. Great. In this video, we have generated a diagnostic plot of a fitted model. In the next video, we will fit a polynomial regression model with LM. Hi, this is the 5th video of the section, Fitting a Polynomial Regression Model with LM. In the previous video, we generated a diagnostic plot of a fitted model. In this video, we introduce how to deal with n-order polynomial regression using the LM and poly functions. Some predictor variables and response variables may have a nonlinear relationship, and their relationship can be modeled as an nth-order polynomial. We can illustrate the second-order polynomial regression model in formula y equal to alpha plus beta x plus cx squared, where alpha is the intercept, while beta illustrates regression coefficients. You have to first prepare the dataset that includes a relationship between the predictor and response variable that can be modeled as an nth-order polynomial. We will continue to use the Quartet dataset from the CAR package. Then we make a scatter plot of the x and y2 variables. Here is our scatter plot. In this, you can see the scatter plot of the x and y2 variables does not fit in a linear relationship, but shows a concave downward curve, or convex upward, with the turning point at x equals 11. In order to model the nonlinear relationship, we apply the poly function with an argument of 2 to fit the independent x variable and the dependent y2 variable. So when we run this, we get the red line. The red line in the plot shows that the model perfectly fits the data. You can also fit a second-order polynomial model with an independent variable equal to the formula of the combined first-order x variable and the second-order x variable. So this is the line of code you need to run for that. You can see the plot here. In this video, we worked with polynomial regression models successfully. Awesome! In the next video, we will fit a robust linear regression model using RLM. Hi, welcome to the 6th video of the section, Fitting a Robust Linear Regression Model with RLM. In the previous video, we learnt how to fit a polynomial regression model with LM. In this video, we introduce how to apply RLM to perform robust linear regression to datasets. In this video, we're going to start with understanding outliers. We will then remove the outlier using RLM and see the effect an outlier has on the regression line. An outlier in the dataset will move the regression line away from the mainstream. Apart from removing it, we can apply a robust linear regression to fit datasets containing outliers. You have to first prepare the dataset that contains an outlier that may move the regression line away from the mainstream. Here we use the Quartet dataset that is already loaded. Generate a scatter plot of the x variable against y3 using the plot function. Here is the plot. As you can see here, the dataset here includes outliers away from the mainstream. To remove the effect of an outlier, we demonstrate how to apply a robust linear regression, RLM, to fit the data. For that, you should import the mass library first. Then you can apply the RLM function to fit the model, and visualize the fitted line with the abline function. You can see that the robust regression line ignores the outlier and matches the mainstream. Cool, right? Now, don't you want to see what happens when there is an outlier? To see the effect of how an outlier can move the regression line away from the mainstream, you may replace the RLM function used here to LM and replot the graph. It is obvious that the outlier, x equals 13, moves the regression line away from the mainstream. In this video, we have fitted a robust linear regression model using RLM. In the next video, we will study a case linear regression on SLID data. Hello, and welcome to the 7th video of the section, studying a case of linear regression on SLID data. In the previous video, we fitted a robust linear model with RLM. In this video, we demonstrate how to apply linear regression to analyze the Survey of Labor and Income Dynamics SLID dataset. We will analyze data and refit the plots to get the optimal output and best results. To summarize the contents of the previous section, we explore more complex data with linear regression. Check whether the CAR library is installed and loaded, as it is required to access the dataset SLID. So here it is, already loaded. So you can use the str function to get an overview of the data, so we get this output. From the structure of the data, we know that there are 4 independent variables that will affect the wages of the dependent variable. Next, we explore the relationship of each independent variable to the dependent variable, wages, through visualization. We visualize the variable wages against language, age, education, and sex. So we have to give respective plotting functions for that. You can see 4 plots here. In the upper left section of this screenshot, you can find the box plot and 3 different languages against wages. The correlation between the languages and wages is not obvious. The upper right section of the screenshot shows that the age appears to have a positive relationship with the dependent variable wages. In the bottom left of the screenshot, it is shown that education also appears to have a positive relationship with wages. Finally, the box plot in the bottom right section of the screenshot shows that the wages of males are slightly higher than females. Then, we can use LM to fit the model. We fit all the attributes except for wages to the model as predictor variables. You can examine the summary of the fitted model through the summary function. By summarizing the model, it is shown that education, age, and sex show a significance, p-value less than 0.05. As a result, we drop the insignificant language attribute, which has a p-value greater than 0.05, and fit the 3 independent variables, education, sex, and age, with regard to the dependent variable, wages, in the linear model. Note that the f-statistic value is 336.8. Then we refit the model with the LM function. This accordingly raises the f-statistic from 336.8 to 565.3. We can then draw a diagnostic plot of LM fit. Within the diagnostic plot, all the 4 plots indicate that the regression model follows the regression assumption. However, from residuals versus fitted and scale location plot, residuals of smaller fitted values are biased towards the regression model. Since wages range over several orders of magnitude, to induce the symmetry, we take the log of wages and replot the diagnostic plot. The red line of residuals versus fitted values plot and the scale location plot are now closer to the grey dashed line. Next, you can diagnose the multicollinearity of the regression model using VIF function. When I run this line, I get the corresponding output. What exactly is multicollinearity? Multicollinearity takes place when a predictor is highly correlated with others. If multicollinearity exists in the model, you might see some variables have a high R-squared value, but are shown as variables insignificant. To detect multicollinearity, we can calculate the variance inflation and generalized variance inflation factors for linear and generalized linear models with the VIF function. If multicollinearity exists, we should find predictors with the square root of variance inflation factor above 2. Then, we can remove redundant predictors or use a principal component analysis to transform predictors to a smaller set of uncorrelated components. Then, you can install and load the LM test package and diagnose the heteroskedasticity of the regression model with the BP test function. So let's do that. It's being installed. Then we load the package. You can see the results of the test here. Heteroskedasticity means that the variance is unequal across observations. To detect and test heteroskedasticity, we can perform the Breusch-Pagan test for heteroskedasticity with the BP test function within the LM-test package. In this case, the p-value shows 2.206 raised to 6, less than 0.5, which rejects the null hypothesis of homoskedasticity, or no heteroskedasticity. Here, it implies that the standard errors of the parameter estimates are incorrect. Finally, you can install and load the RMS package. We use the OLS-fit, ordinary least square fit function. Here we have used robust standard errors to correct the standard error and increase the significance of the truly significant parameters with Robkov from the RMS package. However, since it only takes the fitted model from the RMS series as an input, we have to fit the ordinary least squares model beforehand. For more information about the SLID dataset, you can use the help function to view the related documentation. So here is the document in the Help tab. In this video, we have studied a case of linear regression on SLID data adeptly. Wonderful! In the next video, we will learn how to apply the Gaussian model for generalized linear regression. This is the 8th video of the section, Applying the Gaussian model for generalized linear regression. In the previous video, we have studied linear regression by applying it in SLID data. In this recipe, we first demonstrate how to fit the model into the data using the GLM function, and then show that GLM with a Gaussian model performs exactly the same as LM. Generalized linear model, GLM, is a generalization of linear regression, which can include a link function to make a linear prediction. As a default setting, the family object for GLM is Gaussian, which makes the GLM function perform exactly the same as LM. Check whether the CAR library is installed and loaded, as we require the SLID dataset from this package. So you can run the library function to check that. Fit the independent variables age, sex, and education and dependent variable wages to GLM. So this is the output here. Next, we will fit the independent variables age, sex, and education and the dependent variable wages to LM. By applying the summary function to the two different models, it reveals that the residuals and coefficients of the two output summaries are exactly the same. Use ANOVA to compare the two fitted models. The result of the ANOVA function shows that the two models are similar, with the same residual degrees of freedom, res.df, and a residual sum of squares, RSSDF. For a comparison of generalized linear models with linear models, you can refer to Venables, WN, and Ripley, BD, 2002, Modern Applied Statistics with S. Springer. In this video, we have applied Gaussian model for generalized linear regression. In the next video, we will apply the Poisson model for generalized linear regression. Hi, this is the 9th video of the section, Applying the Poisson model for generalized linear regression. In the previous video, we applied the Gaussian model for generalized linear regression. In this video, we demonstrate how to apply Poisson as a family object within GLM with regard to count data. Generalized linear models allow response variables that have error distribution models other than a normal distribution, Gaussian. The prerequisite of this task is to prepare the count data, with all the input data values as integers. First, we load the warp breaks data and use head to view the first few lines. When we do that, we see the output here. It contains data regarding the number of warp breaks per loom. Then we apply Poisson as a family object for the independent variable, tension, and the dependent variable, breaks. Finally, we viewed the fitted log linear model with the summary function. To understand more on how a Poisson model is related to count data, you can refer to Cameron, AC, and Trivedi, PK, Regression Analysis of Count Data, Cambridge University Press. In this video, we have learnt how to apply Poisson model for generalized linear regression. In the next video, we will apply the binomial model. Hello, this is the 10th video of the section, applying the binomial model for generalized linear regression. In the previous video, we applied the Poisson model for generalized linear regression. In this video, we will understand how to apply the binomial model with the GLM function. For a binary-dependent variable, one may apply a binomial model as the family object in the GLM function. The prerequisite of this task is to prepare a binary-dependent variable. Here we use the VS variable, VEngine or straightEngine, as the dependent variable. First, we examine the first 6 elements of VS within mtcars using the head function. Within the binary data, each observation of the response value is coded as either 0 or 1. The VS is suitable for the binomial model, as it contains binary data. We apply the GLM function with binomial as the family object. We use summary to view the information about the fitted model. So here is the description. Awesome. If you specify the family object in parameters only, you will use the default link to fit the model. However, to use an alternative link function, you can add a link argument. For example, look at this line of code. Here we have specified the link as probit, and run it. If you would like to know how many alternative links you can use, please refer to the family document via the help function. You can see the document in the Help tab. Family object for models. In this video, we have applied the binomial model for generalized linear regression perfectly. Awesome. In the next video, we will fit a generalized additive model to data. Hi, this is the 11th video of the section, fitting a generalized additive model to data. In the previous video, we learned how to apply the binomial model for generalized linear regression. In this video, we introduce how to fit regression using a generalized additive model. Generalized additive model, GAM, which is used to fit generalized additive models, can be used as a semi-parametric extension of GLM. While GLM holds the assumption that there is a linear relationship between dependent and independent variables, GAM fits the model on account of the local behavior of data. As a result, GAM has the ability to deal with highly nonlinear relationships between dependent and independent variables. GAM is designed to maximize the prediction of a dependent variable, y, from various distributions by estimating the non-parametric functions of the predictors that link to the dependent variable through a link function. The notion of GAM is where an exponential family E is specified for y, along with the glink function. F denotes the link function of predictors. We need to prepare a data frame containing variables where one of the variables is a response variable and the others may be predictor variables. First, we need to install and load the mgcv package, which contains the GAM function. So here it is installed and loaded in the R session. Then install the mass package and load the Boston dataset. So here it is being installed and loaded. Then we attach the Boston dataset. Next, we fit the regression using GAM. From the dataset we use DIS, the weighted mean of the distance to 5 Boston employment centers, as the dependent variable, and NOx, nitrogen oxide concentration, as the independent variable, and then input them into the GAM function to generate a fitted model. Then we get the summary information of the fitted model. From the summary, you can find the parametric parameter, significance of smooth terms, and other useful information. Amazing! Apart from GAM, MGCV package provides another generalized additive model, BAM, for large datasets. The BAM package is very similar to GAM, but uses less memory and is relatively more efficient. Use the Help function for more information on this model. Here you can see the document in the Help tab. For more information about generalized additive models in R, please refer to Wood S. 2006, Generalized Additive Models, An Introduction with R, from CRC Press. In this video, we have fitted the generalized additive model to data successfully. Great! In the next video, we will visualize the generalized additive model. Hello, this is the 11th video of the section, Visualizing a Generalized Additive Model. In the previous video, we learnt how to fit a generalized additive model to data. In this video, we demonstrate how to add a GAM-fitted regression line to a scatter plot. In addition, we visualize the GAM fit using the plot function. You need to have already assigned a GAM-fitted model to the fit variable. Generate a scatter plot using the NOX and DIS variables. So we do that and get our scatter plot. Now let's add the regression to the scatter plot. You can see the changes in the plot. There is a red line connecting the points. Alternatively, you can plot the fitted model using the plot function. You can see the plot here. The viz.gam function is used to produce perspective or contour plot views of the GAM model predictions. It is helpful to observe how response variables interact with the two predictor variables. The following is an example of a contour plot on the Boston dataset. So we implement this, a simple contour plot is produced. Amazing! In this video, we visualized the generalized additive model successfully. In the next video, we will diagnose a generalized additive model. Welcome to the last video of the section, Diagnosing a Generalized Additive Model. In the previous video, we visualized a generalized additive model. In this recipe, we demonstrate how to plot diagnostic plots through the gam.check function. GAM also provides diagnostic information about the fitting procedure and results of the generalized additive model. Ensure that the GAM-fitted model is assigned to the fit variable. Generate the diagnostic plot using gam.check on the fitted model. The function is gam.check. You can see the output here. You can also see the plot here. The gam.check function first produces the smoothing parameter estimation convergence information. Here, the smoothing parameter GCV UBRE, Generalized Cross-Validation Unbiased Risk Estimator, score converges after 7 iterations. The mean absolute gradient of the GCV UBRE function at the minimum is 8.79622, raised to 6, and the estimated rank is 10. The dimension check is to test whether the basis dimension for a smooth function is adequate. The low p-value indicates that the k is set too low. One may adjust the dimension choice for smooth by specifying the argument k by fitting GAM to the data. In addition to providing information regarding smoothing parameter estimation convergence, the function returns 4 diagnostic plots. The upper left section of the plot in the screenshot shows a quantile comparison plot. This plot is useful to identify outliers and heavy tails. The upper right section of the plot shows residuals versus linear predictors, which are useful in finding non-constant error variances. The bottom left section of the plot shows a histogram of the residuals, which is helpful in detecting non-normality. The bottom right section shows response versus the fitted value. You can access the help function for more information on gam.check. In particular, this includes a detailed illustration of smoothing parameter estimation convergence and 4 returned plots. In addition, more information for choose.k can be accessed by the following command. So here is the documentation in the Help tab. In this video, we diagnosed the generalized additive model. Amazing! Let's summarize the entire section. We started with how to fit a linear model into data with the LM function. We then performed diagnosis, summarizing, and prediction using the linear regression model. We fit a polynomial and robust linear regression model too. Also, we studied a case of linear regression on SLID data. Next, for distribution in other than the normal Gaussian model, for example Poisson or binomial, we used the GLM function with an appropriate link function correspondent to the data distribution. Finally, we fit a generalized additive model into data using the GAM function and performed the operations performed with LM function. In the next section, we will learn about classification models such as tree, lazy, and probabilistic. See you there! Hi, and welcome to Section 5, Classification, Tree, Lazy, and Probabilistic. In this section, we will illustrate how to use R to perform classification. We first build a training dataset and a testing dataset from the churn dataset, and then apply different classification methods to classify the churn dataset. In the upcoming videos, we will introduce the tree-based classification method using a traditional classification tree and a conditional inference tree, lazy-based algorithm, and a probabilistic-based method using the training dataset to build up a classification model and then use the model to predict the category, class label of the testing dataset. We will also use a confusion matrix to measure the performance. Now we move on to the first video of this section that deals with preparing the training and testing datasets. In this video, we will demonstrate how to split the telecom churn dataset into training and testing datasets, respectively. Before building the classification model, we need to pre-process the data first. Thus, we load the churn data from the C50 package into the R session with the variable name as churn. As we determine that attributes such as state, area code, and account length are not useful features for building the classification model, we remove these attributes. We use the telecom churn dataset as our example data source. The dataset contains 20 variables with 3,333 observations. We would like to build a classification model to predict whether a customer will churn, which is very important to the telecom company as the cost of acquiring a new customer is significantly more than retaining one. Let's perform some steps to split the churn dataset into training and testing datasets. You can retrieve the churn dataset from the C50 package. So first, install C50 package, then load it. After that, load the churn dataset. You can see that the churn test and churn train have been loaded in the R session. Then use str to read the structure of the dataset. You can see the output here. We can remove the state, area code, and account length attributes, which are not appropriate for the classification features. Then split 70% of the data into the training dataset and 30% of the data into the testing dataset. You can see that it's done here. Lastly, use dim to explore the dimensions of both the training and testing datasets. Here we find that 2,315 out of the 3,333 observations are categorized into the training dataset, train set, while the other 1,018 are categorized into the testing dataset, test set. Also, you can combine the split process of the training and testing datasets into the split.data function. Therefore, you can easily split the data into two datasets by calling the function and specifying the proportion and seed in the parameters. This is the code you need to use. Cool! In this video, we have learned preparing the training and testing datasets. Awesome! In the next video, we'll take a look at building a classification model with recursive partitioning trees. Video 2. Building a classification model with recursive partitioning trees. In the previous video, we looked at preparing the training and testing datasets. In this video, we will introduce how to apply a recursive partitioning tree on the customer churn dataset. A classification tree uses a split condition to predict class labels based on one or multiple input variables. The classification process starts from the root node of the tree. At each node, the process will check whether the input value should be recursively continued to the right or left subbranch according to the split condition, and stops when meeting any leaf terminal nodes of the decision tree. The recursive partitioning tree includes two processes, recursion and partitioning. During the process of decision induction, we have to consider a statistic evaluation question, or simply a yes-no question, to partition the data in different partitions in accordance with the assessment result. Then, as we have determined the child node, we can repeatedly perform the splitting until stop criteria is satisfied. For example, the data, shown in this figure, in the root node can be partitioned into two groups with regard to the question of whether f1 is smaller than x. If so, the data is divided into the left-hand side. Otherwise, it is split into the right-hand side. Then, we can continue to partition the left-hand side data with the question of whether f2 is smaller than y. Before starting, you need to have completed the previous video by splitting the churn dataset into the training dataset, train set, and testing dataset, test set. And each dataset should contain exactly 17 variables. Let's start with splitting the churn dataset into training and testing datasets. Load the rpart package first. Here, we use a recursive partitioning tree from the rpart package to build a tree-based classification model. So, use the rpart function to build a classification tree model. We use the churn variable as a classification category. Type churn.rp to retrieve the node detail on the classification tree. In the printed node detail, n indicates the sample size, loss indicates the misclassification cost, yval stands for the classified membership, no or yes in this case, and yprob stands for the probabilities of two classes. The left value refers to the probability reaching label no, and the right value refers to the probability reaching label yes. Next, use the printCp function to examine the complexity parameter. Here's the output. One should find the value of Cp, a complexity parameter, which serves as a penalty to control the size of the tree. In short, the greater the Cp value, the fewer the number of splits, n-split. The output value, the rel error, represents the average deviance of the current tree divided by the average deviance of the null tree. A x error value represents relative error estimated by a tenfold classification. XSTD stands for the standard error of the relative error. To make the Cp, cost complexity parameter, table more readable, we use plotCp to generate an information graphic of the Cp table. You can see the output in Plot tab. The x-axis at the bottom illustrates the Cp value, the y-axis illustrates the relative error, and the upper y-axis displays the size of the tree. The dotted line indicates the upper limit of a standard deviation. From the screenshot, we can determine that minimum cross-validation error occurs when the tree is at size 12. Lastly, use the summary function to examine the built-in model. You can see the statistics here. Quite lengthy, I must say. With the summary function to display the function call, complexity parameter table for the fitted tree model, variable importance, which helps identify the most important variable for the tree classification, summing up to 100, and detailed information of each node. The advantage of using the decision tree is that it is very flexible and easy to interpret. It works on both classification and regression problems, and more, it is non-parametric. Therefore, one does not have to worry about whether the data is linear separable. As for the disadvantage of using the decision tree, it is that it tends to be biased and overfitted. However, you can conquer the bias problems through the use of a conditional inference tree, and solve the problem of overfitting through a random forest method or tree pruning. For more information about the rpart printcp and summary functions, please use the help function. You can run this line of code for help. It will give you the documentation for rpart. In the same way, you can get information for printcp and summary.rpart. C50 is another package that provides a decision tree and a rule-based model. If you are interested in the package, you may refer to the document at cran.rproject.org. Great! In this video, we have looked at building a classification model with recursive partitioning trees. Amazing! In the next video, we'll learn visualizing a recursive partitioning tree. This is video 3, visualizing a recursive partitioning tree. In the previous video, we learned how to build a classification model with recursive partitioning trees. In this video, we demonstrate how to use the plot function to graphically display a classification tree. From the previous video, we learned how to print the classification tree in a text format. To make the tree more readable, we can use the plot function to obtain the graphical display of a built classification tree. One needs to have the previous video completed by generating a classification model and assign the model into the churn.rp variable. Let's perform some steps to visualize the classification tree. Use the plot function and the text function to plot the classification tree. For that, we need to run these lines of code. You can see the plot here. Here, we assign margin equals 0.1 as a parameter to add extra white space around the border to prevent the displayed text being truncated by the margin. It shows that the length of the branches displays the relative magnitude of the drop in deviance. We then use the text function to add labels for the nodes and branches. By default, the text function will add a split condition on each split and add a category label in each terminal node. In order to add extra information on the tree plot, we set the parameter as all equal to true to add a label to all the nodes. In addition to this, we add a parameter by specifying use.n equals true to add extra information, which shows that the actual number of observations fall into two different categories, no and yes. You can also specify the uniform, branch, and margin parameter to adjust the layout. For that, we need these lines of code. You can see another plot here. Here we set the option branch to 0.6 to add a shoulder to each plotted branch. In addition to this, in order to display branches of an equal length, rather than relative magnitude of the drop in deviance, we set the option uniform to true. As a result, this plot shows a classification tree with short shoulders and branches of equal length. You may use plot.rpart to read more about the plotting of the classification tree. This document also includes information on how to specify the parameters uniform, branch, compress, nspace, margin, and min branch to adjust the layout of the classification tree. In this video, we have learned visualizing a recursive partitioning tree. In the next video, we'll take a look at measuring the prediction performance of a recursive partitioning tree. The fourth video of this section, measuring the prediction performance of a recursive partitioning tree. In the previous video, we looked at visualizing a recursive partitioning tree. In this video, we will introduce how to generate a predicted label versus a real label table with the predict function and the table function, and explain how to generate a confusion matrix to measure the performance. Since we have built a classification tree in the previous videos, we can use it to predict the category, i.e. class label, of new observations. Before making a prediction, we first validate the prediction power of the classification tree, which can be done by generating a classification table on the testing dataset. You need to have the previous video completed by generating the classification model churn.rp. In addition to this, you have to prepare the training dataset, trainset, and the testing dataset, testset, generated in the first video of this section. Let's first validate the prediction performance of a classification tree. Here we use the predict function to generate a predicted label of testing the dataset. Next, use the table function to generate a classification table for the testing dataset. You can see the output for this code here. We further generate a confusion matrix using the confusion matrix function provided in the caret package. So here you can see that the caret package is being loaded and the confusion matrix is displayed. From this table, you can discover that there are 859 correctly predicted as no, while 18 are misclassified as yes. 100 of the yes predictions are correctly predicted, but 41 observations are misclassified into no. Here, we use the confusion matrix function from the caret package to produce a measurement of the classification model. You may use $confusion matrix to read more about the performance measurement using the confusion matrix. If you are interested in the definition output by the confusion matrix, you can refer to the Wikipedia entry http://en.wikipedia.org/wiki/confusion_matrix. And you can even refer to the documentation under the Help tab. Great! In this video, we have looked at measuring the prediction performance of a recursive partitioning tree. In the next video, we'll learn pruning a recursive partitioning tree. Video 5. Pruning a recursive partitioning tree. In the previous video, we looked at measuring the prediction performance of a recursive partitioning tree. In this video, we're going to introduce the cost complexity pruning method to prune the classification tree. In the previous videos, we have built a complex decision tree for the churn dataset. However, sometimes we have to remove sections that are not powerful in classifying instances to avoid overfitting and to improve the prediction accuracy. You need to have the previous video completed by generating a classification model and assign the model into the churn.rp variable. Let's now prune the classification tree. So we first find the minimum cross-validation error of the classification tree model. Next, locate the record with the minimum cross-validation errors. Then, get the cost complexity parameter of the record with the minimum cross-validation errors. Now, prune the tree by setting the CP parameter to the CP value of the record with minimum cross-validation errors. After this, we visualize the classification tree by using the plot and text function. You can see the plot here. Let me maximize it. It is clear that the split of the tree is less than the original classification tree. Next, we generate a classification table based on the pruned classification tree model. So you can see the prediction output here. Lastly, we generate a confusion matrix based on the classification table. The result shows that the accuracy 0.9411 is slightly lower than the original model, i.e. 0.942, and also suggests that the pruned tree may not perform better than the original classification tree, as we have pruned some split conditions. However, the pruned tree model is more robust as it removes some split conditions that may lead to overfitting. If you would like to know more about cost complexity pruning, refer to the Wikipedia article for pruning at wikipedia.org/wiki/pruning. Superb! In this video, we have learned pruning a recursive partitioning tree. In the next video, we'll take a look at building a classification model with the conditional inference tree. Video 6. Building a classification model with a conditional inference tree. In the previous video, we looked at pruning a recursive partitioning tree. In this video, we will introduce how to adapt a conditional inference tree to build a classification model. In addition to traditional decision trees, that is rpart, conditional inference trees are another popular tree-based classification method. Similar to traditional decision trees, conditional inference trees also recursively partition the data by performing a univariate split on the dependent variable. However, what makes conditional inference trees different from traditional decision trees is that conditional inference trees adapt the significance test procedures to select variables, rather than selecting variables by maximizing information measures. RPART employs a Gini coefficient. You need to have the first video completed by generating the training dataset, train set, and the testing dataset, test set. Let's perform a few steps to build the conditional inference tree. So, first we use ctree from the party package to build the classification model, and we run this line of code. Then we examine the built tree model. You can see the output here. You can also use help function to refer to the definition of binary tree class and read more about the properties of binary trees. You can refer to the documentation about the binary tree under the Help tab. Cool! In this video, we have learned building a classification model with a conditional inference tree. In the next video, we'll take a look at visualizing a conditional inference tree. This is video 7, Visualizing a Conditional Inference Tree. In the previous video, we learned building a classification model with a conditional inference tree. In this video, we will introduce how to use the plot function to visualize conditional inference trees. Similar to RPART, the party package also provides a visualization method for users to plot conditional inference trees. You need to have the first video completed by generating the conditional inference tree model, ctree.model. In addition to this, you need to have both train set and test set loaded in an R session. You can see train set and test set loaded here. Let's perform some steps to visualize the conditional inference tree. Use the plot function to plot ctree.model built in the previous video. This is the code you need to run. You can see the output here. This output figure reveals that every intermediate node shows the dependent variable name and the p-value. The split condition is displayed on the left and right branches. The terminal nodes show the number of categorized observations, n, and the probability of a class label of either 0 or 1. To obtain a simple conditional inference tree, one can reduce the built model with less input features and redraw the classification tree. This is the code for that. You can see the next plot. In this figure, we can see that we first build a classification model using total, day, charge as the only feature and churn as the class label. The built classification tree shows that when total day charge is above 48.18, the lighter grey area is greater than the darker grey in node 9, which indicates that the customer with a day charge of over 48.18 has a greater likelihood to churn where label equals yes. The visualization of the conditional inference tree comes from the plot, binary tree function. If you are interested in adjusting the layout of the classification tree, you may use the help function to read the documentation. You can see the documentation here. In this video, we have looked at visualizing a conditional inference tree. In the next video, we'll learn measuring the prediction performance of a conditional inference tree. This is video number 8, Measuring the Prediction Performance of a Conditional Inference Tree. In the previous video, we looked at visualizing a conditional inference tree. This video will explain how to generate a confusion matrix to measure the performance of a conditional inference tree. After building a conditional inference tree as a classification model, we can use the tree response and predict functions to predict categories of the testing dataset, test set, and further validate the prediction power with a classification table and a confusion matrix. You need to have the previous video completed by generating the conditional inference tree model ctree.model. In addition to this, you need to have both train set and test set loaded in an R session. We can see ctree.model along with train set and test set over here. Let's perform some steps to measure the prediction performance of a conditional inference tree. You can use the predict function to predict the category of the testing dataset, test set, with the help of this code. You can see the output over here. Furthermore, you can use Confusion Matrix from the Caret package to generate the performance measurements of the prediction result. We can use this code to get Confusion Matrix. You can see the output shown here. Next, you can also use the tree response function, which will tell you the list of class probabilities using this code. Here is the output. For the predict function, you can specify the type as response, prob, or node. If you specify the type as prob when using the predict function, you will get exactly the same result as what tree response returns. In this video, we have looked at measuring the prediction performance of a conditional inference tree. In the next video, we'll learn classifying data with the k-nearest neighbor classifier. This is video number 9, classifying data with the k-nearest neighbor classifier. In the previous video, we looked at measuring the prediction performance of a conditional inference tree. In this video, we are going to take a look at how to apply the k-nearest neighbor algorithm on the churn dataset. K-nearest neighbor, KNN, is a non-parametric lazy learning method. From a non-parametric view, it does not make any assumptions about data distribution. In terms of lazy learning, it does not require an explicit learning phase for generalization. KNN trains all samples and classifies new instances based on a similarity distance measure. For example, the similarity measure can be formulated as follows, shown on screen. In KNN, a new instance is classified to a label, class, that is common among the k-nearest neighbors. If k equals 1, then the new instance is assigned to the class where its nearest neighbor belongs. The only required input for the algorithm is k. If we give a small k input, it may lead to overfitting. On the other hand, if we give a large k input, it may result in underfitting. To choose a proper k value, one can count on cross-validation. You need to have the previous video completed by generating the training and testing datasets. Let's perform some steps to classify the churn data with the k-nearest neighbor algorithm. First, we need to install the class package and have it loaded in an R session. We can use this code for doing that. You can see that the class package is being installed. It's loaded now, as you can see here. Now let's replace yes and no of the voicemail plan and international plan attributes in both the training dataset and testing dataset to 1 and 0. We need to run these lines of code. Then use the KNN classification method on the training dataset and the testing dataset. For that, use this code. Here we build up a classification model by specifying k equals 3, which means choosing the 3 nearest neighbors. Then you can use the summary function to retrieve the number of predicted labels using this code. You can see the output here. Next, you can generate the classification matrix using the table function, using predicted factors and the testing dataset label as the input. This is the code for that. This is the output. Lastly, you can generate a confusion matrix by using the confusion matrix function with the help of this code. You need to load the Caret library first, as shown here, to use the confusion matrix function. Then run it. You can see the output here. The confusion matrix output reveals an accuracy result of 0.8723, which suggests that both the tree-based methods mentioned in previous recipes outperform the accuracy of the k-nearest neighbor classification method in this case. Still, we cannot determine which model is better, depending. There is another package named KKNN, which provides a weighted k-nearest neighbor classification, regression, and clustering. You can learn more about the package by reading documentation at this link. The advantages of KNN are: number 1, the cost of the learning process is 0. Number 2, it's non-parametric, which means that you do not have to make the assumption of data distribution. Number 3, you can classify any data whenever you can find similarity measures of given instances. The main disadvantages of KNN are: number 1, it is hard to interpret the classified result. Number 2, it is an expensive computation for a large dataset. Number 3, the performance relies on the number of dimensions. Therefore, for a high dimension problem, you should reduce the dimension fit to increase the process performance. The use of KNN does not vary significantly from applying a tree-based algorithm mentioned in the previous videos. However, while a tree-based algorithm may show you the decision tree model, the output produced by KNN only reveals classification category factors. However, before building a classification model, one should replace the attribute with a string type to an integer, since the k-nearest neighbor algorithm needs to calculate the distance between observations. In this video, we have looked at classifying data with the k-nearest neighbor classifier. In the next video, we'll take a look at classifying data with logistic regression. This is video number 10, classifying data with logistic regression. In the previous video, we have looked at classifying data with the k-nearest neighbor classifier. In this video, we will introduce how to classify data using logistic regression. Logistic regression is a form of probabilistic statistical classification model, which can be used to predict class labels based on one or more features. The classification is done by using the logit function to estimate the outcome probability. One can use logistic regression by specifying the family as a binomial while using the GLM function. Logistic regression is very similar to linear regression. The main difference is that the dependent variable in linear regression is continuous, but the dependent variable in logistic regression is dichotomous, or nominal. The primary goal of logistic regression is to use logit to yield the probability of a nominal variable is related to the measurement variable. We can formulate logit in this equation, where p is the probability that a certain event occurs. Let's see how to classify data using logistic regression. For that, you need to have completed the first video of this section by generating training and testing datasets. It is already loaded here. Let's perform some steps to classify the churn data with logistic regression. With the specification of family as a binomial, we apply the GLM function on the dataset, train set, by using churn as a class label and the rest of the variables as input features. This is the code we need to run. Now let's use the summary function to obtain summary information about the built logistic regression model using this code. You can see the output here. Then we find the built model contains insignificant variables, which would lead to misclassification. Therefore, we use significant variables only to train the classification model. We need to run this code. You can see the output here. You can then use a fitted model, fit, to predict the outcome of test set. You can also determine the class by judging whether the probability is above 0.5. This is the code which we need to run. It is done. Next, use the summary function. It will show you the binary outcome count and reveal whether the probability is above 0.5. Use this code and see the output here. You can generate the counting statistics based on the testing dataset label and predicted result. You need to run this code. This is the output. You can turn the statistics of the previous step into classification table, and then generate the confusion matrix with the help of this code. You can see the output here. Next, we generate a confusion matrix and for that we load the caret library using this code. So this is the output. The advantage of logistic regression is that it is easy to interpret. It directs model logistic probability and provides a confidence interval for the result. Unlike the decision tree, which is hard to update the model, you can quickly update the classification model to incorporate new data in logistic regression. The main drawback of the algorithm is that it suffers from multicollinearity, and therefore the explanatory variables must be linear independent. GLM provides a generalized linear regression model, which enables specifying the model in the option family. If the family is specified to a binomial logistic, you can set the family as a binomial to classify the dependent variable of the category. For more information on how to use the GLM function, please refer to Section 4, Understanding Regression Analysis, which covers how to interpret the output of the GLM function. In this video, we have learned classifying data with logistic regression. In the next video, we'll take a look at classifying data with the naive Bayes classifier. Hi, this is the last video of the 5th section, classifying data with the naive Bayes classifier. In the previous video, we looked at classifying data with logistic regression. In this video, we used the naive Bayes classifier from the E1071 package to build a classification model. The naive Bayes classifier is also a probability-based classifier, which is based on applying the Bayes theorem with a strong independent assumption. Naive Bayes assumes that features are conditionally independent, which the effect of a predictor, X, to class C is independent of the effect or other predictors to class C. It computes the posterior probability, PCX, as shown in the formula. Where this is called likelihood, Px is called the marginal likelihood, and Pc is called the prior probability. If there are many predictors, we can formulate the posterior probability as shown. In this video, we will introduce how to classify data with the naive Bayes classifier. You need to have the first video of this section completed by generating training and testing datasets. Let's perform some steps to classify the churn data with the naive Bayes classifier. Now load the E1071 library and employ the naive Bayes function to build the classifier. This is the code to do that. Type classifier to examine the function call, a priori probability, and conditional probability with the help of this code. You can see the output here. Next, you can generate a classification table for the testing dataset using this code. You can see the table here. Lastly, you can generate a confusion matrix from the classification table. First, you load the caret package and run the confusion matrix. You can see the output here. The advantage of naive Bayes is that it is relatively simple and straightforward to use. It is suitable when the training set is relatively small and may contain some noisy or missing data. Moreover, you can easily obtain the probability for a prediction. The drawbacks of naive Bayes are that it assumes that all features are independent and equally important, which is very unlikely in real-world cases. At last, we list a few algorithms in this section. First is recursive partitioning tree. Advantages are listed here. Number 1, it is very flexible and easy to interpret. Number 2, it works on both classification and regression problems. Number 3, it's non-parametric. The disadvantage is that it is prone to bias and overfitting. Next is conditional inference tree. Advantages are, number 1, it is very flexible and easy to interpret. Number 2, it works on both classification and regression problems. Number 3, it is non-parametric. Number 4, it is less prone to bias than a recursive partitioning tree. The disadvantage is that it is prone to overfitting. The third one is k-nearest neighbor classifier. The advantages are, number 1, the cost of learning process is 0. Number 2, it is non-parametric. Number 3, you can classify any data whenever you can find similarity measures of any given instances. The disadvantages are: number 1, it is hard to interpret the classified result. Number 2, computation is expensive for a large dataset. Number 3, its performance relies on the number of dimensions. Next, we will take a look at logistic regression. The advantages are: number 1, it is easy to interpret. Number 2, it provides model logistic probability. Number 3, it provides confidence interval. Number 4, you can quickly update the classification model to incorporate new data. The disadvantages are: number 1, it suffers multicollinearity. Number 2, it does not handle the missing value of continuous variables. Number 3, it's sensitive to extreme values of continuous variable. The final one is naive Bayes. The advantages are: number 1, it is relatively simple and straightforward to use. Number 2, it is suitable when the training set is relatively small. Number 3, it can deal with some noisy and missing data. And number 4, it can easily obtain the probability for a prediction. The disadvantages are: it assumes all features are independent and equally important, which is very unlikely in real-world cases. Number 2, it is prone to bias when the number of training sets increase. To learn more about the Bayes theorem, you can refer to this Wikipedia article. Great, so this final video helped us to classify data with the naive Bayes classifier. Let's summarize what we did in this section. We started off by training and testing datasets, and then we built a classification model with recursive partitioning trees. We also visualized and pruned a recursive partitioning tree and further measured its prediction performance. Next, we saw how to build a classification model with a conditional inference tree. Further, we saw the visualization of a conditional inference tree and measured its prediction performance. In the end, we classified data with the k-nearest neighbor classifier, logistic regression, and the naive Bayes classifier. In the next section, we'll take a look at neural network and SVM. Welcome to the 6th section of this course, titled Neural Network and SVM. In the previous section, we saw how to use R to perform classification using tree-based classifier, k-nearest neighbor classifier, logistic regression classifier, or the naive Bayes classifier. In this section, we will see how to classify data with a support vector machine and also choose its cost. We will also see how to visualize SVM fit and predict labels based on a model trained by a support vector machine. Further, we move on to tune the support vector machine and train a neural network with neural net. Later, we will visualize a neural network trained by neural net and labels based on a model trained by neural net. In the end, we will train a neural network with NNet and predict labels based on a model trained by NNet. Here is the first video of this section, titled Classifying Data with a Support Vector Machine. In this video, we continue to use the Telecom Churn dataset as our example data source for training the support vector machine. The two most well-known and popular support vector machine tools are libSVM and SVM-Lite. For our users, you can find the implementation of libSVM in the E107 package and SVM-Lite in the KLAR package. Therefore, you can use the implemented function of these two packages to train support vector machines. In this video, we will focus on using the SVM function, the libSVM implemented version, from the E107 package to train a support vector machine based on the Telecom customer churn data training dataset. For this video, we need to use the Telecom churn dataset. For those who have not prepared the dataset, please refer to the previous section. Now let's perform some steps to train the SVM. First, we need to load the E107 package. For that, you need to run this code. Train the support vector machine using the SVM function, with trainset as the input dataset, and use churn as the classification category. Within the training function, SVM, one can specify the kernel functions, cost, and the gamma function. For the kernel argument, the default value is radial, and one can specify the kernel to a linear, polynomial, radial basis, and sigmoid. As for the gamma argument, the default value is equal to 1/data dimension, and it controls the shape of the separating hyperplane. Increasing the gamma argument usually increases the number of support vectors. As for the cost, the default value is set to 1, which indicates that the regularization term is constant, and the larger the value, the smaller the margin is. Finally, you can obtain overall information about the built model with summary, as shown here. You can see the output here. The support vector machine constructs a hyperplane, or set of hyperplanes, that maximize the margin width between two classes in a high-dimensional space. In these, the cases that define the hyperplane are support vectors, as shown in this figure. Support vector machine starts from constructing a hyperplane that maximizes the margin width. Then, it extends the definition to a nonlinear separable problem. Lastly, it maps the data to a high-dimensional space where the data can be more easily separated with a linear boundary. The advantage of using SVM is that it builds a highly accurate model through an engineering problem-orientated kernel. Also, it makes use of the regularization term to avoid overfitting. It also does not suffer from local optimal and multicollinearity. The main limitation of SVM is its speed and size in the training and testing time. Therefore, it is not suitable or efficient enough to construct classification models for data that is large in size. Also, since it is hard to interpret SVM, how does the determination of the kernel take place? Regularization is another problem that we need to tackle. Another popular support vector machine tool is SVM Lite. Unlike the E1071 package, which provides the full implementation of libSVM, the KLAR package simply provides an interface to SVM Lite only. To use SVM Lite, one can perform the following steps. First, you need to install the KLAR package and load it. Then download the SVM Lite source code and binary for your platform with this link. For example, if your guest OS is Windows 64-bit, you should download the file from this link. Then you should unzip the file and put the workable binary in the working directory. You may check your working directory by using the getwd function, as shown here. Train the support vector machine using the SVM Lite function, for which we need to run this code. Oops, there is an error. Great, so in this video, we saw how to classify data with a support vector machine. In our next video, we will see how to choose the cost of a support vector machine. In the previous video, we saw how to classify data with a support vector machine. Welcome to the second video of this section, choosing the cost of a support vector machine. In this video, we demonstrate how different costs can affect the SVM classifier. The support vector machine creates an optimum hyperplane that separates the training data by the maximum margin. However, sometimes we would like to allow some misclassifications while separating categories. The SVM model has a cost function which controls training errors and margins. For example, a small cost creates a large margin, a soft margin, and allows more misclassifications. On the other hand, a large cost creates a narrow margin, a hard margin, and permits fewer misclassifications. In this video, we will illustrate how the large and small cost will affect the SVM classifier. In this video, we will use the IRIS dataset as our example data source. Let's perform some steps to generate two different classification examples with different costs. Subset the IRIS dataset with columns named as sepal length, sepal width, species, with species in Setosa and Virginica. Then you can generate a scatter plot with sepal.length as the x-axis and sepal.width as the y-axis. You can see the output here in the Plot tab. Next, you can train SVM based on iris.subset with the cost equal to 1. This is the line of code you need to run. Then we can circle the support vector with blue circles using this code. You can see the blue circles on this. Lastly, we can add a separation line on the plot with the help of this code. You can see the line in the graph. In addition to this, we create another SVM classifier where cost equals 10,000. This is the line of code you need to run. From this figure, we can see that the margin created is narrow, a hard margin, and no misclassification cases are present. As a result, the two examples show that the choice of different costs may affect the margin created and also affect the possibilities of misclassification. The idea of soft margin, which allows misclassified examples, was suggested by Karina Cortes and Vladimir N. Vapnik in 1995 in this paper. Nice! This video showed us how to choose the cost of a support vector machine. In the next video, we will see how to visualize an SVM fit. In the previous video, we saw how to choose the cost of a support vector machine. This is the third video of the section, Visualizing an SVM fit. In this video, we demonstrate how to use the plot function to visualize the SVM fit. To visualize the built model, one can first use the plot function to generate a scatter plot of data input and the SVM fit. In this plot, support vectors and classes are highlighted through the color symbol. In addition to this, one can draw a contour-filled plot of the class regions to easily identify misclassified samples from the plot. In this video, we will use two datasets, the IRIS dataset and the Telecom churn dataset. For the Telecom churn dataset, one needs to have completed the previous video by training a support vector machine with SVM, and to have saved the SVM fit model. Let's perform some steps to visualize the SVM fit object. Use SVM to train the support vector machine based on the IRIS dataset, and use the plot function to visualize the fitted model. This is the line of code you need to execute. You can see the plot here. Here, the petal.length assigned to the x-axis, petal.width assigned to the y-axis, and data points with X and O symbols scattered on the plot. Within the scatter plot, the X symbol shows the support vector, and the O symbol represents the data points. These two symbols can be altered through the configuration of the SV symbol and data symbol options. Both the support vectors and true classes are highlighted and colored, depending on their label. Green refers to Virginica, red refers to Versicolor, and black refers to Setosa. The last argument, slice, is set when there are more than two variables. Therefore, in this example, we use the additional variables sepal.width and sepal.length by assigning a constant of 3 and 4 respectively. Next, we take the same approach to draw the SVM fit based on customer churn data. In this example, we use total day minutes and total international charge as the two dimensions used to plot the scatter plot. Let's visualize the SVM fit object model using the plot function with the dimensions of total day minutes and total international charge. Run it. You will see the output plot here. Here the support vectors and data points in red and black are scattered closely together in the central region of the plot, and there is no simple way to separate them. There are other parameters, such as fill, grid, symbol palette, and so on, that can be configured to change the layout of the plot. You can use the help function to view the following document for further information. This is the code you can use for that. You can try using this code as well, but as there is no documentation, we cannot find any search results. In this video, we saw how to visualize the SVM fit. In our next video, we will predict labels based on a model trained by a support vector machine. This is the fourth video of this section, predicting labels based on a model trained by a support vector machine. In the previous video, we saw how to use the plot function to visualize the SVM fit. In this video, we will demonstrate how to use the predict function to predict values based on a model trained by SVM. In the previous video, we trained an SVM based on the training dataset. The training process finds the optimum hyperplane that separates the training data by the maximum margin. We can then utilize the SVM fit to predict the label category of new observations. So let's get started. You need to have completed the previous video by generating a fitted SVM and save the fitted model in Model. Let's perform some steps to predict the labels of the testing dataset. First, we need to predict the label of the testing dataset based on the fitted SVM and attributes of the testing dataset using this code. Then, you can use the table function to generate a classification table with the prediction result and labels of the testing dataset. This is the code we need to run for that. You can see the output here. Next, you can use class agreement to calculate coefficients compared to the classification agreement using this code. You can see the output here. The coefficients include diag, kappa, rand, and crand. The diag coefficient represents the percentage of data points in the main diagonal of the classification table. Kappa refers to diag, which is corrected for an agreement by a change, the probability of random agreements. Rand represents the rand index, which measures the similarity between two data clusters, and crand indicates the rand index, which is adjusted for the chance grouping of elements. Now you can use confusion matrix to measure the prediction performance based on the classification table. So we need to load the caret library as shown, and you can see the output here. Here the accuracy shows that the trained support vector machine can correctly classify most of the observations. However, accuracy alone is not a good measurement of a classification model. One should also reference sensitivity and specificity. Besides using SVM to predict the category of new observations, you can use SVM to predict continuous values. In other words, one can use SVM to perform regression analysis. In this example, we will show you how to perform a simple regression prediction based on a fitted SVM with the type specified as EPS regression. Let's perform the steps to train a regression model with SVM. First, we need to train a support vector machine based on a quartet dataset using this code. Now let's use the predict function to obtain prediction results. This is the line of code for that, and you can see the output here. Plot the predicted points as squares and the training data points as circles on the same plot. You can use this code for that. We can see the plot here. The scatter plot contains predicted data points and training data points. Awesome! In this video, we saw how to predict labels based on a model trained by a support vector machine. In our next video, we will see how to tune a support vector machine. In the previous video, we saw how to predict labels based on a model trained by a support vector machine. Welcome to the fifth video, Tuning a Support Vector Machine. In this video, we will demonstrate how to tune a support vector machine through the use of tune.svm. Besides using different feature sets and the kernel function in support vector machines, one trick that you can use to tune its performance is to adjust the gamma and cost configured in the argument. One possible approach to test the performance of different gamma and cost combination values is to write a for loop to generate all the combinations of gamma and cost as inputs to train different support vector machines. Fortunately, SVM provides a tuning function, tune.svm, which makes the tuning much easier. In this video, we will take a look at tuning the support vector machine. you need to have completed the previous video by preparing a training dataset, TrainSet. Let's perform some steps to tune the support vector machine. First, tune the support vector machine using tune.svm. This is the code for that. It will take a little time. Next, you can use the summary function to obtain the tuning result using this code. You can see the output here. After retrieving the best performance parameter from tuning the result, you can retrain the support vector machine with the best performance parameter. This is the code you need to run. You can see the output here. Then, you can use the predict function to predict labels based on the fitted SVM with the help of this code. Next, generate a classification table based on the predicted and original labels of the testing dataset using this code. You can see the output here. Also, generate a class agreement to measure the performance. This is the code to do that. This is the output here. Finally, you can use a confusion matrix to measure the performance of the retrained model. This is the line of code, and here is the output. For more information about how to tune SVM with svm.tune, you can use the help function to access this document. Wonderful! So this video showed us how to tune a support vector machine. In our next video, we will train a neural network with neural net. In the previous video, we saw how to tune a support vector machine. This is the 6th video, training a neural network with neural net. In this video, we will introduce how to use neural net to train a neural network. The neural network is constructed with an interconnected group of nodes, which involves the input, connected weights, processing element, and output. Neural networks can be applied to many areas, such as classification, clustering, and prediction. To train a neural network in R, you can use neural net, which is built to train multi-layer perceptron in the context of regression analysis, and contains many flexible functions to train forward neural networks. In this video, we will introduce how to use neural net to train a neural network. In this video, we will use an iris dataset as our example dataset. We will first split the iris dataset into a training and testing datasets, respectively. Let's perform some steps to train a neural network with neural net. First, we need to load the iris dataset and split the data into training and testing datasets, using these lines of code. Then install and load the neural net package using this code. You can see that the package is installed. Now add the columns versicolor, setosa, and virginica based on the name-matched value in the species column with the help of this code. Next, train the neural network with the neural net function, with 3 hidden neurons in each layer. Notice that the results may vary with each training, so you might not get the same result. You need to run this code for that. However, you can use set.seed at the beginning, so you can get the same result in every training process. You can see the result. From the output message, it shows the training process needed 23,355 steps until all the absolute partial derivatives of the error function were lower than 0.01, specified in the threshold. The error refers to the likelihood of calculating Akaike Information Criterion, AIC. Now you can view the summary information by accessing the result.matrix attribute of the built neural network model. Run this code. You can see the output here. The output reveals that the estimated weight ranges from -18 to 24.40. The intercepts of the first hidden layer are 1.69, 1.41, and 24.40, and the 2 weights leading to the first hidden neuron are estimated as 0.52 sepal.length, -12.49 sepal.width, -1.34 petal dot length and 16.93 petal dot width. Lastly, you can view the generalized weight by accessing it in the network. You can run this code for that. This is the output you will get. The model generates 12 generalized weights, which are the combination of 4 covariates: sepal.length, sepal.width, petal.length, petal.width, to 3 responses: setosa, virginica, versicolor. For a more detailed introduction on neural net, you can refer to this paper. Brilliant! So in this video, we saw how to use neural net to train a neural network. In our next video, we will demonstrate how to visualize the trained neural network. In the previous video, we saw how to train a neural network with neural net. Welcome to the 7th video, Visualizing a Neural Network Trained by Neural Net. In this video, we demonstrate how to visualize the trained neural network and the generalized weights of each trained attribute. The package Neural Net provides the plot function to visualize a built neural network and the GWPlot function to visualize generalized weights. In this video, we will cover how to use these two functions. You need to have completed the previous video by training a neural network and have all basic information saved in the network. Let's perform some steps to visualize the neural network and the generalized weights. You can visualize the trained neural network with the plot function using this code. You can see the neural network here. The plot displays the network topology of the trained neural network. Also, the plot includes the estimated weight, intercepts, and basic information about the training process. At the bottom of the plot, you can find the overall error and number of steps required to converge. Furthermore, you can use GWPlot to visualize the generalized weights with the help of this code. You can see the output here. This figure presents the generalized weight plot in regard to network.generalized.weights. The 4 plots display the 4 covariates: petal.width, sepal.width, petal.length, and petal.width, in regard to the versicolor response. If all the generalized weights are close to 0 on the plot, it means the covariate has little effect. However, if the overall variance is greater than 1, it means the covariate has a nonlinear effect. For more information about GWPlot, one can use the help function to access the documentation as shown here. Great! So this video showed us how to visualize a neural network trained by neural net. In our next video, we will predict labels based on a model trained by neural net. Welcome to the 8th video of this course, Predicting Labels based on a model trained by neural net. In the previous video, we visualized a neural network trained by neural net. In this video, we demonstrate how to predict labels based on a model trained by neural net. Similar to other classification methods, we can predict the labels of new observations based on trained neural networks. Furthermore, we can validate the performance of these networks through the use of confusion matrix. In the videos which follow, we will introduce how to use the compute function in a neural network to obtain a probability matrix of the testing dataset, labels, and use a table and confusion matrix to measure the prediction performance. You need to have completed the previous video by generating the training dataset, train set, and the testing dataset, test set. The trained neural network needs to be saved in the network. Let's perform some steps to measure the prediction performance of the trained neural network. First, generate a prediction probability matrix based on a trained neural network and the testing dataset, test set. This is the code we need to run. Then, obtain other possible labels by finding the column with the greatest probability using this code. Generate a classification table based on the predicted labels and the labels of the testing dataset with the help of this code. You can see the output here. Next, generate class agreement from the classification table. use this code. This is the output. Finally, use confusion matrix to measure the prediction performance. Use this code. The output is here. As we have created the classification table, we can employ a confusion matrix to measure the prediction performance of the built neural network. As the confusion matrix is in the caret package, so you need to load the caret package first. This is the code for that, and this is the output. In this video, we use the net.result function, which is the overall result of the neural network, used to predict the labels of the testing dataset. Apart from examining the overall result by accessing net.result, the compute function also generates the output from neurons in each layer. You can examine the output of neurons to get a better understanding of how compute works. You can run this code to see the same output. This is the output of compute neuron. In this video, we saw how to predict labels based on a model trained by neural net. In our next video, we will train a neural network with NNet. In the previous video, we predicted labels based on a model trained by neural net. This is the 9th video, training a neural network with NNet. In this video, we demonstrate steps to train a neural network model with the NNet package. The NNet package is another package that can deal with artificial neural networks. This package provides the functionality to train feed-forward neural networks with traditional backpropagation. As you can find most of the neural network function implemented in the neural net package, in this video we provide a short overview of how to train neural networks with NNet. In this video, we do not use the train set and test set generated from the previous step. Please reload the Iris dataset again. Let's perform some steps to train the neural network with NNet. First, install and load the NNet package using this code. You can see that the NNet package is getting installed. Now let's load the package using these codes. It has loaded now. Next, split the dataset into training and testing datasets using this code. Then train the neural network with NNet. This is the code to do that. This is the output. With this function, we can set the classification formula, source of data, number of hidden units in the size parameter, initial random weight in the range parameter, parameter for weight decay in the decay parameter, and the maximum iteration in the maxit parameter. Here we have set maxit to 200. The training process repeatedly runs until the value of the fitting criterion plus the decay term converge. This is the output. There will be 200 iterations. Next, use the summary to obtain information about the trained neural network using this code. You can see the output here. This reveals that the model is built with 4-2-3 networks with 19 weights. Also, the model shows a list of weight transitions from one node to another at the bottom of the printed message. For those who are interested in the background theory of NNet and how it is made, please refer to these articles. So, in this video, we trained a neural network with NNet. In our final video, we will predict labels based on a model trained by NNet. In the previous video, we trained a neural network with NNet. This is the final video, predicting labels based on a model trained by NNet. In this video, we will predict the labels of the testing dataset based on the trained neural network. In this video, we predict labels based on a model trained by NNet. Furthermore, we can assess the model with a confusion matrix adapted from the caret package. So let's get started. You need to have completed the previous video by generating the training dataset, train set, and the testing dataset, test set, from the Iris dataset. The trained neural network also needs to be saved as iris.nn. You can see it is saved here. Let's perform some steps to predict labels based on the trained neural network. Generate the predictions of the testing dataset based on the model iris.nn. This is the code you need to run for that. Within the predict function, we specify the type argument to the class, so the output will be class labels instead of a probability matrix. Now let's generate a classification table based on the predicted labels and labels of the testing dataset. This is the code which you need to run. Lastly, generate a confusion matrix based on the classification table. We need to load the caret library for that. You can see the output here. The confusion matrix helps us to predict the performance of the trained neural network. For the predict function, if the type argument to class is not specified, by default, it will generate a probability matrix as a prediction result, which is very similar to net.result, generated from the compute function within the neural net package. This is the code which you can test and see the output here. Awesome! In this video, we saw how to predict labels based on a model trained by NNet. This was the end of the 6th section. In this section, we classified data with a support vector machine and chose its cost. We also visualized an SVM fit and predicted labels based on a model trained by a support vector machine. Furthermore, we saw how to tune a support vector machine and train a neural network with NeuralNet and predicted labels based on a model trained by NeuralNet. In the end, we trained a neural network with NNet and predicted labels based on a model trained by NNet. In our next section, we will study model evaluation. Welcome to the 7th section of this course, Model Evaluation. In the previous section, we took a look at neural networks and support vector machines. In this section, we will discuss how one can implement a simple R script or use one of the packages, for example caret or RMiner, to evaluate the performance of a fitted model. Let's begin with the first video of this section, titled Estimating Model Performance with K-fold Cross-Validation. In this video, we implement a simple script performing 10-fold cross-validations. Let's get started. The K-fold cross-validation technique is a common technique used to estimate the performance of a classifier as it overcomes the problem of overfitting. For K-fold cross-validation, the method does not use the entire dataset to build the model. Instead, it splits the data into a training dataset and a testing dataset. Therefore, the model built with a training dataset can then be used to assess the performance of the model on the testing dataset. By performing n repeats of the K-fold validation, we can then use the average of n accuracies to truly assess the performance of the built model. In this video, we will illustrate how to perform a K-fold cross-validation. Here we will continue to use the Telecom churn dataset as the input data source to train the support vector machine. For those who have not prepared the dataset, please refer to Section 5, Classification I, Tree, Lazy, and Probabilistic for detailed information. Let's perform a few steps to cross-validate the Telecom churn dataset. First, you need to load the E107 package as library E1071. Then split the index into 10-fold using the cut function. This is the code for that. Next, use for loop to perform a 10-fold cross-validation. Repeat 10 times with the help of this code. It is running now. It's completed now. You can then print the accuracies. This is the output. Lastly, you can generate average accuracies with the mean function using this code. You can see the mean value here. Also, if you wish to perform the K-fold validation with the use of other models, simply replace the line to generate the variable fit to whatever classifier you prefer. For example, if you would like to assess the naive Bayes model with a tenfold cross-validation, you just need to replace the calling function from SVM to naive Bayes. This is the naive Bayes function, as you can see. Run this code. So then you can print the accuracies and calculate its mean using the code. This is the output. Great! So this video walked us through the k-fold cross-validation for estimating model performance. In our next video, we will perform cross-validation with the E1071 package. In our previous video, we saw how to estimate model performance with k-fold cross-validation. Welcome to the second video, performing cross-validation with the E1071 package. In this video, we use the tune.svm function to tune the SVM model with the given formula, dataset, gamma cost, and control functions. We can obtain the performance measures of the tuning and further use the optimum model to generate a classification table. Besides implementing a loop function to perform the k-fold cross-validation, you can use the tuning function, for example tune.nnet, tune.randomforest, tune.rpart, tune.svm, and tune.knn within the E1071 package to obtain the minimum error value. In this video, we will illustrate how to use tune.svm to perform the tenfold cross-validation and obtain the optimum classification model. Here, we continue to use the Telecom churn dataset as the input data source to perform tenfold cross-validation. Let's perform some steps to retrieve the minimum estimation error using cross-validation. Apply tune.svm on the train set with the tenfold cross-validation as the tuning control. If you find an error message, such as could not find function predict.func, please clear the workspace, restart the R session, and reload the E1071 library again. This is the code which we need to run. We use the tune.svm function to tune the SVM model with the given formula, dataset, gamma, cost, and control functions. Within the tune.control options, we configure the option as cross equals 10, which performs a tenfold cross-validation during the tuning process. Next, you can obtain the summary information of the model, tuned against the highlighted code. You can see that the tuning process will eventually return the minimum estimation error, performance detail, and the best model during the tuning process. Therefore, we can obtain the performance measures of the tuning and further use the optimum model to generate a classification table. Then you can access the performance details of the tuned model. This is the code for that. Lastly, you can use the optimum model to generate a classification table using this code. You can see the output here. In the E1071 package, the tune function uses a grid search to tune parameters. For those interested in other tuning functions, use the help function to view the tune document. Use this code. You can learn more about it on this page. Wow! We successfully carried out cross-validation with the E1071 package. In our next video, we will perform cross-validation with the Caret package. Our previous video showed us how to perform cross-validation with the E1071 package. This is the third video, titled Performing Cross-Validation with the Caret package. In this video, we demonstrate how convenient it is to conduct the k-fold cross-validation using the Caret package. The Caret Classification and Regression Training package contains many functions in regard to the training process for regression and classification problems. Similar to the E1071 package, it also contains a function to perform the k-fold cross-validation. In this video, we will demonstrate how to perform k-fold cross-validation using the Caret package. Here we will continue to use the Telecom churn dataset as the input data source to perform the k-fold cross-validation. Let's perform some steps to perform the k-fold cross-validation with the caret package. First, let's set up the control parameter to train with the 10-fold cross-validation in 3 repetitions using this code. The process of repeating the k-fold validation is called repeated k-fold validation, which is used to test the stability of the model. If the model is stable, one should get a similar test result. Then, you can train the classification model on telecom churn data with RPART as shown in this code. We need to run this code. Finally, you can examine the output of the general model. This is the code for that. You can see the output here. The model outputs 3 resampling results as shown here. Of these results, the model with CP equals 0.05555556 has the largest accuracy value, 0.904, and is therefore selected as the optimal model for classification. You can configure the resampling function in train control, in which you can specify boot, boot632, CV, repeated CV, LOOCV, LGOCV, none, OOB, adaptive CV, adaptive boot, or adaptive LGOCV. To view more detailed information on how to choose the resampling method, view the train control document. You can run this line of code for that. You can see the documentation here, where you can learn more about it. Awesome! We saw how to perform cross-validation with the caret package. In the next video, we will see how to rank the variable importance with the caret package. In the previous video, we performed cross-validation with the caret package. Here we are at the 4th video of this section, ranking the variable importance with the caret package. In this video, we first used the var_imp function to retrieve the variable importance and obtain the summary. The overall results show the sensitivity measure of each attribute. Next, we plot the variable importance in terms of rank. After building a supervised learning model, we can estimate the importance of features. This estimation employs a sensitivity analysis to measure the effect on the output of a given model when the inputs are varied. In this video, we will show you how to rank the variable importance with the caret package. You need to have completed the previous video by storing the fitted RPART object in the model variable. Let's perform some steps to rank the variable importance with the caret package. First, you can estimate the variable importance with the var_imp function. This is the code which you need to run. You can see the output here. This overall results shows the sensitivity measure of each attribute. Then you can generate the variable importance plot with the plot function using this code. You can see the graph here. Here we plot the variable importance in terms of rank, which shows the number, customer, service, calls attribute is the most important variable in the sensitivity measure. In some classification packages, such as RPART, the object generated from the training model contains the variable importance. We can examine the variable importance by accessing the output object with the help of this code. You can run this code to see the output, which is as shown. Brilliant! So we saw how to rank the variable importance with the caret package. In our next video, we will see how to rank the variable importance with the R-minor package. In the previous video, we saw how to rank variable importance with the caret package. This is the 5th video, ranking the variable importance with the R-minor package. In this video, we will first install and load the R-minor package. We would then fit the SVM model with the training set. In the end, we will obtain the variable importance and plot it. Besides using the caret package to generate variable importance, you can use the R package to generate the variable importance of a classification model. In this video, we will illustrate how to use R to obtain the variable importance of a fitted model. Here, we will continue to use the telecom churn dataset as the input data source to rank the variable importance. Let's perform some steps to rank the variable importance with R. Install and load the package R. This is the code to do that. You can see that the package is being installed. It might take some time. Once it is done, you need to load the package using this code. You can see R package is loaded in R session with the warning message. Fit the SVM model with the training set using this code. Use the importance function to obtain the variable importance. This is the code to do that. Plot the variable importance ranked by the variance using this code. You can see the graph here. As per the graph, you can see that number, customer, service, calls is the most important variable in the measure of sensitivity. The R package provides many classification models for one to choose from. If you are interested in using models other than SVM, you can view these options with the command shown here. You can see the documentation in the Help tab for more information. Wonderful! We saw how to rank the variable importance with R package. In our next video, we will see how to find highly correlated features with the caret package. In our previous video, we saw how to rank the variable importance with the R package. Welcome to the 6th video, finding highly correlated features with the caret package. In this video, we search for highly correlated attributes using the caret package. In order to retrieve the correlation of each attribute, we first remove non-numeric attributes. Then, we perform correlation to obtain a correlation matrix. Later, we find the highly correlated attributes with their names. When performing regression or classification, some models perform better if highly correlated attributes are removed. The caret package provides the find correlation function, which can be used to find attributes that are highly correlated to each other. In this video, we will demonstrate how to find highly correlated features using the caret package. Here, we will continue to use the telecom churn dataset as the input data source to find highly correlated features. Let's perform some steps to find highly correlated attributes. First, we need to remove the features that are not coded in numeric characters. We will use this code for that. Then, you can obtain the correlation of each attribute using this code. Next, we use find correlation to search for highly correlated attributes with a cutoff equal to 0.75, as you can see here in this code. We then obtain the name of highly correlated attributes. This is the line of code for that. You can see the output here. In addition to the caret package, you can use the leaps, genetic, and anneal functions in the subselect package to achieve the same goal. Amazing! So we just saw how to find highly correlated features with the caret package. In the next video, we will see how to select features using the caret package. In our previous video, we saw how to highlight correlated features with the caret package. This is the 7th video, titled Selecting Features Using the Caret Package. In this video, we first transform the factor-encoded attributes into multiple binary attributes. We then set up control parameters for training using the cross-validation method. We use the recursive feature, elimination, to perform feature selection. We then generate the summary of feature selection, which contains resampling, a performance over the subset size, and top variables. We can then use the obtained model information to plot the number of variables against accuracy. The feature selection method searches the subset of features with minimized predictive errors. We can apply feature selection to identify which attributes are required to build an accurate model. The Caret package provides a recursive feature elimination function, RFE, which can help automatically select the required features. In this video, we will demonstrate how to use the Caret package to perform feature selection. Here we will continue to use the Telecom Churn dataset as the input data source for feature selection. Let's perform some steps to select features. First, we need to transform the feature named as International Plan of the training dataset, TrainSet, to INTL Yes and INTL No. For that, we need to execute this code. Now we need to transform the feature named as Voicemail Plan of the training dataset, TrainSet, to Voice Yes and Voice No. This is the code which we need to run. Remove the International Plan and Voicemail Plan attributes and combine the training dataset, TrainSet, with the data frames INTL Plan and Voice Plan. For that, we use this code. Next, we need to transform the feature named as International Plan of the testing dataset, TestSet, to INTL Yes and INTL No. Use this code for that. Transform the feature named as Voicemail Plan of the training dataset, TrainSet, to Voice Yes and Voice No. Execute this code for that. Now remove the International Plan and Voicemail Plan attributes and combine the testing dataset, TestSet, with the data frames INTL Plan and Voice Plan. This is the code for that. We then create a feature selection algorithm using linear discriminant analysis. Use this highlighted code for that. Next, we perform a backward feature selection on the training dataset, TrainSet, using subsets from 1 to 18. Here is the code for that. You can see the output here. The RFE function generates the summary of feature selection, which contains resampling a performance over the subset size and top variables. Next, we can plot the selection result using this code. You can see the plot here. It is obvious that using 12 features can obtain the best accuracy. In addition to this, we can retrieve the best subset of the variables, in 12 variables in total, the fitted model. We can then examine the best subset of the variables with the help of this code. You can see the output here. Now we can examine the fitted model. This is the line of code to do that. Here is the output. Finally, we can calculate the performance across resamples. This code will help us do that. Here is the output. You can see the accuracy and kappa value. Lastly, we can calculate the performance across resamples, which yields an accuracy of 0.86 and a kappa of 0.25. In order to specify the algorithm used to control feature selection, one can change the control function specified in RFE control. Here are some of the options you can use. Awesome! So in this video, we saw how to select features using the Caret package. The next video will show us how to measure the performance of the regression model. In the previous video, we saw how to select features using the Caret package. We now move on to the 8th video, titled Measuring the Performance of the Regression Model. In this video, we will calculate the root mean square error, relative square error, and R-square as the quantifier of the performance of the regression models. To measure the performance of a regression model, we can calculate the distance from predicted output and the actual output as a quantifier of the performance of the model. Here, we often use the root mean square error, RMSE, relative square error, RSE, and R-square as common measurements. In this video, we will illustrate how to compute these measurements from a built regression model. Here we will use the Quartet dataset, which contains 4 regression datasets as our input data source. So let's perform some steps to measure the performance of the regression model. Load the Quartet dataset from the car package. Use this code for that. Now, let's plot the attribute y3 against x using the lm function using this code. You can see the plot here. You can retrieve predicted values by using the predict function. This is the code which you need to run for that. Now, you can calculate the root mean square error using this code. You can see the output here. The root mean square is as shown here. You can calculate the relative square error using this code. Here is the output. This is the relative square error. Also, you can use r-square as a measurement using this code. This is the r-square value. You can then plot attribute y3 against x using the RLM function from the mass package. This is the code to load the mass package and plot the graph. You can see the graph here. You can then retrieve the predicted value using the predict function. This is the code for that. Next, you can calculate the root mean square error using the distance of the predicted and actual value. Use this code for that. This is the value of the root mean square error. Now let's calculate the relative square error between the predicted and actual labels. This is the relative square error value. Now you can calculate the r-square value. This is the code for that. Here is the r-square value. As this dataset has an outlier at x equals 13, we would like to quantify how the outlier affects the performance measurement. This comparison shows that the outlier may be biased towards the performance measure and may lead us to choose the wrong model. If you would like to perform cross-validation on a linear regression model, you can use the tune function within the E1071 package. We can do that with this code. So, we can see the error estimation of LM. Other than the E107 package, you can use the train function from the caret package to perform cross-validation. In addition to this, you can use the CVLM from the DAG package to achieve the same goal. Great! So in this video, we saw how to measure the performance of the regression model. In the next video, we will measure the prediction performance with a confusion matrix. In the previous video, we saw how to measure the performance of the regression model. This is the 9th video, titled Measuring Prediction Performance with a Confusion Matrix. In this video, we demonstrate how to obtain a confusion matrix to measure the performance of a classification model. To measure the performance of a classification model, we can first generate a classification table based on our predicted label and actual label. Then, we can use a confusion matrix to obtain performance measures such as precision, recall, specificity, and accuracy. In this video, we will demonstrate how to retrieve a confusion matrix using the caret package. Here we will continue to use the Telecom Churn dataset as our example dataset. Let's perform some steps to generate a classification measurement. Train an SVM model using the training dataset. This is the code which you need to run. You need to see that the package required is being loaded and run. You can then predict labels using the fitted model, svm.model, using this code. Next, you can generate a classification table with the help of this code. This is the code for that. You can see the output here. Lastly, you can generate a confusion matrix using the prediction results and the actual labels from the testing dataset. Execute this code and you will see the same output as shown. If you are interested in the available methods that can be used in the train function, you can refer to this website shown on screen. Nice! So this video showed us how to measure prediction performance with a confusion matrix. In the next video, we will measure the prediction performance using ROCR. In the previous video, we saw how to measure prediction performance with a confusion matrix. This is the 10th video of this course, titled Measuring Prediction Performance using ROCR. Here we will demonstrate how to generate an ROC curve to illustrate the performance of a binary classifier. A receiver operating characteristic, ROC curve, is a plot that illustrates the performance of a binary classifier system and plots the true positive rate against the false positive rate for different cut points. We most commonly use this plot to calculate the area under a curve, AUC, to measure the performance of a classification model. In this video, we will demonstrate how to illustrate an ROC curve and calculate the AUC to measure the performance of a classification model. Here we will continue using the Telecom churn dataset as our example dataset. Let's perform some steps to generate two different classification examples with different costs. First, you should install and load the ROCR package using this code. You can see that the ROCR package is being installed. We can then load the package. Train the SVM model using the training dataset with a probability equal to true. This is the code for that. Make predictions based on the trained model on the testing dataset with the probability set as true. Use this code for that. Obtain the probability of labels with yes using this code. Use the prediction function to generate a prediction result with the help of the highlighted code. Now use the performance function to obtain the performance measurement. This code will help you to do that. Next, visualize the ROC curve using the plot function as shown. You can see the plot here. The AUC value here is 0.92, which indicates that the SVM classifier performs well in classifying telecom user churn datasets. For those interested in the concept and terminology of ROC, you can refer to the Wikipedia link as shown. Awesome! We saw how to measure prediction performance using ROCR. In the next video, we will compare an ROC curve using the Caret package. In our previous model, we measured the prediction performance using ROCR. Welcome to the 11th video, comparing an ROC curve using the Caret package. In this video, we demonstrate how we can compare fitted models by illustrating their ROC curve in one figure. In previous sections, we introduced many classification methods. Each method has its own advantages and disadvantages. However, when it comes to the problem of how to choose the best fitted model, you need to compare all the performance measures generated from different prediction models. To make the comparison easy, the Caret package allows us to generate and compare the performance of models. In this video, we will use the function provided by the Caret package to compare different algorithm-trained models on the same dataset. Here, we will continue to use Telecom dataset as our input data source. Let's perform some steps to generate an ROC curve of each fitted model. First, we need to install and load the library proc using these lines of code. You can see the package getting installed and loaded. Now set up the training controls with a 10-fold cross-validation in 3 repetitions. This is the code for that. You can see the error here. To resolve that, we can load the Caret library as shown. Now run the code again. We have now succeeded. Then you can train a classifier on the training dataset using GLM with the help of this code. We can see a few warnings. Also, you can train a classifier on the training dataset using SVM. This is the code which we need to run for that. It might take a little time. It's done now. To see how rpart performs on the training data, we use the rpart function. For that, use these lines of code. You can make predictions separately based on different training models using this code. Now you can generate the ROC curve of each model and plot the curve on the same figure. You can use this code for that. You can see the graph and statistic here. Let's see the values. The AUC of the GLM model, red, is 0.82. For the SVM model, it is 0.921, plotted in green. And the AUC of the rpart model, blue, is 0.7581. From this graph, it is obvious that the SVM performs the best among all the fitted models on this training dataset, without requiring tuning. We use another ROC visualization package, PROC, which can be employed to display and analyze ROC curves. If you would like to know more about the package, please use the help function as shown here. You can see the documentation here. Great! We compared an ROC curve in this video using the Caret package. In our next video, we will measure performance differences between models with the Caret package. In our previous video, we compared an ROC curve using the Caret package. This is the final video of this section, titled Comparing an ROC Curve Using the Caret Package. In this video, we demonstrate how we can compare fitted models by illustrating their ROC curve in one figure. In the previous video, we introduced how to generate ROC curves for each generated model and have the curve plotted on the same figure. Apart from using an ROC curve, one can use the resampling method to generate statistics of each fitted model in ROC, sensitivity and specificity metrics. Therefore, we can use these statistics to compare the performance differences between each model. This video will introduce how to measure performance differences between fitted models with the Caret package. One needs to have completed the previous video by storing the GLM fitted model, SVM fitted model, and the rpart fitted model into glm.model, svm.model, and rpart.model respectively. Let's perform some steps to measure performance differences between each fitted model. First, we need to resample the 3 generated models. This is the code for that. Then, you can obtain a summary of the resampling result using summary functions. This is the code for that. You can see the output here. The output shows the entire statistics of 3 models in the ROC, sensitivity and specificity metrics. Next, use dot plot to plot the resampling result in the ROC metric. For that, use this code. You can see the output here. You can see how ROC varied between each model, that is SVM, GLM, and rpart model. Also, you can use a box whisker plot to plot the resampling result. This is the code for that. You can see the box plot here. Besides using dot plot and BW plot to measure performance differences, one can use density plot, splom, and XY plot to visualize the performance differences of each fitted model in the ROC, sensitivity, and specificity metrics. Great! At the end of this section, we saw how to measure performance differences between models with the Caret package. This is the final video. Let's summarize what we've covered in this section. In this video, we saw how to estimate model performance with k-fold cross-validation. We then performed cross-validation with the E1071 and Caret package. Further, we ranked the variable importance with Caret and R minor package. Next, we found and selected highly correlated features with the caret package. Later, we moved on to measure the performance of a regression model. We also measured the prediction performance of confusion matrix and ROCR. In the end, we saw how to compare an ROC curve using the caret package and to measure performance differences between models with the caret package. In our next section, we will take a look at the ensemble learning. Hi, and welcome to Section 8, Ensemble Learning. In this section, we will discuss how to use bagging and boosting to classify data. We can then perform cross-validation to estimate the error rate of each classifier. In addition to this, we'll introduce the use of a margin to measure the certainty of a model. Next, we cover random forests, similar to the bagging and boosting methods, and introduce how to train the model to classify data and use margins to estimate the model certainty. Lastly, we'll demonstrate how to estimate the error rate of each classifier and use the error rate to compare the performance of different classifiers. Now we move on to the first video of this section that deals with classifying data with the bagging method. In this video, we will illustrate how to use the bagging method from AdaBag to generate a classification model using the Telecom Churn dataset. Ensemble learning is a method to combine results produced by different learners into one format, with the aim of producing better classification results and regression results. In previous sections, we discussed several classification methods. These methods take different approaches, but they all have the same goal, that is, finding an optimum classification model. However, a single classifier may be imperfect, which may misclassify data in certain categories. As not all classifiers are imperfect, a better approach is to average the results by voting. In other words, if we average the prediction results of every classifier with the same input, we may create a superior model compared to using an individual method. In ensemble learning, bagging, boosting, and random forest are the three most common methods. Bagging is a voting method, which first uses Bootstrap to generate a different training set, and then uses the training set to make different base learners. The bagging method employs a combination of base learners to make a better prediction. Boosting is similar to the bagging method. However, what makes boosting different is that it first constructs the base learning in sequence, where each successive learner is built for the prediction residuals of the preceding learner. With the means to create a complementary learner, it uses the mistakes made by the previous learners to train the next base learner. Random forest uses the classification results voted from many classification trees. The idea is simple. A single classification tree will obtain a single classification result with a single input vector. However, a random forest grows many classification trees, obtaining multiple results from a single input. Therefore, a random forest will use the majority of votes from all the decision trees to classify data or use an average output for regression. Bagging is derived from the name Bootstrap aggregating, which is a stable, accurate, and easy-to-implement model for data classification and regression. The definition of bagging is that, given a training dataset of size n, bagging performs bootstrap sampling and generates m new training sets, di, each of size n. Finally, we can fit m bootstrap samples to m models and combine the result by averaging the output for regression or voting for classification. The advantage of using bagging is that it is a powerful learning method, which is easy to understand and implement. However, the main drawback of this technique is that it is hard to analyze the result. The AdaBag package implements both boosting and bagging methods. For the bagging method, the package implements Bryman's bagging algorithm, which first generates multiple versions of classifiers and then obtains an aggregated classifier. In this video, we continue to use the Telecom Churn dataset as the input data source for the bagging method. For those who have not prepared the dataset, please refer to Section 5, Classification Tree, Lazy and Probabilistic for detailed information. Let's perform some steps to generate a classification model for the Telecom Churn dataset. First, you need to install and load the Adabag package. It might take a while to install Adabag. Next, you can use the bagging function to train a training dataset. This is the line of code we need to run. The result may vary during the training process. Now, access the variable importance from the bagging result using this line of code. You can see the output here. You can set the number of iterations to 10 in the mFinal argument. Once the classification model is built, you can examine the importance of each attribute. Ranking the attributes by importance reveals the number of customer service calls plays a crucial role in the classification model. After generating the classification model, you can use the predicted results from the testing dataset. Apply the predict bagging function to predict the labels of the testing dataset. Now, we can use the labels of the testing dataset and predicted results to generate a classification table and obtain the average error. So, here we obtain a classification table. Finally, we can retrieve the average error of the bagging result with this line of code. This is the average error. Now, besides Adabag, the IPRED package provides a bagging method for classification tree. We demonstrate here how to use the bagging method of the IPRED package to train a classification model. First, you need to install and load the IPRED package. You can then use the bagging method to fit the classification model. This is the line of code to do that. This is the output, where the misclassification error is 0.0557. Next, obtain an out-of-bag estimate of misclassification of the errors. This is the value. You can then use the predict function to obtain the predicted labels of the testing dataset. Once you run this line of code, obtain the classification table from the labels of the testing dataset and prediction result. This is the code you'd need to use. And here is the output of the predicted table. Cool, isn't it? In this video, we have learned classifying data with the bagging method. Awesome! In the next video, we'll take a look at performing cross-validation with the bagging method. In the previous video, we looked at classifying data with the bagging method. In this video, we will introduce how to use bagging.cv to perform cross-validation with the bagging method. To assess the prediction power of a classifier, you can run a cross-validation method to test the robustness of the classification model. Here we continue to use the Telecom Churn dataset as the input data source to perform a k-fold cross-validation with the bagging method. Let's perform some steps to retrieve the minimum estimation errors by performing cross-validation with the bagging method. First, we will use bagging.cv to make a 10-fold classification on the training dataset with 10 iterations. We specify v equals 10 and mFinal equals 10. Once that is done, you can then obtain the confusion matrix from the cross-validation results. This is the line of code to do that. Here, you can see the output. Lastly, you can retrieve the minimum estimation errors from the cross-validation results. This is the value of the error. If you are interested in tuning the parameters of bagging.cv, please view the bagging.cv document by using the Help function. You can see the documentation in the Help tab, where you can learn more. Awesome! In this video, we performed cross-validation with the bagging method. Great! In the next video, we'll learn about classifying data with the boosting method. In the previous video, we learned how to perform cross-validation with the bagging method. In this video, we will use the boosting method in AdaBag to classify the telecom churn dataset. The idea of boosting is to boost weak learners, for example a single decision tree, into strong learners. Assuming that we have n points in our training dataset, we can assign a weight, w, I, where I is less than n and greater than or equal to 0, for each point. Then, during the iterative learning process, we assume the number of iterations is m. We can reweigh each point in accordance with the classification result in each iteration. If the point is correctly classified, we should decrease the weight. Otherwise, we increase the weight of the point. When the iteration process is finished, we can then obtain the M-fitted model, Fix. Finally, we can obtain the final prediction through the weighted average of each tree's prediction, where the weight, B, is based on the quality of each tree. Both bagging and boosting are ensemble methods, which combine the prediction power of each single learner into a strong learner. The difference between bagging and boosting is that bagging method combines independent models, but boosting performs an iterative process to reduce the errors of preceding models by predicting them with successive models. Similar to the bagging method, boosting starts with a simple or weak classifier and gradually improves it by reweighting the misclassified samples. Thus, the new classifier can learn from previous classifiers. The AdaBag package provides implementation of the AdaBoost M1 and SAM algorithms. Therefore, one can use the boosting method in AdaBag to perform ensemble learning. In this video, we will continue to use the telecom churn dataset as the input data source to perform classifications with the boosting method. You need to have the AdaBag package loaded in R before commencing. Let's perform some steps to classify the telecom churn dataset with the boosting method. You can use the boosting function from the AdaBag package to train the classification model. This is the line of code for that. One can specify parameters such as the number of iterations, mfinal equals 10, the weight update coefficient, coeflearn equals Freund, the weight of how each observation is used, and the control for rpart, a single decision tree. We set the iteration to 10 using Freund, the AdaBoost M1 algorithm implemented method, as coeflearn, booz set to false, and max depth set to 3 for rpart configuration. We use the boosting method to fit the classification model and then save it in churn.boost. You can then make a prediction based on the boosted model and testing dataset. We obtain predicted labels using the prediction function. Once it's done, you can retrieve the classification table from the predicted results. That's the output. Finally, you can obtain the average errors from the predicted results. This is the average error. In addition to using the boosting function in the AdaBag package, one can also use the caret package to perform a classification with the boosting method. First, load the mboost and PROC package. You can see that mboost package is not available, so we need to install the mboost package. Also, install and load PROC. It's being installed. OK. It's loaded now. Next, set the training control with the train control function and use the train function to train the classification model with AdaBoost. This is the line of code you need to run. Now the train control function is included in the library called carrots. So we need to first load carrot library. And then we can try again. Once it's done, use the summary function to obtain the details of the classification model. You can see the output here. Next, use the plot function to plot the ROC curve within different iterations. The curve would be similar to this one. Finally, we can make predictions using the predict function and view the classification table. You can see the output here. Great! In this video, we have learned classifying data with the boosting method. Amazing! In the next video, we'll perform cross-validation with the boosting method. In the previous video, we looked at classifying data with the boosting method. In this video, we will demonstrate how to perform cross-validation using boosting.cv from the package Adabag. Similar to the bagging function, Adabag provides a cross-validation function for the boosting method, named boosting.cv. In this video, we continue to use the telecom churn dataset as the input data source to perform a k-fold cross-validation with the boosting method. Let's perform some steps to retrieve the minimum estimation errors via cross-validation with the boosting method. First, you can use boosting.cv to cross-validate the training dataset. If v is set to 10 and mfinal is set to 5, the boosting method will perform 10-fold cross-validations with 5 iterations. Also, one can set the control of the rpart fit within the parameter. We can set the complexity parameter to 0.01. You can then obtain the confusion matrix from the boosting results using this line of code. This is the output classification table. Finally, you can retrieve the average errors of the boosting method. You can see this is the estimated error. For those who require more information on tuning the parameters of boosting.cv, please view the boosting.cv document by using the help function. You can see the documentation in the help tab. Cool! In this video, we have looked at performing cross-validation with the boosting method. In the next video, we'll learn about classifying data with gradient boosting. Previously, we looked at performing cross-validation with the boosting method. In this video, we are going to learn how to use GBM to classify a telecom churn dataset. The algorithm of gradient boosting involves first the process of computing the deviation of residuals for each partition and then determining the best data partitioning in each stage. Next, the successive model will fit the residuals from the previous stage and build a new model to reduce the residual variance, an error. The reduction of the residual variance follows the functional gradient descent technique, in which it minimizes the residual variance by going down its derivative, as shown here. Gradient boosting ensembles weak learners and creates a new base learner that maximally correlates with the negative gradient of the loss function. One may apply this method on either regression or classification problems, and it will perform well in different datasets. We continue to use the telecom churn dataset as the input data source for the bagging method. For those who have not prepared the dataset, please refer to Section 5, Classification Tree, Lazy and Probabilistic, for detailed information. Let's perform some steps to calculate and classify data with the gradient boosting method. First, install and load the GBM package. The GBM function only uses responses ranging from 0 to 1. Therefore, you should transform yes-no responses to numeric responses 0 and 1. This is the code. Next, we use the GBM function to train a training dataset. Here, as our prediction target is the churn attribute, which is a binary outcome, we therefore set the distribution as a Bernoulli in the distribution argument. Also, we set the 1000 trees to fit in the n.tree argument. The maximum depth of the variable interaction to 7 in interaction.depth, the learning rate of the step size reduction to 0.01 in shrinkage, and the number of cross-validations to 3 in CV.folds. After the model is fitted, we can use the summary function to obtain the relative influence information of each variable in the table and figure. The relative influence shows the reduction attributable to each variable in the sum of the square error. Here we can find total day minutes is the most influential one in reducing the loss function. You can obtain the best iteration using cross-validation with this line of code. The Bernoulli deviance graph can be seen here. The gbm.perf function to find the optimum iteration. Here we estimate the optimum number with cross-validation by specifying the method argument to CV. The function further generates two plots, where the black line plots the training error and the green one plots the validation error. The error measurement here is a Bernoulli distribution, which we have defined earlier in the training stage. The blue dashed line on the plot shows where the optimum iteration is. Then, you can retrieve the odd value of the log returned from the Bernoulli loss function. You can see the output here. Then, we use the predict function to obtain the odd value of a log in each testing case returned from the Bernoulli loss function. In order to get the best prediction result, one can set the n-trees argument to an optimum iteration number. However, as the returned value is an odd value log, we still have to determine the best cutoff to determine the label. Next, you can plot the ROC curve and get the best cutoff that will have the maximum accuracy. Use this code to plot the ROC curve. This is the plot for sensitivity versus specificity. You can then retrieve the best cutoff with the coords function and use this cutoff to obtain the predicted label. Here are the threshold, specificity, and sensitivity values. Here, the if-else function is used to determine the class label from the odd value of the log. Lastly, we can use the table function to generate the classification table and see how accurate the classification model is. In addition to using the boosting function in the GBM package, one can also use the mboost package to perform classifications with the gradient boosting method. First, install and load the mboost package. The package is being installed. The mboost function only uses numeric responses. Therefore, you should transform yes-no responses to numeric responses 0, 1. Once it is done, you should remove non-numerical attributes such as voicemail plan and international plan. We can then use mboost to train the classification model. Next, use the summary function to obtain the details of the classification model. You can see the output over here. Lastly, we use the plot function to draw a partial contribution plot of each attribute. You can see the two plots here. One is for the total day minutes, and another one is for number of customer service calls. Awesome! In this video, we have learned classifying data with gradient boosting. Cool! In the next video, we'll take a look at calculating the margins of a classifier. In the last video, we looked at classifying data with gradient boosting. In this video, we are going to demonstrate how to calculate the margins of the generated classifiers. A margin is the measurement of certainty of the classification. It is computed by the support of the correct class and the maximum support of the incorrect class. The formula of margins can be formulated as: here, the margin of the Xi sample equals the support of a correctly classified sample. C denotes the correct class, minus the maximum support of a sample that is classified to class J, where J is not equal to C and J equals 1 to K. Therefore, correctly classified examples will have positive margins, and misclassified examples will have negative margins. If the margin value is close to 1, it means that correctly classified examples have a high degree of confidence. On the other hand, examples of uncertain classifications will have small margins. You need to have completed the previous video by storing a fitted bagging model in the variables churn.bagging and churn.predbagging. Also, put the fitted boosting classifier in both churn.boost and churn.boost.pred. The margins function calculates the margins of AdaBoost M1, AdaBoost SAM, or the bagging classifier, which returns a vector of a margin. To visualize the margin distribution, one can use a margin cumulative distribution graph. So, first use the margins function to calculate the margins of the boosting classifiers. Once it's done, you can then use the plot function to plot a marginal cumulative distribution graph of the boosting classifiers. This is the code you need to run. You can see the margin cumulative distribution graph. In this graph, the x-axis shows the margin and the y-axis shows the percentage of observations where the margin is less than or equal to the margin value of the x-axis. If every observation is correctly classified, the graph will show a vertical line at the margin equal to 1, where margin equals 1. You can then calculate the percentage of negative margin matches, training errors, and the percentage of negative margin matches, test errors. This is the line of code to get the training error, and this is the line of code to get testing error. So, you can see the difference. Also, you can calculate the margins of the bagging classifiers. When you run this code, you might see the warning message showing no non-missing argument to min. The message simply indicates that the min and max function is applied to the numeric of the zero-length argument. You can then use the plot function to plot a margin cumulative distribution graph of the bagging classifiers using this code. So for the margin cumulative distribution graph of the boosting classifiers, we can see that there are two lines plotted on the graph, in which the green line denotes the margin of the testing dataset and the blue line denotes the margin of the training set. The figure shows about 6.39% of negative margins match the training error, and 6.26% of negative margins match the test error. Finally, you can compute the percentage of negative margin matches training errors and the percentage of negative margin matches test errors. This is the line of code you need to run for the training dataset. And this is the line of code you need to run for the testing dataset. You can see the values here. We can find that 17.33% of negative margins match the training error, and 4.3% of negative margins match the test error in the margin cumulative distribution graph of the bagging classifiers. Normally, the percentage of negative margins matching the training error should be close to the percentage of the negative margins that match the test error. As a result of this, we should then examine the reason why the percentage of negative margins that match the training error is much higher than the negative margins that match the test error. If you are interested in more details on margin distribution graphs, please refer to the following source: Kuncheva-Lee, 2004, Combining Pattern Classifiers. Methods and Algorithms, John Wiley & Sons. Cool! That marks the end of this video. In this video, we have learned calculating the margins of a classifier. Amazing! In the next video, we'll learn about calculating the error evolution of the ensemble method. Previously, we looked at calculating the margins of a classifier. In this video, we will demonstrate how to use error evol to show the evolution of errors of each ensemble classifier. The AdaBag package provides the error evol function for a user to estimate the ensemble method errors in accordance with the number of iterations. You need to have completed the previous recipe by storing the fitted bagging model in the variable churn.bagging. Also, put the fitted boosting classifier in churn.boost. Let's perform some steps to calculate the error evolution of each ensemble learner. First, use the error evol function to calculate the error evolution of the boosting classifiers. This is the code you need to run. You can see the boosting error graph. Next, use the error evol function to calculate the error evolution of the bagging classifiers. This is the code for that. You can see the bagging error graph. The resulting graphs reveal the error rate of each iteration. The trend of the error rate can help measure how fast the errors reduce while the number of iterations increases. In addition to this, the graphs may show whether the model is overfitted. If the ensemble model is overfitted, you can use the predict.bagging and predict.boosting functions to prune the ensemble model. For more information, you can use the help function to refer to predict.bagging and predict.boosting using this command. You can see the documentation in the Help tab. Great! In this video, we have looked at calculating the error evolution of the ensemble method. Awesome! In the next video, we'll learn classifying data with random forest. In the previous video, we learned how to calculate the error evolution of the ensemble method. In this video, we will illustrate how to classify data using the random forest package. The purpose of random forest is to ensemble weak learners, for example, a single decision tree, into a strong learner. The process of developing a random forest is very similar to the bagging method, assuming that we have a training set containing n samples with m features. The process first performs bootstrap sampling, which samples n cases at random, with the replacement as the training dataset of each single decision tree. Next, in each node, the process first randomly selects m variables, where m is very small compared to m. Then finds the predictor variable that provides the best split among m variables. Next, the process grows the full tree without pruning. In the end, we can obtain the predicted result of an example from each single tree. As a result, we can get the prediction result by taking an average or weighted average for regression of an output or taking a majority vote for classification. A random forest uses two parameters, ntree the number of trees, and mtry, the number of features used to find the best feature, while the bagging method only uses ntree as a parameter. Therefore, if we set mtry equal to the number of features within a training dataset, then the random forest is equal to the bagging method. The main advantage of random forest is that it is easy to compute. It can efficiently process data and is fault-tolerant to missing or unbalanced data. The main disadvantage of random forest is that it cannot predict the value beyond the range of a training dataset. Also, it is prone to overfitting of noisy data. Random forest is another useful ensemble learning method that grows multiple decision trees during the training process. Each decision tree will output its own prediction results corresponding to the input. The forest will use the voting mechanism to select the most voted class as the prediction result. In this video, we will continue to use the Telecom Churn dataset as the input data source to perform classifications with the random forest method. Let's perform some steps to classify data with random forest. First, you have to install and load the random forest package. So it's installed and loaded. You can then fit the random forest classifier with a training set. You need to run this line of code. We set importance equals t, which will ensure that the importance of the predictor is assessed. Here you can see the output. Similar to the bagging and boosting methods, once the model is fitted, one can perform predictions using a fitted model on the testing dataset. So next, we make predictions using this line of code. Similar to other classification methods, you can obtain the classification table using table function. Here you can see the output. You can use the plot function to plot the mean square error of the forest object. This is the graph, where the tree is on x-axis and error is on y-axis. You can then examine the importance of each attribute within the fitted classifier using the importance function. You can see the output here. Next, you can use the var_imp plot function to obtain the plot of variable importance. This is the line of code you need to run. You can see the output here. From this, you can easily make out that the number of customer service calls is most essential. Similar to AddABag, which contains a method to calculate the margins of the bagging and boosting methods, Random Forest provides the margin function to calculate the margins of the forest object. So we use the margin function to calculate the margins and plot the margin cumulative distribution. Furthermore, you can use a histogram to visualize the margin distribution of the random forest. You can see the histogram here. You can also use boxplot to visualize the margins of the random forest by class. This is the boxplot. Apart from the random forest package, the party package also provides an implementation of random forest. In further steps, we illustrate how to use the cforest function within the party package to perform classifications. First, install and load the party package. Next, use the cforest function to fit the classification model. You can use this line of code. Once it's done, you can run churn.cforest to view the output. You can see the number of trees are 1,000 and number of observations are 2,315 in the output. You can make predictions based on the built model and the testing dataset. This is the line of code for prediction. Finally, obtain the classification table from the predicted labels and the labels of the testing dataset using the table function. Here is the classification table. In this video, we have learnt classifying data with Random Forest. Amazing! In the next video, we'll take a look at estimating the prediction errors of different classifiers. Hi, this is the last video of this section, estimating the prediction errors of different classifiers. In the previous video, we looked at classifying data with Random Forest. In this video, we are going to estimate the error rates of 4 different classifiers using the error_est function from the IPRED package. At the beginning of this section, we discussed why we use ensemble learning and how it can improve the prediction performance compared to using just a single classifier. We now validate whether the ensemble model performs better than a single decision tree by comparing the performance of each method. In order to compare the different classifiers, we can perform a 10-fold cross-validation on each classification method to estimate test errors using error_est from the IPRED package. In this video, we will continue to use the Telecom churn dataset as the input data source to estimate the prediction errors of the different classifiers. Let's perform some steps to estimate the prediction errors of each classification method. First, estimate the error rate of the bagging model. You can see the classification error as 0.0523. You can then estimate the error rate of the boosting method. For that, you need ADA package. I've already installed it. You may need to restart the R session. You can see the error. This is because IPRED package is not loaded. So, I'll just load IPRED and try once again. Next, estimate the error rate of the Random Forest model. The error_est function is not found. So, try loading the Random Forest library. Now we can try again. Finally, make a prediction function using churn.predict, and then use the function to estimate the error rate of the single decision tree. This is the code you need to run. You can see the misclassification error. The error_est function performs a 10-fold cross-validation on each classifier and calculates the misclassification error. The estimation results from the 4 chosen models reveal that the boosting method performs the best with the lowest error rate, and the Random Forest method has the second lowest error rate. The single decision tree classifier rpart performs the worst among the 4 methods, with an error rate equal to 0.0674, outperform a single decision tree classifier. In this video, we mentioned the ADA package, which contains a method to perform stochastic boosting. For those interested in this package, please refer to Additive Logistic Regression, a Statistical View of Boosting by Friedman et al. 2000. That's all for this video. Great! In this video, we compare the boosting, bagging, and Random Forest methods, and the single decision tree classifier. That marks the end of this section. In this section, we started off with classifying data and performing cross-validation with bagging and boosting method. We then moved on to gradient boosting, calculating margins and error evaluation of the ensemble. Finally, we looked at classifying data with Random Forest and estimating errors of different classifiers. That's amazing! In the next section, we're going to take a look at clustering. In our previous section, we got acquainted with the ensemble learning method. Welcome to the 9th section of this course, titled Clustering. In this section, we will see how to cluster data using hierarchical clustering and k-means method. We will also cut trees into clusters and draw a bivariate cluster plot. Further, we will compare clustering methods and see how to extract silhouette information from clustering. Next, we will see how to obtain the optimum number of clusters for k-means. Later, we move on to cluster data with the density-based and the model-based method. In the end, we will visualize a dissimilarity matrix and validate clusters externally. Let's get started with the first video of this section, titled Clustering Data with Hierarchical Clustering, where we will demonstrate how to cluster customers with hierarchical clustering. In this video, we will perform hierarchical clustering on customer data, which involves segmenting customers into different groups. For that, we will first download the data and examine the data structure. We will then use agglomerative hierarchical clustering to cluster data. Let's begin. Hierarchical clustering adopts either an agglomerative or divisive method to build a hierarchy of clusters. Regardless of which approach is adopted, both first use a distance similarity measure to combine or split clusters. The recursive process continues until there is only one cluster left or you cannot split more clusters. Eventually, we can use a dendrogram to represent the hierarchy of clusters. In order to perform hierarchical clustering on customer data, we will first download the data from this GitHub page. You need to right-click and download the customer.csv file, as shown here. Let's go to the R session now. We need to make sure that we place the customer data file in the working directory. Next, we need to perform a few steps in order to cluster customer data into a hierarchy of clusters. First, you need to load data from customer.csv and save it into customer. This is the line of code that we need to run. You can see the output here. All the values are loaded. You can then examine the dataset structure using str function. You can see the output here. Next, you should normalize the customer data into the same scale. This can be done using this line of code. Further, you can use agglomerative hierarchical clustering to cluster the customer data. This is the line of code to do that. This is the output. Lastly, you can use the plot function to plot the dendrogram. This is the code for it. This is how the dendrogram of hierarchical clustering looks like. Finally, we can simply use the plot function to plot the dendrogram of the hierarchical clusters. This is the code for it. You can see the dendrogram class here. We specify hang to display labels at the bottom of the dendrogram and use cex to shrink the label to 70% of the normal size. In order to compare the differences using the ward.d2 and single methods to generate a hierarchy of clusters, let's draw another dendrogram using single. Additionally, you can use the single method to perform hierarchical clustering and see how the generated dendrogram differs from the previous. This is the line of code to do that. You can see the difference between the two graphs. You can choose a different distance measure and method while performing hierarchical clustering. For more details, you can refer to the documents for dist and hclust functions. For that, you can use help command. You can use help command for hclust too. In this video, we use hclust to perform agglomerative hierarchical clustering. If you would like to perform divisive hierarchical clustering, you can use the Diana function. First, you can use Diana to perform divisive hierarchical clustering. This is the code to do that. Hierarchical clustering is a clustering technique that tries to build a hierarchy of clusters iteratively. Generally, there are two approaches to build hierarchical clusters. Number 1. Agglomerative hierarchical clustering. This is a bottom-up approach. Each observation starts in its own cluster. We can then compute the similarity, or the distance, between each cluster and then merge the two most similar ones at each iteration, until there is only one cluster left. Number 2. Divisive hierarchical clustering. This is a top-down approach. All observations start in one cluster, and then we split the cluster into two least dissimilar clusters recursively, until there is one cluster for each observation, as shown here. Before performing hierarchical clustering, we need to determine how similar the two clusters are. Here, we list some common distance functions used for the measurement of similarity. Number 1. Single linkage. This refers to the shortest distance between 2 points in each cluster. Number 2. Complete linkage. This refers to the longest distance between the 2 points in each cluster. Number 3. Average linkage. This refers to the average distance between 2 points in each cluster, where Ci is the size of cluster Ci and Cj is the size of cluster Cj. Number 4. Ward method. This refers to the sum of the squared distance from each point to the mean of the merged clusters. Next, we will see how to use hclust to perform agglomerative hierarchical clustering. If you would like to perform divisive hierarchical clustering, you can use the Diana function. First, you can use Diana to perform divisive hierarchical clustering. This is the code to load the library, and this is the code to load the Diana function. Then, you can use summary function to obtain the summary information. This is the code to do that. You can see the summary information here. Lastly, you can plot a dendrogram and banner with the plot function. This is the code to plot the graph. It will ask you to write the return statement. You can do that and press Enter. If you are interested in drawing a horizontal dendrogram, you can use the dendextend package. Use the following procedure to generate a horizontal dendrogram. First, install and load the dendextend and magrittr packages. If your R version is 3.1 and above, you do not have to install and load the magrittr package. You can see the package is being installed. So the dendextend package is getting loaded. Magrittr package is loaded here. Next, let's set up the dendrogram. Finally, plot the horizontal dendrogram shown here. Great! So in this video, we saw how to cluster data with hierarchical clustering. In our next video, we will see how to cut trees into cluster. In the previous video, we saw how to cluster data with hierarchical clustering. Welcome to the second video of the 9th section, titled Cutting Trees into Clusters. In this video, we will see how to categorize data and examine cluster labels for it. We then count the number of data within each cluster and then visualize how data is clustered. In a dendrogram, we can see the hierarchy of clusters, but we have not grouped data into different clusters yet. However, we can determine how many clusters are within the dendrogram and cut the dendrogram at a certain tree height to separate the data into different groups. In this video, we demonstrate how to use the cut tree function to separate the data into a given number of clusters. In order to perform the cut tree function, you need to have the previous video completed by generating the hclust object, hc, which you can see here. We need to perform a few steps to cut the hierarchy of clusters into a given number of clusters. First, categorize the data into 4 groups using this code. You can then examine the cluster labels for the data using this code. You can see the output here after running the code. Now let's count the number of data within each cluster using the table function to count the number of data within each cluster. You can see the output. We find that most of the data is in cluster 4. Finally, you can visualize how data is clustered with the red rectangle border. We draw red rectangles around the clusters to show how data is categorized into the 4 clusters with the rect.hclust function. This is the line of code for it. You can see the output here. There are 4 clusters and the 4th is the biggest one. We can determine the number of clusters from the dendrogram in this figure. Besides drawing rectangles around all hierarchical clusters, you can place a red rectangle around a certain cluster. To do that, this is the code. You can see that the rectangle is drawn in the second cluster, as mentioned in the which command. Also, you can color clusters in different colors, with a red rectangle around the clusters by using the dendextend package. You have to complete the instructions outlined in the previous video and perform the steps, which are: color the branch according to the cluster it belongs to. This is the code to do that. You can see the color of the branch has changed here in the horizontal dendrogram. You can then add a red rectangle around the clusters. This is the code for that. You can see the rectangles here. Finally, you can add a line to show the tree cutting location. You can see the line here. This is the output for it. Wow! So we saw how to successfully cut trees into clusters. In our next video, we will see how to cluster data with the k-means method. In our previous video, we saw how to cut trees into clusters. Here we are at the third video, clustering data with the k-means method. In this video, we use k-means to cluster the data. We will inspect the center of each cluster. Then, we will draw a scatter plot of data to color the points. K-means clustering is a flat clustering technique, which produces only one partition with k clusters. Unlike hierarchical clustering, which does not require a user to determine the number of clusters at the beginning, the k-means method requires this to be determined first. However, k-means clustering is much faster than hierarchical clustering, as the construction of a hierarchical tree is very time-consuming. In this video, we will demonstrate how to perform k-means clustering on the customer dataset. Here we will continue to use the customer dataset as the input data source to perform k-means clustering. Perform the following steps to cluster the customer dataset with the k-means method. First, you can use k-means to cluster the customer data. You can then inspect the center of each cluster using bar plot. Lastly, you can draw a scatter plot of the data and color the points according to the clusters. K-means clustering is a method of partitioning clustering. The goal of the algorithm is to partition n objects into k clusters, where each object belongs to the cluster with the nearest mean. The objective of the algorithm is to minimize the within-cluster sum of squares, WCSS. Assuming X is a given set of observations, S equal to S1, S2 to Sk denotes k partitions and mu I is the mean of Si, then we can formulate the WCSS function as follows. The process of k-means clustering can be illustrated by the following 5 steps. Number 1. Specify the number of k clusters. Number 2. Randomly create k partitions. Number 3. Calculate the center of the partitions. Number 4. Associate objects closest to the cluster center. Number 5. Repeat steps 2, 3, and 4 until the WCSS changes very little or is minimized. In this video, we demonstrate how to use k-means clustering to cluster customer data. In contrast to hierarchical clustering, k-means clustering requires the user to input the number of k. In this example, we use k equals 4. Then, the output of a fitted model shows the size of each cluster, the cluster means of 4 generated clusters, the cluster vectors with regard to each data point, the within-cluster sum of squares by the clusters, and other available components. Further, you can draw the centers of each cluster in a bar plot, which will provide more details on how each attribute affects the clustering. Lastly, we plot the data point in a scatter plot and use the fitted cluster labels to assign colors with regard to the cluster label. In k-means clustering, you can specify the algorithm used to perform clustering analysis. You can specify either Hartigan-Wong, Lloyd, Forgy, or McQueen as the clustering algorithm. For more details, please use the help function to refer to the document for the k-means function. Great! So in this video, we saw how to cluster data using k-mean method. In our next video, we will see how to draw a bivariate cluster plot. In our previous video, we clustered data with the help of the k-means method. This is the fourth video of the section titled Drawing a Bivariate Cluster Plot. In this video, we will see how to install and load the cluster package. We will then draw a bivariate cluster plot. In the previous video, we employed the k-means method to fit data into clusters. However, if there are more than 2 variables, it is impossible to display how data is clustered in 2 dimensions. Therefore, you can use a bivariate cluster plot to first reduce the variables into 2 components and then use components such as axis and circle as clusters to show how data is clustered. In this video, we will illustrate how to create a bivariate cluster plot. We will continue to use the customer dataset as the input data source to draw a bivariate cluster plot. Let's perform some steps to draw a bivariate cluster plot. We will now install and load the cluster package. This is the code to do that. You can see the cluster package is being installed here. Let's load the package now. You can try it. Once again. Then you can draw a bivariate cluster plot using this code. In the clustplot function, we can set shade to true and color to true to display a cluster with colors and shades. As per this figure, we found that the bivariate uses 2 components, which explains 85.01% of point variability, as the x-axis and y-axis. The data points are then scattered on the plot in accordance with component 1 and component 2. Data within the same cluster is circled in the same color and shade. You can also zoom into the bivariate cluster plot using this code. Besides drawing the 4 clusters in a single plot, you can use rect to add a rectangle around the specific area within a given x-axis and y-axis range. You can then zoom into the plot to examine the data within each cluster by using xlim and ylim in the clustplot function. The clustplot function uses princomp and cmd-scale to reduce the original feature dimension to the principal component. Therefore, one can see how data is clustered in a single plot with these 2 components as the x-axis and y-axis. To learn more about princomp and cmd-scale, one can use the help function to view related documents. This is the line of code for that. Here you can learn more about cmd-scale, and with this we can study principal components analysis. For those interested in how to use cmd-scale to reduce the dimensions, you can perform the following steps, like these. You can see the plot here. This is the scatter plot of the data with regard to the scale dimension. Nice! We saw how to draw a bivariate cluster plot. In our next video, we will compare the clustering methods. In our previous video, we saw how to draw a bivariate cluster plot. Welcome to the fifth video, Comparing Clustering Methods. In this video, we will first install and load the FPC package. Then we will use different clustering methods and generate cluster statistics for them in order to compare. After fitting data into clusters using different clustering methods, you may wish to measure the accuracy of the clustering. In most cases, you can use either intra-cluster or intercluster metrics as measurements. We now introduce how to compare different clustering methods using cluster.stat from the FPC package. In order to perform a clustering method comparison, one needs to have the previous video completed by generating the customer dataset. Let's perform some steps to compare clustering methods. First, install and load the FPC package using this code. You can see the FPC getting installed and loaded. You then need to use hierarchical clustering with the single method to cluster customer data and generate the object HCSingle. This is the code you need to run for that. Use hierarchical clustering with the complete method to cluster customer data and generate the object HCComplete. This is the line of code you need to run. You can then use k-means clustering to cluster customer data and generate the object km. Next, retrieve the cluster validation statistics of either clustering method. Use this code for that. Most often, we focus on using within.cluster.ss and avg silwidth to validate the clustering method. Here is the code for it. You can see the output here. From the output, the within.cluster.ss measurement stands for the within cluster's sum of squares, and avg.silwidth represents the average silhouette width. The within.cluster.ss measurement shows how closely related objects are in clusters. The smaller the value, the more closely related objects are within the cluster. On the other hand, a silhouette is a measurement that considers how closely related objects are within the cluster and how clusters are separated from each other. Finally, we can generate the cluster statistic of each clustering method and list them in a table. This is the code for that. You can see the output here. Here, the summary table generated in the last step shows that the complete hierarchical clustering method outperforms a single hierarchical clustering method and k-means clustering in within.clusters.ss and avg.silwidth. Mathematically, we can define the silhouette width for each point x as follows. In the preceding equation, ax is the average distance between x and all other points within the cluster, and bx is the minimum of the average distances between x and the points in the other clusters. The silhouette value usually ranges from 0 to 1. A value closer to 1 suggests the data is better clustered. The k-means function also outputs statistics, for example, within SS and between SS, for users to validate a clustering method. This is the code for that. We can see the output here. You can also measure the between SS. This is the value for that. Wonderful. So we compared the clustering methods in this video. In our next video, we will extract silhouette information from clustering. In our previous video, we compared the clustering methods. This is the sixth video, extracting silhouette information from clustering. In this video, we will first generate a k-means object. We will then compute and plot the silhouette information. Silhouette information is a measurement to validate a cluster of data. In the previous video, we mentioned that the measurement of a cluster involves the calculation of how closely the data is clustered within each cluster and measures how far different clusters are apart from each other. The silhouette coefficient combines the measurements of the intracluster and intercluster distance. The output value typically ranges from 0 to 1. The closer to 1, the better the cluster is. In this video, we will introduce how to compute silhouette information. In order to extract the silhouette information from a cluster, you need to have the previous video completed by generating the customer dataset. Let's perform the following steps to compute the silhouette information. First, let's use k-means to generate a k-means object, km. This is the line of code you need to run. You can then compute the silhouette information. Here is the code for it. You can see the output here. As you can see, we have retrieved the silhouette information, which shows cluster sizes, the average silhouette widths, and individual silhouette widths. The silhouette coefficient is a value ranging from 0 to 1. The closer to 1, the better quality of the cluster. Next, you can plot the silhouette information using plot function, as shown here. The left-hand side of the plot shows the number of horizontal lines, which represents the number of clusters. The right-hand column shows the mean similarity of the plot of its own cluster minus the mean similarity of the next similar cluster. The average silhouette width is presented at the bottom of the plot. For those interested in how silhouettes are computed, please refer to the Wikipedia entry for the silhouette value at this link. Brilliant! We explored silhouette information from clustering in this video. In our next video, we will see how to obtain the optimum number of clusters for k-means. In our previous video, we saw how to extract silhouette information from clustering. Welcome to the 7th video, obtaining the optimum number of clusters for k-means. In this video, we demonstrate how to find the optimum number of clusters by iteratively getting within the sum of squares and the average silhouette value. While k-means clustering is fast and easy to use, it requires k to be the input at the beginning. Therefore, we can use the sum of squares to determine which k value is best for finding the optimum number of clusters for k-means. In this video, we will discuss how to find the optimum number of clusters for the k-means clustering method. In order to find the optimum number of clusters, you need to have the previous video completed by generating the customer dataset. Now let's perform some steps to find the optimum number of clusters for the k-means clustering. First, calculate the within sum of squares, within SS, of different numbers of clusters. This is the code you will need to use for that. You can see the output here. From this output, the lower values represent clusters with better quality. You can then use a line plot to plot the within sum of squares with a different number of k. This is the code for it. By plotting the within sum of squares in regard to different number of k, we find that the elbow of the plot is at k equals 4. Next, you can calculate the average silhouette width, avg.silwidth, of different numbers of clusters. This is the code for it. You can see the output here. You can then use a line plot to plot the average silhouette width with a different number of k. This is the code you will need to run. You can see the graph here. This graph shows the maximum average silhouette width appears at k equals 4. Lastly, we use which.max to obtain the value of k to determine the location of the maximum average silhouette width. Retrieve the maximum number of clusters using this code. For those interested in how the within sum of squares is computed, please refer to the Wikipedia entry of k-means clustering at this link. Nice! We obtained the optimum number of clusters for k-means. In our next video, we will cluster data with the density-based method. In the previous video, we saw how to obtain the optimum number of clusters for k-means. This is the 8th video, which will focus on clustering data with the density-based method. In this video, we demonstrate how to use the dbScan density-based method to cluster customer data. As an alternative to distance measurement, you can use a density-based measurement to cluster data. This method finds an area with a higher density than the remaining area. One of the most famous methods is dbScan. In this video, we will demonstrate how to use dbScan to perform density-based clustering. Here we will use simulated data generated from the MLBench package. Let's perform the following steps to perform density-based clustering. First, you need to install and load the FPC and MLBench packages. This is the code for MLBench. Next, here is the code for the FPC package. So this is loaded now. You can then use the MLBench library to draw a Cassini problem graph. This is the code for it. Oops, there is an error. Now let's try to load the MLBench package again. So we have successfully loaded it now. Let's plot the graph now. This is the graph which is plotted. This is the Cassini problem graph. Next, you can cluster data with regard to its density measurement. This is the line of code to do that. You can see the output here. We specify the reachability distance as 0.2, the minimum reachability number of points to 2, the progress reporting as null, and use distance as a measurement. The clustering method successfully clusters data into 3 clusters with sizes of 200, 200, and 100. Now let's plot the data in a scatter plot with different cluster labels as the color. By plotting the points and cluster labels on the plot, we see that 3 sections of the Cassini graph are separated in different colors. You can also use dbScan to predict which cluster the data point belongs to. In this example, first make 3 inputs in the matrix P, as you can see here. This is the code for it. This is the output. The FPC package also provides a predict function, and you can use this to predict the cluster labels of the input matrix. You can then predict which cluster the data belongs to using this code. This is the output you get after running the code. Point C, 0, 0, is classified into cluster 3. Point C, 0, 1, 5 is classified into cluster 1. And point C, 1, 1 is classified into cluster 2. Density-based clustering uses the idea of density reachability and density connectivity, which makes it very useful in discovering a cluster in nonlinear shapes. Before discussing the process of density-based clustering, some important background concepts must be explained. Density-based clustering takes 2 parameters into account: EPS and min-PTS. EPS stands for the maximum radius of the neighborhood. Min-PTS denotes the minimum number of points within the EPS neighborhood. With these 2 parameters, we can define the core point as having points more than min-PTS within EPS. Also, we can define the board point as having points less than min-PTS, but is in the neighborhood of the core points. Then we can define the core object as if the number of points in the EPS neighborhood of P is more than min-PTS. Furthermore, we have to define the reachability between 2 points. We can say that a point P is directly density reachable from another point Q, if Q is within the EPS neighborhood of P, and P is a core object. Then we can define that a point P is generic and density reachable from the point Q, if there exists a chain of points P1, P2 to Pn, where P1 equals Q, Pn equals P, and Pi plus 1 is directly density reachable from Pi with regard to EPS and min-PTS for 1 is less than equals I is less than equals N. With the preliminary concept of density-based clustering, we can then illustrate the process of DB-scan, the most popular density-based clustering, as shown in these steps. Number 1. Randomly select a point P. Number 2. Retrieve all the points that are density reachable from P with regard to EPS and min-PTS. Number 3. If P is a core point, then a cluster is formed. Otherwise, if it is a board point and no points are density reachable from P, the process will mark the point as noise and continue visiting the next point. Number 4. Repeat the process until all points have been visited. The FPC package contains flexible procedures of clustering and has useful clustering analysis functions. For example, you can generate a discriminant projection plot using the plot cluster function. For more information, you can make use of the help function as shown. You can see the documentation here. Great! So this video showed us how to cluster data with the density-based method. In our next video, we will see how to cluster data using the model-based method. In our previous video, we saw how to cluster data with the density-based model, clustering data with the model-based method. In this video, we demonstrate how to use model-based clustering to cluster data. In contrast to hierarchical clustering and k-means clustering, which uses a heuristic approach and do not depend on a formal model, model-based clustering techniques assume varieties of data models and apply an EM algorithm to obtain the most likely model and further use the model to infer the most likely number of clusters. In this video, we will demonstrate how to use the model-based method to determine the most likely number of clusters. In order to perform a model-based method to cluster customer data, you need to have the previous video completed by generating the customer dataset. Perform some steps for model-based clustering. First, please install and load the library mclust. This is the code for it. Let's load the library. Try it once again if the error occurs. You can then perform model-based clustering on the customer dataset. This is the code for that. You can see here there are 4 different plots. We can press 1 for BIC, 2 for classification, 3 for uncertainty, and 4 for density. Here, you can first press 1 to obtain the BIC against the number of components. You can see a BIC plot here. The BIC plot shows the BIC value, and one can use this value to choose the number of clusters. Then you can press 2 to show the classification with regard to different combinations of features. The classification plot shows how data is clustered in regard to different dimension combinations. Press 3 to show the classification uncertainty with regard to different combinations of features. The uncertainty plot shows the uncertainty of classifications in regard to different dimension combinations. Next, press 4 to plot the density estimation. The density plot shows the density estimation in the contour. Then you can press 0 to plot density to exit the plotting menu. Lastly, use the summary function to obtain the most likely model and number of clusters. You can see the output here. The most possible number of clusters is 5, with a BIC value equal to minus 556.1142. Instead of taking a heuristic approach to build a cluster, model-based clustering uses a probability-based approach. Model-based clustering assumes that the data is generated by an underlying probability distribution and tries to recover the distribution from the data. One common model-based approach is using finite mixture models, which provide a flexible modeling framework for the analysis of the probability distribution. finite mixture models are linearly weighted sum of component probability distribution. Assume the data y equals y1, y2 to yn contains n independent and multivariable observations. G is the number of components. The likelihood of finite mixture models can be formulated as this. The process of model-based clustering has several steps. First, the process selects the number and types of component probability distribution. Then, it fits a finite mixture model and calculates the posterior probabilities of a component membership. Lastly, it assigns the membership of each observation to the component with the maximum probability. For those interested in detail on how mClust works, please refer to these sources. Awesome! So we have clustered the data with model-based method. The next video will help us visualize a dissimilarity matrix. In our previous video, we clustered data with the model-based method. Here we are at the 10th video, visualizing a dissimilarity matrix. In this video, we use a dissimilarity plot to visualize the dissimilarity matrix. We first install and load the package seriation, and then apply the displot function on the k-means clustering output. A dissimilarity matrix can be used as a measurement for the quality of a cluster. To visualize the matrix, we can use a heat map on a distance matrix. Within the plot, entries with low dissimilarity or high similarity are plotted darker, which is helpful to identify hidden structures in the data. In this video, we will discuss some techniques that are useful to visualize a dissimilarity matrix. In order to visualize the dissimilarity matrix, you need to have the previous recipe completed by generating the customer dataset. In addition to this, a k-means object needs to be generated and stored in the variable km. Let's perform some steps to visualize the dissimilarity matrix. First, install and load the seriation package. This is the code for it. You can see that it has been installed and loaded. You can then use displot to visualize the dissimilarity matrix in a heat map. This is the code to generate the plot. You can see the plot here. It shows that clusters similar to each other are plotted darker, and dissimilar combinations are plotted lighter. Therefore, we can see clusters against their corresponding clusters, such as cluster 4 to cluster 4, are plotted diagonally and darker. On the other hand, clusters dissimilar to each other are plotted lighter and away from the diagonal. Next, apply displot on hierarchical clustering in the heat map. This is the code to do that. This generated plot shows the similarity of each cluster in a single heat map. Besides using displot to visualize the dissimilarity matrix, one can also visualize a distance matrix by using the dist and image functions. In the resulting graph, closely related entries are plotted in red. Less related entries are plotted closer to white. This is the code for it. You can see the image here. In order to plot both a dendrogram and heat map to show how data is clustered, you can use the heat map function. For that, you need to run this code. You can see the graph here, where you can see the dendrogram and heat map on the same graph. Wow! We just saw how to visualize a dissimilarity matrix. In our final video, we will see how to validate clusters externally. In our previous video, we saw how to visualize a dissimilarity matrix. This is the final video of this section, validating clusters externally. In this video, we demonstrate how different clustering methods work in regard to a handwriting dataset. The aim of the clustering is to separate 1 and 7 into different clusters. we perform different techniques to see how data is clustered in regard to the k-means and dbScan methods. Besides generating statistics to validate the quality of the generated clusters, you can use known data clusters as the ground truth to compare different clustering methods. In this video, we will demonstrate how clustering methods differ with regard to data with known clusters. In this video, we will continue to use handwriting digits as clustering inputs. You can find the figure on the author's GitHub page shown here. Here you can find the handwriting.png image, which you can download and save in the working directory. Now let's perform some steps to cluster digits with different clustering techniques. For that, let's open the RStudio. First, you need to install and load the package PNG as shown. You can see it is installed and loaded. Then please read images from handwriting.png and transform the read data into a scatterplot. This is the code for that. You can see the image here. To generate the data, we use the Windows application paint.exe to create a PNG file with dimensions of 28 by 28 pixels. We then read the PNG data using the readPNG function and transform the readPNG data points into a scatterplot, which shows the handwriting digits in 17, as you can see here. Perform a k-means clustering method on the handwriting digits using this code. Run the code and you can see the change in the plot. Next, we perform k-means clustering, where k equals 2 on the dataset. Since k-means clustering employs distance measures, the constructed clusters cover the area of both the 1 and 7 digits. Next, perform the dbScan clustering method on the handwriting digits. Use this code for doing that. You can see the output here. Let's plot the dbScan using this plot function. You can see the plot here. We can then perform dbScan on the dataset. As dbScan is a density-based clustering technique, it successfully separates digit 1 and digit 7 into different clusters. If you are interested in how to read various graphic formats in R, you may refer to the document of help. Here you will find the documentation for readPNG and writePNG. You can learn about it here. Great! So in this video, we covered how to validate clusters externally. With this, we come to the end of this section. In this section, we saw how to cluster data with hierarchical clustering, k-means method, density-based and model-based method. Besides that, we also covered topics such as cutting a tree into clusters, drawing a bivariate cluster plot, and comparing clustering methods. Further, we saw how to extract silhouette information from clustering and obtaining optimum clusters for k-means. Finally, we saw how to visualize a dissimilarity matrix and how to validate clusters externally. In the next section, we will cover association analysis and sequence mining. Hi, and welcome to Section 10, Association Analysis and Sequence Mining. In this section, we will cover tasks to create and inspect transaction datasets, performing association analysis with an a priori algorithm, visualizing associations in various graph formats, and finding frequent item sets using the ECLAT algorithm. Lastly, we will create transactions with temporal information and use the C-SPADE algorithm to discover frequent sequential patterns. Now we move on to the first video of this section that deals with transforming data into transactions. In this video, we will introduce how to transform either a list, matrix, or data frame into transactions. Before creating a mining association rule, we need to transform the data into transactions. In this video, we will generate 3 different datasets in a list, matrix, or data frame. We can then transform the generated dataset into transactions. Let's perform some steps to transform different formats of data into transactions. First, install and load the package arule. You can see that the arule package has been installed. Then try and load the package. Next, we generate the dataset in a list format, containing 3 vectors of purchase records. This is the line of code to do that. Here you can see a tr list is created of type list. Then, use the as function to transform the data frame into transactions. Here is the output. You can also transform the matrix format data into transactions using this code. To denote how items are purchased, one should use a binary incidence matrix to record the purchase behavior of each transaction with regard to different items purchased. Likewise, we can use an as function to transform the dataset from the matrix format into transactions. You can see there are 3 transactions and 4 iterations. Lastly, you can transform the data frame format datasets into transactions. This is the code we'll need to run. You can see that the TRDF is created and is changed into transaction. Here, the data frame contains 2 factor type vectors. One is a transaction ID named TRID, while the other shows purchased items named in item with regard to different transactions. We've again used the as function to transform the data frame format data into transactions. The transactions class is used to represent transaction data for rules or frequent pattern mining. It is an extension of the item matrix class. If you are interested in how to use the 2 different classes to represent transaction data, please use the help function to refer to these documents. You can see the documentation for transactions and item matrix. Cool, isn't it? In this video, we have learned transforming data into transactions. Awesome! In the next video, we'll take a look at displaying transactions and associations. In the previous video, we looked at transforming data into transactions. In this video, we will illustrate how to display transactions and association rules via various functions in the arule package. The arule package uses its own transaction class to store transaction data. As such, we must use the generic function provided by arule to display transactions and association rules. Ensure that you have completed the previous video by generating transactions and storing these in the variable trans. Let's start with displaying transactions and associations. First, obtain a list representation of the transaction data within the list function. You can see the output here. Next, use the summary function to show a summary of the statistics and details of the transactions. Here is the output where you can see the detailed information. You can then display transactions using the inspect function. You can see the output here, the items and their transaction ID. In addition to this, you can filter the transactions by size. This is the line of code you need to run and then inspect the element. So you can see the output here. Also, you can use the image function to visually inspect the transactions. We can see the image here. To visually show the frequency support bar plot, one can use item frequency plot. This is the plots here. You can see relative item frequency of each item. Besides using item frequency plot to show the frequency bar plot, you can use the item frequency function to show the support distribution. For more details, please use the help function. Great! In this video, we have looked at displaying transactions and associations. Splendid! In the next video, we'll learn mining associations with the a priori rule. In the previous video, we looked at displaying transactions and associations. In this video, we will introduce how to perform association analysis using the a priori rule. Association mining is a technique that can discover interesting relationships hidden in transaction datasets. This approach first finds all frequent item sets and generates strong association rules from frequent item sets. A priori is the most well-known association mining algorithm, which identifies frequent individual items first and then performs a breadth-first search strategy to extend individual items to larger item sets until larger frequent item sets cannot be found. The purpose of association mining is to discover associations among items from the transactional database. Typically, the process of association mining proceeds by finding item sets that have the support greater than the minimum support. Next, the process uses the frequent item sets to generate strong rules. For example, milk is more than or equal to bread. A customer who buys milk is likely to buy bread, that have the confidence greater than the minimum confidence. By definition, an association rule can be expressed in the form of X is more than or equal to Y, where X and Y are disjointed item sets. We can measure the strength of association between the two terms, support and confidence. Support shows how much of the percentage of a rule is applicable within a dataset, while confidence indicates the probability of both X and Y appearing in the same transaction. As support and confidence are metrics for the strength rule only, you might still obtain many redundant rules within a high support and confidence. Therefore, we can use the third measure, lift, to evaluate the quality, ranking, of the rule. By definition, lift indicates the strength of a rule over the random co-occurrence of X and Y. So we can formulate lift in the following form. A priori is the best-known algorithm for mining associations, which performs a level-wise breadth-first algorithm to count the candidate item sets. The process of a priori starts by finding frequent item sets, a set of items that have minimum support, level-wisely. For example, the process starts with finding frequent one-item sets. Then the process continues by using frequent one-item sets to find frequent two-item sets. The process iteratively discovers new frequent k+1 item sets from frequent k item sets until no frequent item sets are found. Finally, the process utilizes frequent item sets to generate association rules. In this video, we will use the built-in transaction dataset, groceries, to demonstrate how to perform association analysis with the a priori algorithm in the A-Rules package. Make sure that the A-Rules package is installed and loaded first. Let's perform some steps to analyze the association rules. First, you need to load the groceries dataset. The groceries dataset contains 1 month of real-world point-of-sale transaction data from a typical grocery outlet. You can then examine the summary of the groceries dataset using the summary function. This is the output. The summary statistics shows that the dataset contains 9,835 transactions, which are categorized into 169 categories. In addition to this, the summary shows information such as most frequent items, item set length distribution, and example extended item information within the dataset. Next, you can use item frequency plot to examine the relative item frequency of item sets. This is the line of code you'll have to use. The graph can be seen here. It shows the 5 most frequent items with support over 0.1. Let's use a priori to discover rules within the support over 0.001 and confidence over 0.5. From the output summary, we find the a priori algorithm generates 5,668 rules with support over 0.001 and confidence over 0.5. Further, we can find the rule length distribution, summary of quality measures, and mining information. In the summary of the quality measurement, we find descriptive statistics of 3 measurements, which are support, confidence, and lift. Support is the proportion of transactions containing a certain item set. Confidence is the correctness percentage of the rule. Lift is the response target association rule, divided by the average response. We then inspect the first few rules. You can see the output here. You can sort rules by confidence and inspect the first few rules by using this line of code. That's the output. Here we have used the inspect function to view the first 6 rules of the 5,668 generated rules. We can sort rules by confidence and list rules with the most confidence. Therefore, we find that rich sugar associated to whole milk is the most confident rule, with the support equal to 0.0012220132, confidence equal to 1, and lift equal to 3.913649. For those interested in the research results using the groceries dataset and how the support, confidence, and lift measurement are defined, you can refer to papers by Michael Hassler, Kurt Hornick, and Thomas Reuterer, 2006, Implications of Probabilistic Data Modeling for Mining Association Rules, and in M. Spiliopoulou, R. Cruz, C. Borgelt, A. Neurenberger, and W. Gall, editors, From Data and Information Analysis to Knowledge Engineering Studies and Classification, Data Analysis, and Knowledge Organization. Also, in addition to using the summary and inspect functions to inspect association rules, you can use interest measure to obtain additional interest measures. This is the code you can use. That's the output where all details can be seen. Awesome! In this video, we have learned mining associations with the a priori rule. Cool! In the next video, we'll take a look at pruning redundant rules. In the previous video, we looked at mining associations with the a priori rule. In this video, we will take a look at how to prune or remove repeated or redundant rules. The two main constraints of association mining are to choose between the support and confidence. For example, if you use a high support threshold, you might remove rare item rules without considering whether these rules have a high confidence value. On the other hand, if you choose to use a low support threshold, the association mining can produce huge sets of redundant association rules, which makes these rules difficult to utilize and analyze. Therefore, we need to prune redundant rules so we can discover meaningful information from these generated rules. For this video, you have to complete the previous video by generating rules and have it stored in the variable rules. Let's get started then. Follow these steps to find redundant rules. First, run this code. Here we search for redundant rules. We sort the rules by a lift measure and then find subsets of the sorted rules using the is.subset function, which will generate an item matrix object. We can then set the lower triangle of the matrix to NA. Lastly, we compute col sums of the generated matrix, of which col sums is greater than or equal to 1, indicates that the specific rule is redundant. You can then remove redundant rules and inspect them using these lines of code. This is the output. In order to find subsets or supersets of rules, you can use the is.superset and is.subset functions on the association rules. These two methods may generate an item matrix object to show which rule is the superset or subset of other rules. You can refer to the help function for more information. You can see the documentation for is.superset and is.subset. In this video, we have learned pruning redundant rules. In the next video, we'll take a look at visualizing association rules. In the previous video, we learned pruning redundant rules. In this video, we will introduce how to use the arule-viz package to visualize the association rules. Besides listing rules as text, you can visualize association rules using arules-viz, which makes it easier to find the relationship between item sets. In this video, we will continue using the groceries dataset. To get started, you need to have completed the previous video by generating the pruned rule, rules.pruned. Let's perform some steps to visualize the association rule. First, you need to install and load the package arulesviz. You can see the arulesviz package is being installed. Let's load it using library function. Next, make a scatter plot from the pruned rules generated in the previous video. So we find the rules are shown as points within the scatter plot, with the x-axis in support and y-axis in confidence. The shade of color shows the lift of the rule. The darker the shade, the higher the lift. Additionally, to prevent overplotting, you can add jitter to the scatter plot. This is the line of code to add jitter. You can see the output here. We then produce new rules with soda on the left-hand side using the a priori algorithm. This is the line of code you need to run. You can see the output here. It shows the parameter specification, algorithmic control, absolute minimum support count, and other information about the datasets. Next, plot soda rule in a graph plot. You can see the output where graph for 18 rules is displayed. Instead of printing all the rules on a single plot, we choose to produce new rules with soda on the left-hand side. We then sort the rules by using the lift and visualize the rules in the graph. From the graph, every item set is presented in a vertex, and their relationship is presented in an edge. The figure shows it is clear that the rule with soda on the left-hand side to whole milk on the right-hand side has the maximum support, for the size of the node is greatest. Also, the rule shows that soda on the left-hand side to bottled water on the right-hand side has the maximum lift, as the shade of color in the circle is the darkest. Also, the association rules can be visualized in a balloon plot using this line of code. You can see the balloon plot here. We are using the same data with soda on the left-hand side to generate a grouped matrix, which is a balloon plot with the left-hand side rule as column labels and the right-hand side as row labels. In the graph, the size of the balloon shows the support of the rule, and the color of the balloon shows the lift of the rule. Here we have introduced 3 visualization methods to plot association rules. However, arulesviz also provides features to plot parallel coordinate plots, double-decker plots, mosaic plots, and other related charts. For those who are interested in how these plots work, you may refer to Visualizing Association Rules, Introduction to the R extension package arulesviz, R project module by Hassler M. and Chelaboyner S. 2011. In addition to generating a static plot, you can generate an interactive plot by setting interactive equal to true through these steps. This is the line of code you need to run. This is the scatter plot. You can see that the plot is interactive and it asks for selecting a region with 2 clicks. We can click on a certain point and then on Inspect, and it will display information related to that point. This is an interactive plot, and you can create it by setting interactive equals to true. You can also click on some other spot and then click Filter. That will give you a filtered plot. With zoom in and zoom out, you can zoom into and out of the plot, and you can click on End to end the rule. Cool. In this video, we have looked at visualizing association rules. Amazing! In the next video, we'll learn about mining frequent item sets with ECLAT. In the previous video, we looked at visualizing association rules. In this video, we are going to introduce how to use the ECLAT algorithm to generate frequent item sets. In addition to the a priori algorithm, you can use the ECLAT algorithm to generate frequent item sets. As the a priori algorithm performs a breadth-first search to scan the complete database, the support counting is rather time-consuming. Alternatively, if the database fits into the memory, you can use ECLAT algorithm, which performs a depth-first search to count the supports. The ECLAT algorithm, therefore, performs quicker than the a priori algorithm. Although a priori is a straightforward and easy-to-understand association mining method, the algorithm has the disadvantage of generating huge candidate sets and performs inefficiently in support counting, for it takes multiple scans of databases. In contrast to a priori, ECLAT uses equivalence classes, depth-first searches, and set intersections, which greatly improves the speed in support counting. In a priori, the algorithm uses a horizontal data layout to store transactions. On the other hand, ECLAT uses a vertical data layout to store a list of transaction IDs, TID, for each item. Then ECLAT determines the support of any k+1 item set by intersecting TID lists of two k item sets. Lastly, ECLAT utilizes frequent item sets to generate association rules. In this video, we will continue using the dataset groceries as our input data source. Let's start generating a frequent item set using the ECLAT algorithm. Similar to the a priori method, we can use the ECLAT function to generate the frequent item set. This is the line of code you need to run. You can see the output here. Next, we obtain the summary information from the generated frequent item set. Here we obtain summary statistics, which include most frequent items, item set length distributions, summary of quality measures, and mining information. Lastly, we examined the top 10 support frequent item sets using the inspect function. You can see the output here. The whole milk has the maximum support of around 0.255. Besides a priori and ECLAT, another popular association mining algorithm is FP growth. Similar to ECLAT, this takes a depth-first search to count supports. However, there is no existing R package that you can download from CRAN that contains this algorithm. However, if you are interested in knowing how to apply the FP growth algorithm in your transaction dataset, you can refer to Christian Borgelt's page at borgelt.net for more information. Awesome! In this video, we have learned mining frequent item sets with ECLAT. Amazing! In the next video, we'll be creating transactions with temporal information. In the previous video, we looked at mining frequent item sets with ECLAT. In this video, we demonstrate how to create transactions with temporal information. In addition to mining interesting associations within the transaction database, we can mine interesting sequential patterns using transactions with temporal information. In this video, we will generate transactions with temporal information. We can use the generated transactions as the input source for frequent sequential pattern mining. Let's perform some steps to create transactions with temporal information. First, install and load the package arules sequences. This might take a while. You can see that the package is loaded. Now we'll create a list with purchasing records. So, create a list of transactions and assign a transaction ID for each transaction. You can then turn the list into transactions and add event ID and sequence ID as temporal information using this code. After generating transactions with temporal information, one can use this dataset for frequent sequential pattern mining. Next, use the inspect function to inspect the transactions. You can see the output here. You can then obtain the summary information of the transactions with the temporal information. These are the summary statistics. In addition to creating your own transactions with temporal information, you already have data stored in a text file. You can use the read basket function from the A-rule sequences to read the transaction data into the basket format. Here we have used the as function, which we used earlier as well. The A-rule sequences function provides two additional data structures, sequences and timed sequences, to present pure sequence data and sequence data with the time information. If you are interested in these two collections, use the help function to view these documents. You can see the documentation for sequences and timed sequences. Cool! In this video, we have created transactions with temporal information. Amazing! In the next video, we'll take a look at mining frequent sequential patterns with CSPADE. Hi, this is the last video of this section, mining frequent sequential patterns with CSPADE. In the previous video, we learned creating transactions with temporal information. In this video, we will demonstrate how to use CSPADE to mine frequent sequential patterns. In contrast to association mining, which only discovers relationships between item sets, we may be interested in exploring patterns shared among transactions where a set of item sets occurs sequentially. One of the most famous frequent sequential pattern mining algorithms is the sequential pattern discovery using equivalence classes, SPADE algorithm, which employs the characteristics of a vertical database to perform an intersection on an ID list with an efficient lattice search and allows us to place constraints on mined sequences. The object of sequential pattern mining is to discover sequential relationships or patterns in transactions. You can use the pattern mining result to predict future events or recommend items to users. One popular method of sequential pattern mining is SPADE. SPADE uses a vertical data layout to store a list of IDs. In these, each input sequence in the database is called SID, and each event in a given input sequence is called EID. The process of SPADE is performed by generating patterns level-wisely by an a priori candidate generation. In detail, SPADE generates subsequent n sequences from joining n-1 sequences from the intersection of ID lists. If the number of sequences is greater than the minimum support, MinSup, we can consider the sequence to be frequent enough. The algorithm stops when the process cannot find more frequent sequences. In this video, we will complete the previous videos by generating transactions with the temporal information and have it stored in the variable trans. Let's start with mining the frequent sequential patterns. First, you can use the CSPADE function to generate frequent sequential patterns. This is the line of code you need to run. And here is the output. As we have transactions with temporal information loaded in the variable trans, we can use the CSPADE function with the support over 0.75 to generate frequent sequential patterns in the sequences format. Next, examine the summary of the frequent sequential patterns. We can then obtain summary information, such as most frequent items, sequence size distributions, a summary of quality measures, and mining information. Now, transform a generated sequence format data back to the data frame, so that we can examine the sequence and support of frequent sequential patterns with the support over 0.75. This is the line of code we need to use. You can see the output here. If you are interested in the concept and design of the SPADE algorithm, you can refer to the original published paper M. J. Zaki 2001, SPADE, an efficient algorithm for mining frequent sequences, Machine Learning Journal. Great! In this video, we looked at mining frequent sequential patterns with CSPADE. So that marks the end of this section. In this section, we started off with transforming data into transactions and displaying transactions and associations. We then moved on to mining associations with the a priori rule, pruning redundant rules, and visualizing association rules. Lastly, we saw mining frequent item sets with ECLAT, creating transactions with temporal information, and mining frequent sequential patterns with CSPADE. That's amazing! In the next section, we'll learn about dimension reduction. Hi, and welcome to this section, Dimension Reduction. In this section, we will first discuss how to perform feature ranking and selection. Next, we will focus on the topic of feature extraction and cover videos in performing dimension reduction with both linear and non-linear methods. For linear methods, we will introduce how to perform PCA, determine the number of principal components, and its visualization. We then move on to MDS and SVD. Furthermore, we will introduce the application of SVD to compress images. For non-linear methods, we will introduce how to perform dimension reduction with ISOMAP and LLE. Now we move on to the first video of this section that shows how to perform feature selection with F-Selector. In this video, we will first install and load the package F-Selector, and then make an evaluator to select the feature subsets. After this, we will find the optimum feature subset using a hill climbing search. Most datasheets contain features such as attributes or variables that are highly redundant. In order to remove irrelevant and redundant data to reduce the computational cost and avoid overfitting, you can reduce the features into a smaller subset without a significant loss of information. The mathematical procedure of reducing features is known as dimension reduction. The objective of feature selection is to select a set of relevant features to construct the model. The techniques for feature selection can be categorized into feature ranking and feature selection. Feature ranking ranks features with a certain criteria and then selects features that are above a defined threshold. On the other hand, feature selection searches the optimal subset from a space of feature subsets. In feature extraction, the problem can be categorized as a linear or non-linear. The linear method searches an affine space that best explains the variation of data distribution. In contrast, the non-linear method is a better option for data that is distributed on a highly non-linear curved surface. Here, we list some common linear and non-linear methods. So let's have a look at some common linear methods. The first one is PCA. It maps data to lower dimension so that variance of the data in low dimension representation is maximized. Next is MDS, which is a method that allows you to visualize how near, i.e. pattern proximities objects are to each other, and can produce a representation of your data with lower dimension space. PCA can be regarded as the simplest form of MDS if the distance measurement used in MDS equals the covariance of data. Then comes SVD, which removes redundant features that are linear correlated from the perspective of linear algebra. PCA can also be regarded as a specific case of SVD, whereas the examples of common non-linear methods are ISOMAP and LLE. ISOMAP can be viewed as an extension of MDS, which uses the distance metric of geodesic distances. In this method, geodesic distance is computed by graphing the shortest path distances. LLE performs local PCA and global eigen decomposition. LLE is a local approach, which involves selecting features for each category of the class feature. In contrast, ISOMAP is a global approach, which involves selecting features for all features. Let's now perform feature selection with F-Selector. The F-Selector package provides two approaches to select the most influential features from the original feature set. Firstly, rank features by some criteria and select the ones that are above a defined threshold. Secondly, search for optimum feature subsets from a space of feature subsets. So here, we will introduce how to perform feature selection with the F-Selector package. In this video, we will continue to use the Telecom Churn dataset as the input data source to train the support vector machine. If you have not prepared the dataset, please refer to Section 5, Classification Tree, Lazy and Probabilistic for detailed information. Let's perform feature selection on a churn dataset. So we first install and load the package, fselector. So you need to wait a bit while the fselector package is being installed. Then we use random.forest.importance to calculate the weight for each attribute, where we set the importance type to 1. Here we use the random forest algorithm with the mean decrease in accuracy where importance.type equals 1 as the important measurements to gain the weights of each attribute. Besides the random forest algorithm, you can select other feature ranking algorithms, for example, chi-squared, information.gain, from the fselector package. So let's run this code. Here you can see the output. Next, we use the cutoff function to obtain the attributes of the top 5 weights. Let's run this code too. In this case, number of customer service calls, international plan, total day charge, total day minutes, and total international calls are the 5 most important features. After this, we make an evaluator to select the feature subsets. First, we need to make a 5-fold cross-validation function to evaluate the importance of feature subsets. Finally, we can find the optimum feature subset using a hill-climbing search. Here we use the hill-climbing searching algorithm to find the optimum feature subsets from the original feature sets. Besides the hill-climbing method, one can select other feature selection algorithms, i.e. forward.search, from the fselector package. Once you run this code, you can see that the international plan plus voicemail plan plus number vmail messages plus total day minutes plus total day calls plus total eve minutes plus total eve charge plus total international minutes plus total international calls plus total international charge plus number customer service calls are optimum feature subsets. You can also use the caret package to perform feature selection. As we have discussed in related videos in the Model Assessment section, you can refer to Section 7, Model Evaluation, for more detailed information. For both feature ranking and optimum feature selection, you can explore the package, fselector, for more related functions in the Help tab. Cool. In this video, we performed feature selection with fselector. In the next video, we're going to take a look at performing dimension reduction with principal component analysis. Performing dimension reduction with PCA. In the previous video, we looked at performing feature selection with fselector. In this video, we first load the Swiss dataset, obtain a summary from the PCA results, and then use the predict function. Principal component analysis, i.e. PCA, is the most widely used linear method in dealing with dimension reduction problems. It is useful when data contains many features, and there is redundancy, correlation, within these features. To remove redundant features, PCA maps high-dimension data into lower dimensions by reducing features into smaller numbers of principal components that account for most of the variance of the original features. Here, we will introduce how to perform dimension reduction with the PCA method. In this video, we will use the Swiss dataset as our target to perform PCA. The Swiss dataset includes standardized fertility measures and socio-economic indicators from around the year 1888 for each of the 47 French-speaking provinces of Switzerland. So let's now perform principal component analysis on the Swiss dataset. First, load the Swiss dataset. Next, we exclude the first column of the Swiss data. Then we perform principal component analysis on the Swiss data with this line of code. Let's run it. So you can see the standard deviation in the output. Here, first we remove the standardized fertility measures and use the rest of the predictors as input to the function, prcomp. In addition to this, we set Swiss as an input dataset. The variable should be shifted to the 0 center by specifying center equals true. Scale variables into the unit variance with the option scale true and store the output in the variable swiss.pca. Then, we print out the values stored in swiss.pca. we can find the standard deviation and rotation of the principal component. The standard deviation indicates the square root of the eigenvalues of the covariance correlation matrix. On the other hand, the rotation of the principal components shows the coefficient of the linear combination of the input features. For example, PC1 equals agriculture times 0.524 plus examine times minus 0.572 plus education times minus 0.492 plus Catholic times 0.385 plus infant.mortality times 0.092. Here we can find that the attribute agriculture contributes the most for PC1, for it has the highest coefficient. Now let's obtain a summary from the PCA results. You can see the output for this code in the console below. Additionally, you can use the summary function to obtain the importance of components. So the first row shows the standard deviation of each principal component. The second row shows the proportion of variance explained by each component, and the third row shows the cumulative proportion of the explained variance. Lastly, we use the predict function to output the value of the principal component with the first row of data. We use the predict function to obtain principal components from the input features. Here we input the first row of the dataset and retrieve 5 principal components, as you can see all these. Now, since the feature selection method may remove some correlated but informative features, you have to consider combining these correlated features into a single feature with the feature extraction method. PCA is one of the feature extraction methods, which performs orthogonal transformation to convert possibly correlated variables into principal components. Also, you can use these principal components to identify the directions of variance. The process of PCA is carried on by these steps. Firstly, find the mean vector by using this equation, where x of I indicates the data point and n denotes the number of points. Secondly, we compute the covariance matrix by the second equation. Thirdly, compute the eigenvectors and the corresponding eigenvalues. In the fourth step, we rank and choose the top k eigenvectors. In the fifth step, we construct a D by k-dimensional eigenvector matrix, i.e. U. Here, D is the number of original dimensions and k is the number of eigenvectors. Finally, we can transform the data samples into a new subspace. In this figure, it is illustrated that we can use 2 principal components, phi1 and phi2, to transform the data point from a 2-dimensional space to new 2-dimensional subspace. Let's explore more on PCA. Another principal component analysis function is called princomp. In this function, the calculation is performed by using eigen on a correlation or covariance matrix instead of a single-value decomposition used in the prcomp function. In general practice, using prcomp is preferable. However, we cover how to use princomp here. First, use princomp to perform PCA. Once you run this code, you get the output for the poor-incom function, with the standard deviation for 47 observations. Then we obtain the summary information. Here the output gives the importance of components. Next, we use the predict function to obtain principal components from the input features. So, this is the line of code we need to run. Here we obtain 5 components with their corollary values. In addition to the prcomp and princomp functions from the stats package, you can use the principal function from the psych package. So first, install and load the psych package. Use this code. The psych package gets installed and it is loaded. Then we use the principal function to retrieve the principal components. So, you can see all the outputs for the prcomp and princomp functions in the console window. You can also see that the fit based upon off-diagonal value is 1. Wonderful. In this video, we have used the Swiss dataset as our target to perform PCA. In the next video, we will determine the number of principal components using the scree test. This is the third video of this section, determining the number of principal components using the scree test. In the previous video, we used the Swiss dataset as our target to perform PCA. In this video, we will see how to determine the number of principal components using a scree plot. So, first we will generate a bar plot by using scree plot, and then generate a line plot by using scree plot to get the number of principal components. As we only need to retain the principal components that account for most of the variance of the original features, we can either use the Kaiser method, scree test, or the percentage of variation explained as the selection criteria. The main purpose of a scree test is to graph the component analysis results as a scree plot and find where the obvious change in the slope occurs, i.e. the elbow. In a scree plot, there are two types of plots, namely bar plots and line plots. Here we will demonstrate how to use a scree plot to determine the number of principal components. In a scree plot, there are two types of plots, namely bar plots and line plots. For this, you need to ensure that you have completed the previous video by generating a principal component object and save it in the variable swiss.pca. Now, let's determine the number of principal components with the scree plot. First, you need to generate a bar plot by using scree plot. You can also generate a line plot by using scree plot. As you can see, the swiss.pca is the input and the type here is bar plot. When you run this code, you obtain the plot for variances. Next, we generate a line plot by using scree plot. Here we have changed the type of the plot to line. When you run this code, you can observe the change in the output. As both generated scree plots reveal, the obvious change in slope, the so-called elbow or knee, occurs at component 2. As a result, we should retain component 1, where the component is in a steep curve before component 2, which is where the flat line trend commences. However, as this method can be ambiguous, you can use other methods, such as the Kaiser method, to determine the number of components. By default, if you use the plot function on a generated principal component object, you can also retrieve the scree plot. For more details on scree plot, you can refer to the document through the help function. You can also use n factors to perform parallel analysis and your non-graphical solutions to the Cattell scree test. For this, you need to first install and load the n factors. So we run this, and the n factor is loaded with a warning message. So you can see the output now, where the circle represents the eigenvalues and the triangle represents the parallel analysis. Here the red line represents the optimal coordinates and acceleration factor is represented with blue, which is equal to 1. Amazing! In this video, we have determined the number of principal components using a scree plot. In the next video, we will determine the number of principal components in a similar way with the Kaiser method. This is the fourth video of this section, determining the number of principal components using the Kaiser method. In the previous video, we looked at determining the number of principal components using the scree test. In this video, we will learn how to determine the number of principal components using the Kaiser method. So we will first obtain the standard deviation and variance from swiss.pca and then use the scree plot to select components with a variance above 1. In addition to the scree test, you can use the Kaiser method to determine the number of principal components. In this method, the selection criteria retains eigenvalues greater than 1. First, you need to ensure that you have completed the previous video by generating a principal component object and save it in the variable swiss.pca. Let's now determine the number of principal components with the Kaiser method. So we obtain the standard deviation from swiss.pca. Next, we obtain the variance from swiss.pca which is the square root of the standard deviation. So what you get in the output for this is the variance of the corresponding standard deviation. From this computed variance, we find both component 1 and 2 have a variance above 1. Now let's select components with a variance above 1, so we can see that both 1 and 2 can be determined as the number of principal components. You can also use the scree plot to select components with a variance above 1. So you can see the line graph here. Here we have drawn a red line on the scree plot to indicate that we need to retain component 1 and 2 in this case. In this video, we have learned to determine the number of principal components using the Kaiser method. In the next video, we will explore visualizing multivariate data using biplot. The fifth video of this section, visualizing multivariate data using biplot. In the previous video, we looked at determining the number of principal components using the Kaiser method. In this video, we will see how to use biplot to plot both variables and data. We will first create a scatter plot using component 1 and 2. We will then create biplot using the generated principal component object. In order to find out how data and variables are mapped in regard to the principal component, you can use biplot, which plots data and the projections of original features onto the first two components. Here, we will demonstrate how to use biplot to plot both variables and data on the same figure. So you need to ensure that you have completed the previous video by generating a principal component object and save it in the variable swiss.pca. Now let's create a biplot. We create a scatter plot using component 1 and 2, and these are lines of code we inserted for it. When you run this, you can see the plot in the project window, where the first component is on the x-axis and the second component is on the y-axis. In the first step, we demonstrate that we can actually use the first two components to create a scatter plot. Now, if you like to add features on the plot, you can create biplot using the generated principal component object. In biplot, you can see the provinces with higher indicators in the agriculture variable, lower indicators in the education variable, and examination variable scores that are higher in PC1. On the other hand, the provinces with the higher infant mortality indicators and lower agricultural indicators score higher in PC2. Now, besides biplot in the stats package, you can also use ggbiplot. However, you may not find this package from CRAN. You have to first install DevTools and then install ggbiplot from GitHub. So, we have inserted the line of code to do this, and now we run this code. So, now the DevTool is installed and loaded. Then we load the DevTool libraries. So, the libraries are loaded with a warning message. Then we install ggbiplot and also load the libraries. Finally, we use the ggbiplot function with swiss.pca to plot the biplot. So here is the output with the first component on the x-axis and the second component on the y-axis. In this video, we have seen how to use biplot to plot both variables and data. In the next video, we will dive into performing dimension reduction with MDS. Hey, welcome to the sixth video of this section, performing dimension reduction with MDS. In the previous video, we learned how to visualize multivariate data using biplot. In this video, we will illustrate how to perform MDS on the Swiss dataset. We will first perform metric MDS with a maximum of 2 dimensions, and then plot the Swiss data in a 2-dimension scatterplot. Multidimensional scaling, i.e. MDS, is a technique to create a visual representation of similarities or dissimilarities, distance, of a number of objects. The multi prefix indicates that one can create a presentation map in 1, 2, or more dimensions. However, We most often use MDS to present the distance between data points in 1 or 2 dimensions. In MDS, you can either use a metric or a non-metric solution. The main difference between the two solutions is that metric solutions try to reproduce the original metric, while non-metric solutions assume that the ranks of the distance are known. In this recipe, we will illustrate how to perform MDS on the Swiss dataset. Let's move ahead and perform multidimensional scaling using the metric method. First, we perform metric MDS with a maximum of 2 dimensions. Here we specify k equals 2, so the maximum generated dimensions equals 2. Then we plot the Swiss data in a 2-dimension scatterplot. So you can see the scatterplot, where the first component is plotted on the x-axis and the second component, t, is plotted on the y-axis. In addition, you can perform non-metric MDS with ISO-MDS. First, you need to load the library, MAS. Once it is loaded, you can use this line of code to perform ISO-MDS. In non-metric MDS, we do not match the distances, but only arrange them in order. We also set Swiss as an input dataset with maximum dimensions of 2. After this, we also plot the data points in a 2-dimension scatterplot. So in the adjacent window, you can see the ISO-MDS mass plotted with components. Then we plot the data points in a 2-dimension scatterplot using the Shepard function. Here we use a Shepard plot, which shows how well the project distances match those in the distance matrix. As per this figure, the projected distance matches well in the distance matrix. Let's now dive into working in MDS. MDS reveals the structure of the data by providing a visual representation of similarities among a set of objects. In more detail, MDS places an object in an n-dimensional space, where the distances between the pairs of points corresponds to the similarities among the pairs of objects. Usually, the dimensional space is a 2-dimensional Euclidean space, but it may be non-Euclidean and have more than 2 dimensions. In accordance with the meaning of the input matrix, MDS can be mainly categorized into 2 types: metric MDS, where the input matrix is metric-based; non-metric MDS, where the input matrix is non-metric-based. Metric MDS is also known as principal coordinate analysis, which first transforms a distance into similarities. In the simplest form, the process linearly projects original data points to a subspace by performing principal components analysis on similarities. On the other hand, the process can also perform a nonlinear projection of similarities by minimizing the stress value. So this equation gives the stress value, where d of k, L is the distance measurement between 2 points, xk and xl, and d' of k, L is the similarity measurement of 2 projected points, x' and x'. As a result, we can represent the relationship among objects in the Euclidean space. In contrast to metric MDS, which uses a metric-based input matrix, a non-metric-based MDS is used when the data is measured at the ordinary level. As only the rank order of the distances between the vectors is meaningful, non-metric MDS applies a monotonically increasing function f on the original distances and projects the distance to new values that preserve the rank order. The normalized equation can be formulated as this one. Another visualization method is to present an MDS object as a graph. So this is sample code you can run to represent MDS as a graph. So you can also compare differences between the generated results from MDS and PCA. You can compare their differences by drawing the projected dimensions in the same scatterplot. If you use a Euclidean distance on MDS, the projected dimensions are exactly the same as the ones projected from PCA. In this video, we have seen how to perform MDS on the Swiss dataset. In the next video, we'll look into reducing dimensions with SVD. The 7th video of this section, reducing dimensions with SVD. In the previous video, we performed dimension reduction with MDS. In this video, we will illustrate how to perform dimension reduction with SVD. We will begin with performing SVD on the Swiss dataset, and then we will plot the percentage of variance and the cumulative variance. Lastly, we will reconstruct the data with only one singular vector. Singular value decomposition, i.e. SVD, is a type of matrix factorization, which can factorize matrices into two orthogonal matrices and diagonal matrices. You can multiply the original matrix back using these three matrices. SVD can reduce redundant data that is linear dependent from the perspective of linear algebra. Therefore, it can be applied to feature selection, image processing, clustering, and many other fields. In this video, we will continue using the dataset Swiss as our input data source. So let's perform dimension reduction using SVD. First, we perform SVD on the Swiss dataset. So we run this line of code. Next, we plot the percentage of variance explained and the cumulative variance explained in accordance with the SVD column. So in the output, you can see the singular vector on the x-axis and variance explained on the y-axis. Here we generate two plots. One shows the variance explained in accordance to a singular vector. The other shows the cumulative variance explained in accordance to a singular vector. Next, we reconstruct the data with only one singular vector. Also, we compare the original dataset with the constructed dataset in an image. Here you can see that the first singular vector can explain 80% of variance. We now want to compare the differences from the original dataset and the reconstructed dataset with a single singular vector. We therefore reconstruct the data with a single singular vector and use the image function to present the original and reconstructed datasets side by side and see how they differ from each other. This figure reveals that these two images are very similar. That means the original data and the reconstructed data are very similar. As I mentioned earlier, PCA can be regarded as a specific case of SVD. Here we generate the orthogonal vector from the Swiss data from SVD and obtained the rotation from PRComp. We can see that the two generated matrices are the same. So, you can see the output here with 5 components. From the output, you can make out that we get the same result for SVD and PCA. Wonderful! In this video, we demonstrated how to factorize a matrix with SVD and then reconstruct the dataset by multiplying the decomposed matrix. In the next video, we will step ahead and see how to compress images with SVD. The 8th video of this section, compressing images with SVD. In the previous video, we saw how to reduce dimensions with SVD. In this video, we will learn to compress images by performing SVD on the read numeric matrix and then using 18 vectors to reconstruct the image. Let's begin with downloading the image of Lena beforehand from www.ece.rice.edu. So this is the image which we are going to download and use as the sample data. So, click on it and save the image. You can even prepare an image of your own to see how image compression works. Let's move to RStudio now. Let's compress an image with SVD. We first install and load BMP, so you can see that it is loaded with a warning message. Then we read the image of Lena as a numeric matrix with the read.bmp function. When the reader downloads the image, the default name is lena512.bmp. Now we rotate and plot the image. Next, we perform SVD on the read numeric matrix and plot the percentage of variance explained. After this, we obtain the number of dimensions to reconstruct the image. So you can see the value for the reconstructed image, which is 512. This is the dimension value. Now obtain the point at which the singular vector can explain more than 90% of the variance. Further, as we discover that we can use 18 components to explain 90% of the variance, We then use these 18 components to reconstruct Lena. We also wrap the code into a function, Lena compression, and you can use this function to plot compressed Lena. Next, we use 18 vectors to reconstruct the image. As we entered 18 as the input to the function, which returns a rather blurry Lena image, as you can see in this figure. However, we can at least see an outline of the image. Now we obtain the point at which the singular vector can explain more than 99% of the variance. So, you can see the value 92 is written here. So to obtain a clearer picture, we use 92 components to explain 99% of the variance. We therefore set the input to the function Lena compression as 92. The figure in step 9 shows that this generates a clearer picture than the one constructed using merely 18 components. For more details on the Lena picture, you can refer to this website. In this video, we have demonstrated how to perform SVD on the classic image processing material, Lena. In the next video, we will perform nonlinear dimension reduction with IsoMap. The 9th video of this section, performing nonlinear dimension reduction with IsoMap. In the previous video, we demonstrated how to perform SVD on the classic image processing material, Lena. In this video, we will illustrate how to perform a nonlinear dimension reduction with IsoMap. We will first install and load the RNav graph image data and vegan packages. After this, we will use IsoMap to perform dimension reduction. IsoMap is one of the approaches for manifold learning, which generalizes linear framework to nonlinear data structures. Similar to MDS, IsoMap creates a visual representation of similarities or dissimilarities, distance, of a number of objects. However, as the data is structured in a nonlinear format, the Euclidean distance measure of MDS is replaced by the geodesic distance of a data manifold in IsoMap. So here we will use the digits data from the RNav graph image data as our input source. First, we install and load the RNav graph image data and vegan packages. So we install these one by one. Next, we install the vegan package. After this, we load both the libraries. Next, we load the dataset, digits. Let's rotate and plot the image. Next, we select one digit and plot its rotated image. And you can see an image of the handwritten digit, i.e. the numeral 3, in the output figure. Next, we randomly sample 300 digits from the population. Let's transpose the selected digit data and then compute the dissimilarity between objects using VegDist function. Now, once the data is ready, we calculate the distance between each object and perform a dimension reduction. Here we use VegDist to calculate the dissimilarities between each object using a Euclidean measure. Next, we use IsoMap to perform dimension reduction on the digits data, with the dimension set as 6, number of shortest dissimilarities retained for a point as 8, and ensure that you analyze the largest connected group by specifying fragmented OK as true. So, you can see the image here. Finally, we use the generated IsoMap object to make a two-dimension scatterplot. Lastly, overlay the scatterplot with the minimum spanning tree marked in red. So this is the 2D scatterplot overlay with minimum spanning tree. You can also use the RNav graph package to visualize high-dimensional data using graphs as a navigational infrastructure. For more information, you can refer to this web documentation at www.icesi.edu.co. Let's now see how to use RNav graph to visualize high-dimensional data in a graph. So we first install and load the RNav graph and graph packages. So we run these lines of code. We need to wait a bit while these packages and libraries are being loaded and installed. We then create an ngData object for the digit data. So we run these lines of code for it. Next, we create an ngGraph object from ngData. Finally, we visualize the graph in the 2K2D plot. Awesome. This is the session 2. Here's session 3. So you can run it as many times as you want and see different plots. Also, you can view a 4D transition graph plot. You can plot type as images and see the graph here. Cool! In this video, we have performed a nonlinear dimension reduction with IsoMap. In the next video, we will see how to perform a nonlinear dimension reduction with local linear embedding. Hi, welcome to the last video of this section, performing nonlinear dimension reduction with local linear embedding. In the previous video, we learned how to perform a nonlinear dimension reduction with IsoMap. In this video, we will perform nonlinear dimension reduction with local linear embedding. So we will first install and load the LLE package, and then use plot.lle to plot the LLE result. Locally linear embedding, LLE, is an extension of PCA, which reduces data that lies on a manifold embedded in a high-dimensional space into a low-dimensional space. In contrast to IsoMap, which is a global approach for nonlinear dimension reduction, LLE is a local approach that employs a linear combination of the k-nearest neighbor to preserve local properties of data. Here we will use digit data from the LLE SCURV data within the LLE package as our input source. Let's first install and load the LLE package. So you can see we have successfully installed and loaded the LLE package, with a few warnings. Next, we load LL SCURV data from LLE. Then we perform LLE on LLE SCURV data. Here we have performed LLE with 2 dimensions and 12 neighbors, and list the dimensions for every data point by specifying ID equals true. The LLE has 3 steps, including building a neighborhood for each point in the data, finding the weights for linearly approximating the data in that neighborhood, and finding the low-dimensional coordinates. Now let's examine the result with the str, and you can also see the output here. The str function returns x, y, choice, and id. Here x represents the input data, y stands for the embedded data, choice indicates the index vector of the kept data, while subset selection and ID show the dimensions of every data input. Then we use the plot function. The plot function returns the scatter plot of the embedded data. Lastly, we use plot LLE to plot the result. Here we enable the interaction mode by setting the inter equal to true. Lastly, we use plot LLE to plot LLE result. Here we enable the interaction mode by setting the inter equal to true. So this is the output for RGL device 1 focus. Now LLE is a nonlinear dimension reduction method, which computes a low-dimensional neighborhood, preserving embeddings of high-dimensional data. The algorithm of LLE can be illustrated in these steps. First, LLE computes the k neighbors of each data point, i.e. x to I. Secondly, it computes a set of weights for each point, which minimizes the residual sum of errors, which can best reconstruct each data point from its neighbors. The residual sum of errors can be described with this expression, where wij equals 0 if xi is not one of xi's k nearest neighbor, and for each I, summation of w is equal to 1. Finally, find the vector y, which is best reconstructed by the weight w. The cost function can be illustrated with the second equation. Another useful package for nonlinear dimensional reduction is the RDR Toolbox, which is a package for nonlinear dimension reduction with IsoMap and LLE. So you can use the following command to install RDR Toolbox. This is the line of code you need to run for it. As you run, you can see that it is extracting the source and the RDR Toolbox is being loaded and installed in the R session. Excellent. In this section, we first saw how to perform feature ranking and selection. Next, we learned feature extraction and covered performing dimension reduction with both linear and non-linear methods. For linear methods, we introduced how to perform PCA. We also determined the number of principal components and visualized it. We then went ahead to explore MDS and SVD. We also diced into the application of SVD to compress images. For non-linear methods, we then performed dimension reduction with Isomap and LLE. In the next section, we will do big data analysis with R and Hadoop. Hello, welcome to the last section of the course. In this section, we will start by preparing the Hadoop environment so that you can install R Hadoop. We then cover the installation of three main packages: RMR, RHDFS, and PLY-RMR. Next, we will introduce how to use RMR to perform MapReduce from R, operate an HDFS file through RHDFS, and perform a common data operation using PLY-RMR. Further, we will explain how to perform machine learning using R Hadoop. Lastly, we will introduce how to deploy multiple R Hadoop clusters on Amazon EMR. Now let's get started with the first video of the section, preparing the R Hadoop environment. In this video, we will load and install R Hadoop using Cloudera Quick Start VM. We will start the R session and have a look at how to work on it. As R Hadoop requires an R and Hadoop integrated environment, we must first prepare an environment with both R and Hadoop installed. Instead of building a new Hadoop system, we can use the Cloudera Quick Start VM. The VM is free, which contains a single node Apache Hadoop cluster and R. In this video, we will demonstrate how to download the Cloudera Quick Start VM. To use Cloudera Quick Start VM, it is suggested that you prepare a 64-bit guest OS with either VMware or VirtualBox or the KVM installed. If you choose to use VMware, you should prepare a player compatible with Workstation 8.x or higher, Player 4.x or higher, ESXi 5.x or higher, or Fusion 4.x or higher. Note, 4 GB of RAM is required to start VM, with an available disk space of at least 3 GB. Let's start. Visit the Cloudera Quick Start VM download site. After you click on Downloads, you can see Quick Starts, Cloudera Manager, and Cloudera Director. So click on the Download now in Quick Starts. You can see the Select the Platform and Quick Start for your machine. Here it is 5.8. It will automatically show 5.8. Here there are 4 platforms: Docker, Image, VirtualBox, VMware, and KVM. Depending on the virtual machine platform installed on your OS, choose the appropriate link. Here, I require VMware. To download VMware, you can select VMware and click on Get It Now. Once you click on Get It Now, you will need to sign up to get the zip file for CDH 5.8. Next, you can start the Quick Start VM using the virtual machine platform installed on your OS. You should see the desktop of CentOS 6.7 in a few minutes. You can just start with the VMware workstation. Click on Open Virtual Machine, Play Virtual Machine. So the virtual machine is getting started. This will take some time. Once that is done, you can then open a terminal and type Hadoop, which will display a list of functions that can operate a Hadoop cluster. type R to access an R session. Check whether version 3.1.1 is already installed in the Cloudera Quick Start VM. If you cannot find R installed in the VM, please use the following command to install R. Here it is showing that you need to be root to perform this command. So you can try the command with sudo. This will take time as the file is large. Once it is installed, you can see that installation is complete and all the dependencies are updated. Besides using Cloudera Quick Start VM, you may consider using a sandbox VM provided by Hortonworks or MapR. You can find Hortonworks Sandbox at this link and download and install it. Also, MapR provides a sandbox. You can find it at this link. You can download the sandbox for VMware or VirtualBox and use it. In this video, we downloaded and installed Cloudera Quick Start VM successfully. Amazing! In the next video, we will be installing RMR2. This is the second video of the section, Installing RMR2. In the previous video, we installed R Hadoop environment using Cloudera Quick Start VMware. In this video, we are going to install the RMR2 package and also how to work with it. The RMR2 package allows you to perform big data processing and analysis via MapReduce on a Hadoop cluster. To perform MapReduce on a Hadoop cluster, you have to install R and RMR2 on every task node. In this video, we will illustrate how to install RMR2 on a single node of a Hadoop cluster. Ensure that you have completed the previous recipe by starting the Cloudera Quick Start VM and connecting the VM to the internet so that you can proceed with downloading and installing the RMR2 package. Perform the following steps to install RMR2 on the Quick Start VM. First, open the terminal within the Cloudera Quick Start VM. So let's go to the Application System tool. You can see the terminal here. Use the permission of the root to enter an R session. Type this command. You can then install dependent packages before installing RMR2. So these commands are for installing the packages, such as code tools, RCPP, RJSON-O, BitOps, Digest, Functional, Strings, PLYR, Reshape2, RJava, and CarTools. Press Enter. You will need to choose a CRAN mirror from this. So I will select India. Once the depending packages are installed, you can quit the R session. So we quit the R session. Next, you can download RMR-3.3.0 to the Quick Start VM. You may need to update the link if Revolution Analytics upgrades the version of RMR2, so you can type this command. Now you are connected to GitHub and DRMR2 is installed. You can then install RMR-3.3.0 to the Quick Start VM using the sudo command. This is the complete command. Run the command. You can see that it's being installed. Lastly, you can enter an R session and use the library function to test whether the library has been successfully installed. So first, we type R. Then we type library RMR2. To see more information and read updates about R Hadoop, you can refer to the R Hadoop wiki page hosted on GitHub link. This is the link. Here is the page. In this video, we installed RMR2 package successfully. Awesome! In the next video, we will install RHDFS. Hi, this is the third video of the section, Installing RHDFS. In the previous video, we installed RMR2 packages. In this video, we will introduce how to install RHDFS on the Cloudera Quick Start VM. The RHDFS package is the interface between R and HDFS, which allows users to access HDFS from an R console. Similar to RMR2, you should install RHDFS on every task node, so that one can access HDFS resources through R. Ensure that you have completed the previous recipe by starting the Cloudera Quick Start VM and connecting the VM to the internet, so that you can proceed with downloading and installing the RHDFS package. First, you can download RHDFS 1.0.8 from GitHub. For that, you need to run this wget command with the link of RHDFS. When we run it, we see that RHDFS is being downloaded from GitHub. Next, you can install RHDFS under the command line mode, so we run this command. When we press Enter, we see that RHDFS is installed. You can then set up Java Home. The configuration of Java Home depends on the installed Java version within the VM. You need to run this command to set the Java Home. Last, you can set up the system environment and initialize RHDFS. You may need to update the environment setup if you use a different version of Quick Start VM. Type R. This is the command to set the environment variable. Next, you need to set up the Hadoop system environment for the Hadoop streaming. We run this command. You can also check if the RHDFS is properly installed or not using the library command. So here, when I type the command, I can see that it is loaded into the R session. Then we will initialize the HDFS using hdfs.init function. So you can see that the HDFS is loaded with some warnings. You don't have to worry about the warnings now. To find where Hadoop CMD is located, you can use the which Hadoop command in the Linux shell. In most Hadoop systems, Hadoop CMD is located at usr bin Hadoop. So you can just type which Hadoop. Sorry, first you need to quit from the R session and then run the command. As you can see here, it is stored in the user bin Hadoop. As for the location of Hadoop streaming, the streaming jar file is often located in usr lib Hadoop MapReduce. However, if you cannot find the directory usr lib Hadoop MapReduce in your Linux system, you can search the streaming jar by using the locate command. For example, you have to write sudo update db. Once that is done, type this command line. You get the streaming files and their locations. Amazing! In this video, we installed RHDFS on Cloudera Quick Start VM. In the next video, we'll see how to operate HDFS with RHDFS. Hi, this is the fourth video of the section, Operating HDFS with RHDFS. In the previous video, we installed RHDFS. In this video, we will demonstrate how to use the RHDFS function to manipulate HDFS. We will perform various operations, such as moving a file, renaming, writing into a file, changing permissions, etc. The RHDFS package is an interface between Hadoop and R. which can call an HDFS API in the back end to operate HDFS. As a result, you can easily operate HDFS from the R console through the use of the RHDFS package. You need to have installed RHDFS into R and validate that you can initial HDFS via the hdfs.init function. Initialize the RHDFS package. You need to set up the system environment by typing this command. Next, you need to set up the Hadoop streaming environment. You also need to load the library of the RHDFS. So it is loaded. You can then type hdfs.init to initialize the HDFS environment. You can then manipulate files stored on HDFS as follows. First, use hdfs.put to copy a file from the local file system to HDFS using this code. It will return true because it is done successfully. For hdfs.ls, read the list of directory from HDFS using this. You can see the list of directories and files in HDFS. You can use hdfs.copy to copy a file from one HDFS directory to another. So again, the copying is successful. We will then use hdfs.move to move a file from one HDFS directory to another. Our next function is hdfs.delete. It is used to delete an HDFS directory from R. The next function is hdfs.rm, which deletes an HDFS directory from R. So, you can see that the file is already deleted, so it is showing an error that no such file is found. To download a file from HDFS to a local file system, you can use hdfs.get. You can see that it is successful. So your file is downloaded into the directory. Now you can use hdfs.rename to rename a file stored on HDFS. You have to give the old name and new name of the file in the function. You can change the permissions of a file or directory using the hdfs.chmod function. You can read the meta information of the HDFS file using hdfs.chmod function, so you get the meta information of the files. Also, you can write stream to the HDFS file. For that, you can write this line. iris.txt is the name of the file. W denotes that you have writing permission for the file. You can load the iris dataset, as we do in R. You can write into the iris file now using the hdfs.write function. So our writing was successful. Then you can close the file. Lastly, you can read stream from the HDFS file. You would have to change the mode of the file. Write R instead of W, which means that you are giving reading permission instead of writing. Then you have to give this command. You can then give unserializing to retrieve your file back. You can see the file here. Then I will close this file. To initialize RHDFS, you have to set Hadoop CMD and Hadoop streaming in the system environment. Instead of setting the configuration each time you're using RHDFS, you can put the configurations in the rprofile file. Therefore, every time you start an R session, the configuration will be automatically loaded. In this video, we understood and operated an HDFS using RHDFS. In the next video, we will implement a word count problem with R Hadoop. Hello, this is the 5th video of the section, implementing a word count problem with R Hadoop. In the previous video, we have operated on HDFS using RHDFS. In this video, we will demonstrate how to use RMR2 to implement a word count problem. To demonstrate how MapReduce works, we illustrate the example of a word count, which counts the number of occurrences of each word in a given input set. Here we will need an input file as our word count program input. You can download the example input from this GitHub link. You can see a wc.input.txt file here. Click on it to download the file. First, you need to configure the system environment and then load RMR2 and RHDFS into an R session. You may need to update the use of the jar file if you use a different version of Quick Start VM. You can run this code to configure the system environment. Then load RMR using the library function. Then we can just load the RHDFS library. Then we need to initialize the HDFS. You can then create a directory on HDFS and put the input file into a newly created directory. To make the directory, you need to run the hdfs.mkdir function. You have to give the file name and the path where you have to save the file. So that is done here. Next, you can create a map function. You can see the map function here. Next, we begin implementing the MapReduce program. Normally, we can divide the MapReduce program into the map and reduce functions. In the map function, we first use the strsplit function to split each line into words. Then, as the strsplit function returns a list of words, we can use the unlist function to character vectors. Lastly, we can return key-value pairs with each word as a key and the value as 1. Create a reduce function. This is the reduce function. As the reduce function receives the key-value pair generated from the map function, the reduce function sums the count and returns the number of occurrences of each word or key. Now let's call the MapReduce program to count the words within a document. So first, you need to set the HDFS root as word count and HDFS data as part of the file, and hdfs.out as variable. Then we can call the word count function. After we have implemented the map and reduce functions, we can submit our job via the MapReduce function. Normally, MapReduce function requires 4 inputs, which are the HDFS input path, the HDFS output path, the map function, and the reduce function. In this case, we specify the input as word count data, output as word count out, map function as MapReduce function as reduce, and wrap the MapReduce call in function word count. Lastly, we call the function word count and store the output path in the variable out. This is the line of code to get the output. You can see that it is being run. In the output, you can see that number of splits is 2 and the input path is 1. You can see that it is being mapped and reduced. This will take a little time. So here, the file is created. Lastly, you can retrieve the top 10 occurring words within the document. We can use the from.dfs function to load the HDFS data into the results variable, which contains the mapping of words and number of occurrences. We can then generate the top 10 occurring words from the results variable. So here are our characters and their corresponding counts. In this video, we demonstrate how to write an R MapReduce program to solve a word count problem. However, if you are interested in how to write a native Java MapReduce program, you can refer to this link. In this video, we learned how to implement word count function in R Hadoop successfully. Awesome! In the next video, we will make a comparison between an R MapReduce program and a standard R program. Hi, and welcome to the 6th video of the section, comparing the performance between an R MapReduce program and a standard R program. Previously, we implemented a word count problem in R Hadoop. In this video, we'll compare the performance between an R MapReduce program and a standard R program to demonstrate that Hadoop does not perform as quickly as some may believe. Those not familiar with how Hadoop works may often see Hadoop as a remedy for big data processing. Some might believe that Hadoop can return the processed results for any size of data within a few milliseconds. In this video, you should have completed the previous task by installing RMR2 into the R environment. And also, you need to set the Hadoop directory and Hadoop streaming. You need to load the RMR2 and HDFS library and initialize HDFS. Firstly, you can implement a standard R program to have all numbers squared. The output is here. We implement two programs to square all the numbers. In the first program, we use a standard R function, sapply, to square the sequence from 1 to 100,000. To record the program execution time, we first record the processing time before the execution in a.time, and then subtract a.time from the current processing time after the execution. Normally, the execution takes no more than 10 seconds. To compare the performance, you can implement an R MapReduce program to have all numbers squared. So the MapReduce program is being run. In the second program, we use RMR2 package to implement a program in the R MapReduce version. In this program, we also record the execution time. Normally, this program takes a few minutes to complete a task. You can see the difference between the time. The performance comparison shows that a standard R program outperforms the MapReduce program when processing small amounts of data. This is because a Hadoop system often requires time to spawn daemons, job coordination between daemons, and fetching data from data nodes. Therefore, a MapReduce program often takes a few minutes to a couple of hours to finish the execution. As a result, if you can fit your data in the memory, you should write a standard R program to solve the problem. Otherwise, if the data is too large to fit in the memory, you can implement a MapReduce solution. In order to check whether a job will run smoothly and efficiently in Hadoop, you can run a MapReduce benchmark, MRBench, to evaluate the performance of the job. So the code for that is this line. You need to specify the jar file of your Hadoop test and also the n number of runs. Here I have taken hat as 5. When I press enter, I get an error here. For that, you need to quit your R session. You can save your workspace, then you try again. Running that command, you can see here that the MRBench program is running. It will take a little time. As we have mentioned, number of runs as 5. Currently, it is running job 2, so you can see that this is the output. You can see the number of maps as 2 and the reduces as 1. The average time is 35 seconds approximately. In this video, we have made a brilliant comparison between RMapReduce and standard R program. Excellent! In the next video, we will look at testing and debugging the RMR2 program. This is the 7th video of this section, testing and debugging the RMR2 program. In the previous video, we looked at comparing the performance between an RMapReduce program and a standard R program. In this video, we will introduce the technique to test a MapReduce program in local mode and then list the content of the variable within the map or reduce function. Since running a MapReduce program will require a considerable amount of time, varying from a few minutes to several hours, testing and debugging becomes very important. Here we will illustrate some techniques you can use to troubleshoot an RMapReduce program. So, you should have completed the previous video by installing RMR2 into an R environment. Perform the following steps to test and debug an RMapReduce program. If you are starting the R session for the first time, you need to set the Hadoop environment and the streaming environment in this session. And you need to load the libraries RMR2 and RHDFS. And you need to start initializing HDFS. First, we configure the backend as local in rmr.options. Now here we have introduced the technique to test a MapReduce program in local mode. If you would like to run the MapReduce program in a pseudo-distributed or fully distributed mode, it would take you a few minutes to several hours to complete the task, which would involve a lot of wastage of time while troubleshooting your MapReduce program. Therefore, you can set the backend to the local mode in rmr.options, so that the program will be executed in the local mode, which takes less time to execute. Now again, we execute the number squared MapReduce program we used in the previous video. So first, you need to calculate the current time. Then you need to just initialize the int variable from 1 to 100,000. And now you can run a MapReduce program, and with this you can calculate the current time. In addition to this, if you want to print the structure information of any variable in the MapReduce program, we use rmr.str function. So we run this line of command. Now another debugging technique is to list the content of the variable within the map or reduce function. In an R program, you can use the str function to display the compact structure of a single variable. In RMR2, the package also provides a function named rmr.str, which allows you to print out the content of a single variable onto the console. Here we use rmr.str to print the content of variables within a MapReduce program. So you can see the dotted pair list of 14 numbers as the output. Now, if you are interested in the options settings for the RMR2 package, you can refer to the help document or rmr.options by running the help rmr.options command. Here you can find all the details of the RMR2 package. Wonderful! In this video, we have learned how to test and debug the RMR2 program. In the next video, we will have a look at installing PLY-RMR. Hi, and welcome to the next video of Section 12, Installing PLY-RMR. In the previous video, we have learned how to test and debug the RMR2 program. In this video, we will introduce how to install PLY-RMR on the Hadoop system. PLY-RMR package provides common operations, as found in PLYR or Reshape 2 for users to easily perform data manipulation through the MapReduce framework. Ensure that you have completed the previous section by starting the Cloudera Quick Start VM and connecting the VM to the internet. Also, you need to have the RMR2 package installed beforehand. Perform the following steps to install PLY-RMR on the Hadoop system. First, you should install libxml2 devel and curl devel in the Linux shell. You can then access R and install the dependent packages. Before proceeding further, you need to ensure that all the dependent packages are installed, and if not, you can install it individually from the CRAN sites. Next, you can download PLY-RMR 0.5.0 and install it on Hadoop VM. You may need to update the link if Revolution Analytics upgrades the version of PLY-RMR by using this code. Lastly, validate the installation. Besides writing an R MapReduce program, using the RMR2 package, you can use the PLY-RMR to manipulate data. The PLY-RMR package is similar to Hive and Pig in the Hadoop ecosystem, which is the abstraction of the MapReduce program. Therefore, we can implement an R MapReduce program in PLYR style instead of implementing the mapf and reduce functions. To install PLY-RMR, first install the package of libxml2 devel and curl devel using the yum install command. Then access R and install the dependent packages. Lastly, download the file from GitHub and install PLY-RMR in R. To read more information about PLY-RMR, you can use the help function to refer to the document. Great! We have successfully installed PLY-RMR. In the next video, we will see how to manipulate data with PLY-RMR. Welcome to the next video of Section 12, Manipulating Data with PLY-RMR. In the previous video, we have learned how to install PLY-RMR. In this video, we will learn to manipulate data with PLY-RMR. While writing a MapReduce program with RMR2 is much easier than writing a native Java version, it is still hard for non-developers to write a MapReduce program. Therefore, you can use PLY-RMR, a high-level abstraction of the MapReduce program, so that you can use PLYR-like operations to manipulate big data. In this video, we will introduce some operations you can use to manipulate data. In this video, you should have completed the previous section by installing PLY-RMR and RMR2 in R. Perform the following steps to manipulate data with PLY-RMR. First, you need to load both PLY-RMR and RMR2 into R. You can then set the execution mode to the local mode. Otherwise, you will have to wait anywhere between a few minutes to several hours if PLY-RMR is running on Hadoop mode, the default setting. Next, load the Titanic dataset into R. Let's begin the operation by filtering the data. You can use a pipe operator to filter the data. Put the Titanic data into HDFS and load the path of the data to the variable TIData. Next, you can generate a summation of the frequency from the Titanic data. You can also group the frequency by sex with the transmute and sum functions. Also, PLY-RMR allows users to sum up the frequency by gender. You can then sample 10 records out of the population. In addition to this, you can use PLY-RMR to join two datasets. Here we list some functions that can be used to manipulate data with PLY-RMR. You may refer to the help function for further details on their usage and functionalities. Number 1. Data manipulation. Bind.cols. This adds new columns. Select. This is used to select columns. Where. This is used to select rows. Transmute. This uses all of the above plus their summaries. Number 2. From reshape to melt and decast. It converts long and wide data frames. Number 3. Summary. Count, quantile, sample. Number 4. Extract. Top.k, bottom.k. Awesome! We have successfully manipulated data with PLY-RMR. In the next video, we will learn how to conduct machine learning with R Hadoop. Hi, and welcome to the next video of Section 12, Conducting Machine Learning with R Hadoop. In the previous video, we have learned how to manipulate data with PLY-RMR. In this video, we will complete installing RMR2 into the R environment. In the previous sections, we have demonstrated how powerful R is when used to solve machine learning problems. Also, we have shown that the use of Hadoop allows R to process big data in parallel. At this point, some may believe that the use of R Hadoop can easily solve machine learning problems of big data via numerous existing machine learning packages. However, you cannot use most of these to solve machine learning problems, as they cannot be executed in the MapReduce mode. In the videos which follow, we will demonstrate how to implement a MapReduce version of linear regression and compare this version with the one using the LM function. In this video, you should have completed the previous section by installing RMR2 into the R environment. Perform some steps to implement a linear regression in MapReduce. First, load the CATS dataset from the MAS package. We first retrieve the CATS dataset from the MAS package. We then load X as the body weight and Y as the heart weight. You can then generate a linear regression model by calling the LM function. You can now make a regression plot with the given data points and model. Load RMR2 into R. You can then set up X and Y values. The sum function to sum up the values is highlighted here. Compute XTX in MapReduce Job 1. As we cannot perform linear regression using the LM function in the MapReduce form, we have to rewrite the regression model in a MapReduce fashion. Here we would like to implement a MapReduce version of linear regression in 3 steps, which are: calculate the XTX value with the MapReduce, Job 1. Calculate the XTY value with MapReduce, Job 2, and then derive the coefficient value. In the first step, we pass the matrix X as the input to the map function. The map function then calculates the cross product of the transposed matrix, X and X. The reduce function then performs the sum operation defined in the previous section. You can then compute XTY in MapReduce Job 2. In the second step, the procedure of calculating XTY is similar to calculating XTX. The procedure calculates the cross product of the transposed matrix X and Y. The reduce function then performs the sum operation. Lastly, you can derive the coefficient from XTX and XTY. We use the solve function to derive the coefficient, which is highlighted here. As the results show, the coefficients computed by LM and MapReduce differ slightly. Generally speaking, the coefficient computed by the LM model is more accurate than the one calculated by MapReduce. However, if your data is too large to fit in the memory, you have no choice but to implement linear regression in the MapReduce version. You can access more information on machine learning algorithms at this GitHub link. Great! We have successfully conducted machine learning with R Hadoop. In the next video, we will learn how to configure R Hadoop clusters on Amazon EMR. Hi, this is the last video of the section, Configuring R Hadoop Clusters on Amazon EMR. In the previous video, we learnt conducting machine learning with R Hadoop. In this video, we will demonstrate how to configure R Hadoop clusters in Amazon EMR. Until now, we have only demonstrated how to run a R Hadoop program in a single Hadoop node. In order to test our R Hadoop program on a multi-node cluster, the only thing you need to do is install R Hadoop on all the task nodes with either Task Tracker or MapReduce version 1 or Node Manager or MapReduce version 2 of Hadoop clusters. However, the deployment and installation is time-consuming. On the other hand, you can choose to deploy your R Hadoop program on Amazon EMR, so that you can deploy multi-node clusters and R Hadoop on every task node in only a few minutes. In the following video, we will demonstrate how to configure R Hadoop cluster on an Amazon EMR service. In this video, you must register and create an account on AWS, and you also must know how to generate an EC2 key pair before using Amazon EMR. For those who seek more information on how to start using AWS, please refer to the tutorial provided by Amazon at Perform the following steps to configure R Hadoop on Amazon EMR. First, you can access the console of the Amazon Web Service. Refer to this link and find EMR in the Analytics section, then click on EMR. You should find yourself in the cluster list of the EMR dashboard. Refer to this link. Click on Create Cluster. Then you should find yourself on the Create Cluster page. Refer to this link. Next, you should specify cluster name and log folder S3 location in the cluster configuration. You can then configure the Hadoop distribution on Software Configuration. Next, you can set up the software configuration and choose the Hadoop distribution you would like to install. Amazon provides both its own distribution and MapR distribution. Normally, you would skip this section unless you have concerns about the default Hadoop distribution. Next, you can configure the number of nodes within the Hadoop cluster. You can then configure the hardware by specifying the master, core, and task node. By default, there is only one master node and two core nodes. You can add more core and task nodes if you like. You should then set up the key pair to log into the master node. You can then specify the EC2 key pair for the master node login. To set up R Hadoop, one has to perform Bootstrap actions to install R Hadoop on every task node. Please write a file named bootstrap rhadoop.sh and insert the following lines within the file. You should next make a file containing all the start scripts named bootstrap rhadoop.sh. After the file is created, you should save the file in the S3 storage. You can then specify custom action in bootstrap action with bootstrap rhadoop.sh as the bootstrapped script. You should upload bootstrap rhadoop.sh to S3. You now need to add the bootstrap action with the custom action and add S3 location. Next, you can click on Create Cluster to launch the Hadoop cluster. Lastly, you should see the master public DNS when the cluster is ready. You can now access the terminal of the master node with your EC2 key pair. Google also provides its own cloud solution, the Google Compute Engine. For those who would like to know more, please refer to this site. Awesome! We have successfully configured our Hadoop clusters on Amazon EMR. This video concludes the last section of this course. I hope you enjoyed watching this video.